Hi guys, my name is Amelia and I'm a member of FRC Team 3132 and we'll be taking over the second stream of the 24 Hours of STEM. So our first speaker will be Travis Shu from FRC Team 971 who will be presenting a CAD style guide. Welcome Travis. Hi Travis, how you doing?
Doing well.
All right. You excited?
Yeah, good to be here.
Yep. All right, well, once you're ready, you're good to take it away.
Thank you. Hopefully this is sharing through.
Yes, all good.
Great. So thanks everyone. Hello, my name is Travis Shu. I'm a mentor with Team 971 and I've been a mentor for, I guess, the last couple of years. So for my presentation today, I'm going to go through, what I would call a CAD style guide. This really is borrowing from, the concepts with programming. You might have, if you done any programming, you might have heard about a style guide. Really, people have gone out and talked about what it looks like to make good code or bad code. And really, I think that there's it's something we should be talking about with CAD too. There's good CAD and bad CAD. But I think that the one difference is that, with CAD, as soon as you get to like the drawing or the parts made, like it doesn't really matter what the model looks like. So I think people don't give it as much focus as it's due. But I think in the process of designing and building robots quickly, it's important to pay attention to how you're CADing things and not just what you're CADing. Before I get, so I'll go through and talk through that more throughout the presentation. Before I get started, I just want one disclaimer up front. All of this presentation was done referencing SolidWorks because that is the platform that we use we've used for our robots. But a lot of the concepts that I'll talk through will be applicable to other platforms. Be it something like Onshape or something in the Autodesk family. So to get started, I've got two parts up here, once as you're looking at this, I want you guys to think about, what are the differences between these two parts? I guess it's kind of a little bit of a trick question, but there really actually isn't any difference in the geometry of these two parts. The difference really lies in how the two parts are made, and you can't see that unless you really dig into the file and look through what the feature tree of how the parts are made. So same geometry, but two different ways to get there. On the part on the left, you'll notice that you have a lot more features to get to the same endpoint, and you have a couple broken features in there. So the one on the right is a pretty streamlined feature tree. The one on the right will be it was both easier to create and will be easier to maintain. And so why is that important when building FRC robots? Well, really, no one really gets to design right the first time. So you're gonna have to come back later and update things. Just be it, change lengths of something as you shift around, a mechanism when you figure out that something's interfering. Well, you need to go back and edit it and move it around and stuff. Well, as you're going back and editing parts that are built better are going to be faster to edit, and you're going to have less errors in there. So really, I think it's important to, as you're building parts, pay attention to what you're doing and try to get that right. So we'll dig a little, you can dig a little bit more into that. And in this example, let's say you come back and you figure out you have too much, your shaft's too short for your gearbox. If you made it, it wouldn't all fit together. Now you need to go back and change it. Well, in the second part, going and changing the length of the shaft, you'd go into that base revolve feature. All of the dimensions that you might want to change, or most all of them, are all pretty clearly laid out. And you can go in there and it's pretty easy to see where the link's driven from and to change that. On the part on the left that was on the left, to change the length, you actually have to go and you have to find the extrude that the length was set in, and then you have to go and you edit it and change it. And it's just going to be a lot, it's a little bit more confusing and not as clear. And if you wanted to change multiple dimensions at once, it's kind of hard to see how they play together. So the part I'm going to say that the part on the right is a lot easier to update and maintain, and also easier to make, and is the type of parts that we should be striving for. So I'm going to go through a couple of different things here. I'm going to start by talking about this philosophy of capturing design intent and go through what that looks like. I'm going to talk about how do you go about making models that are easy to update, how to go about creating robust references, and then a little bit at the end about some tips and tricks for working quickly. That's kind of more specific to SolidWorks. So first, starting with capturing design intent. What does that mean? So let's say we're designing a part. Well, I guess I should probably, before I get in there. So capturing design intent really is about create. The idea is you want to create the way you create the part should reflect, what the part is trying to do. And if you structure the way you structure the part file like you're trying, the part's physically structured or as the part is used, it'll be easier to make and be easier to maintain. So what's an example? What are the different ways you go about doing that? One of them is you want to start with the features that capture the design essence and then build out from there. And that will give you, that kind of sets, you up with a solid foundation for the piece. And everything it makes it so that things logically cascade. So, the first thing that you want to, think about it is, what is the job of the part? And so for the part that I'm going to talk about in this, this assembly in particular is going to be this potentiometer mount here. And so you look at the part and it's got a couple things that it's doing. It's got to mount the potentiometer. It's got to hold it a certain, it's got, has some tensioner slots in it to allow us to be able to set the right tension on the belt when we hold it. And, it's got to be, when we're mounting the potentiometer, we've got to be able to, do that so that the belt lines up between the pulley on the potentiometer and the pulley on the shaft. Those are kind of some of the main features there. And now we can kind of, look at the piece here, and, there's different sort of ways that we could start CADing it. And I think, with this sort of, this simple 2-ish dimensional part here, you could either start from, the front profile, that view on the left, or you could start from the profile on the right. And really, I postulate that the thing to do is to think about, what are the most critical features of the part, and then start with the view or start from the perspective that captures that critical feature the best. So kind of listed out a couple different features there. We'll list them out here, and kind of the different features that we talked through. I think that kind of the two main ones are holding the potentiometer at the right belt pitch and spacing, and then the second one would be holding the pulling alignment. And that first one of holding it at the right spacing, that's probably the prime. I would think is the primary function of this part, and that's going to choose or that's going to determine which view we start from. And so the view that captures that better is the view on the left there, and that's because it captures both the mount point for the potentiometer and then the holes, and the mounting holes are the slots for that. So what does that look like in practice when we actually dig into building the part itself? Here's the sketch of that part there, the first sketch there, and you see really it's about taking those key features and then laying them out and then putting together dimensions in there that really are about capturing the key functionality of the part that we're trying to do there. So a lot of different ways. It's one thing that you put the geometry down there. We have 2 slots and the outside profile and the circle. Not a lot going on, but there's a lot of different ways that we could have chosen to dimension these parts. And so the way we laid it out is kind of trying to focus on some of those key functions and make them easy to, make them explicitly defined with the dimensions and make them easy to update. And so, I think one of the key things here as we're designing this is this dimension here, which is the distance from the pot to the mounting holes. That's something that, as you change the belt length or you change where it's mounting to the gearbox, that's something you're going to want to be able to easily update. Then some of the other key things in here, we've got the spacing between the 2 holes. That's critical for that's critical for how it mounts in. You need to have the same spacing on the two tapped holes in the gearbox plate. And kind of working out from there. Some of the other things is we've got the throw of the how much slops or not slop but tensioner range do we have on the adjustment slot. What's the diameter that we're mounting the potentiometer to? What's the overall size? You can kind of you can see you can sort of start from the core dimensions and the features, dimension those, and define your way out from there. And so this is the first feature in that part and that first view. And then once you do that, then we can talk about creating that second view, really. And what's going on here is that to be able to mount the potentiometer and the pulley at the right spot, the part has, the pulley has to be inset some, or the potentiometer has to be inset some from the face of the gearbox, and that's achieved by this cutout here. And so that's done, in that second feature there. Here's another example. Just go through it. I think there's an important point, so go through it with another example before we move on. We'll look at this part down at the bottom. That's this it's this clevis that's mounted to the end of a tube in our 2019 climber. You can see there's a couple functions going on here. And this part, the clevis needs to be, it needs to hold a pivot. We're going to be holding, we're mounting it to some putting on some bushing for rotation. There's a bolt that's actually holding it in, and there's some features and there's the clearance associated with getting that bolt to locate in. And then we have this boss on the end of it that's used for locating it into the piece, so that we can get reasonable alignment there. We can sort of take this piece and we can think about it. There's three different, it's a rectangle. There are three different views that we can look at. We can look at a top view, we can look at a side view, or we can look at a front view. And we could start the model from any three of these views. So really, goes back to that same theme of think about, what are the key jobs of the part, and what's the order of priority on them. And then we'll use that to choose which direction we come from. So of those three things that I went through, this is the order that I chose to prioritize them. Really, that pivot geometry, I think, is the most important, sort of function of this part. When both the size and the size of that pivot, and then where it's located, relative to the rest of it. And maybe you could maybe one and two could be switched around. You could argue either way, but I chose to route it route it this way. And then the third is, I think a clear third is here is the locating it to the tube. So then let's walk through how that plays out and how the part's set up. So here we go. This is that view on the side. And you can see that we're capturing some of the key features here in the dimensions. You'll notice that you'll see that we have the diameter for the hole that needs to be interfacing with the spacer that's being put through here. We have the width of the part, which is designed to match to the diameter of the tube. So that's kind of tied into sort of the next phase, the next step. And then from, there's different ways that we could dimension sort of this height of the part and where the hole is. And, I choose to split it out into two dimensions, instead of dimensioning an overall height and maybe a location of the hole from one of the edges, really chose to split it out into two parts of the distance from one edge and the distance from the other edge. And really the total length of the part is the sum of those two decisions. There's regardless of how we decide to change the how much space there is between the mounting point of the tube and the clevis, the clevis pinhole, we're still probably going to want the same distance on the other side to the end, and that's going to determine the wall thickness of the piece here. So really split them out into two sides. That makes it easier. If you want to go in and update it, if you want to update the pivot hole and make that further out, maybe you figure out you need more clearance for the screw head, and when you put it all in the assembly, there's one dimension to change instead of having to change maybe two dimensions. So that's the first part. We did a boss extrude off of that, and then now we're creating the slot that's capturing the clearance for the bolt. Really, I guess we could have done this from either the top or the side. I don't know, if I was to do this again, I might do it from the side. That might be a cleaner thing, because then you can kind of control the depth of that, and the width and everything in one view. But this is what we actually chose to do during the season, and you can see the key dimension here. It's really just everything else is constrained by relationships, but the key dimension is the width of that. And then the last view, the last feature that we talked about was adding that locating boss. And that's done as an extrude off of that face. It comes last, and you can see that only key dimension left at this point is the diameter that's interfacing with the inside diameter of the tube. So that's kind of walking through those two parts should give you an example of how does your understanding of and your thinking about what the part's going to do tie into and then influence how you go about CADing the part itself. And I guess two more examples before we walk on these, move on. Some parts it's pretty obvious, which way you start. If you're doing a lot of flat plate, either laser, router, water jet, it's pretty clear which view you're going to start with. It's really it's a two-dimensional part. You're going to start with a side view, and then similarly, if you're making a part on a lathe, often the main view that you want to start with is with a cross section of a slice of the part, and you base a revolve onto that. So these are, I'd say probably 80% of the parts that we do fall into one of these two methods. So it's good to be thinking about this and good place to start. Next point I want to go through is that when you're designing more complicated parts, and there's different sort of features that are playing between each other that need to be balanced out to be able to make the part work. You want to try to capture those features in one sketch. And we'll talk a little bit more about this later. And there's this balance between you can have one sketch to rule them all that has everything of the part in it, that has the ultimate amount of flexibility. You can go and you can reference anything to any place, any one place to any other place, and have it so they update through SolidWorks magic. But the downside is that it becomes as you get to more and more complicated parts, it can become particularly unwieldy to be able to manage that. So really when I'm starting parts like a gearbox or something like this, thinking about what are the key features that are interdependent to each other, and how do we then get them together in one sketch so we can make those design decisions and use the sketching tools and to be able to trade those decisions on. So this here is a picture of our 2019 intake roller, and showing. We'll look at this gearbox in a little bit more depth here. And if we think about what are the key features or functions of that gearbox, well, and the things that we need to relate together, well, we've got the location of this front structural tube. We've got this motor that needs to package both behind that tube and above the wheels. And then we have this added constraint of we can only where we place the motor is dependent on what gears we're using and where they are. And so we need to be able to locate the gears and this intermediate axle in the right spot. So how do you take that and how do you put it into capture that in a SolidWorks sketch? Well, really, the way we chose to lay this out is we actually. The first sketch is not actually in a feature. The first sketch is really just a layout sketch that is taking these core intertwined features and choosing how they all reference to each other. And so you can see in here some of those key features that we are looking at from that isometric view. We've got this front tube sitting here. We've got the motor. We've got the gears modeled in. We've got the sizing and the pitch diameters of the gears, and then modeling in the little the nominal gap for allowing for some tolerance on that. We've got the wheel here, and you can see where as things are laid out. We try to put sketch relationships or put dimensions in between things that are capturing sort of the key things that we're thinking that we care about, and working from well, what are the most important things, and then letting SolidWorks kind of run the optimization to figure out, well, what does that mean that where all the other parts land. And so kind of walking through this piece here, obviously when and then first started putting in all the sizes that are constrained by the geometry of the pieces that we're using. And then as we start sort of putting these three main cylinders relative to each other, the first thing it kind of started with is like, well, we've got this tube, and we want to sort of constrain the wheel relative to the tube. And sort of two main thoughts on that is that, well, we want the wheel as close to the front of the robot as possible. So that we can get that, acquire the ball as quickly as possible. But we wanted some gap there so that when we run into things, the tubes take what's taking the hit and not the wheels. In this case, probably, we left about, half an inch of clearance there, because thinking about maybe the tube gets dented, maybe, there's some deflection, maybe the thing we run into isn't perfectly straight, leaving a little bit of margin on that, because we didn't need to cut it super close. So we put half inch there. And then similarly thinking about, well, we need the wheels not to run into the tube, so we need some clearance there. Chose 3/8 of an inch there, and that's kind of driven by, it's also a similarly sort of conservative-ish number there, because thinking about, well, the tube, there should be a mile between the two, there should be no problem there. But what if the axle gets bent? We want the wheels to still spin, the intake would still function with a bent shaft, but as long as it doesn't start hitting that tube. So pick that number there, and then needed to sort of constrain the gearbox. Said, well, it actually starting to look like we probably just put the gears in a line, so constrain the gears to be along the line. And then last thing is deciding the clearance between the motor and the front tube. Well, they're not moving. They're pretty static relative to each other. We just can put something that's a nominally small distance, but that's maybe small to the human, but ginormous to machine tolerances. And chose I don't know why, but chose 80 thou there. So that's kind of that's walking through sort of how we could go about capturing the design intent in a sketch. So that was the first sketch in this part, really laying that foundation there. And then, once you got the interdependencies, now we can build the part on top of it. And, you can see that profile, comes on top of that and is referencing all of that sketch sketch relations, in the other place. And you'll see things like, having the plate, the outer profile of the plate is referenced as having, just nominally larger than the tube, and also becoming nominally lower than the gear. So we don't hit the gear. So in these, this is kind of, one approach, and we could have put all of these sketch, could have put all of these, lines in that previous sketch and started our extrude from there. But, sometimes it's just simpler to not clutter up that trade-off of like trying to figure out where everything goes, and leave the profiles and leave the bearings and things like that to a later feature. This is kind of an extreme. That was a simpler one. This is kind of an extreme here. This is our 2018 monster gearbox for the arm. And a lot of things going on in this assembly. A lot of different gears that needed to all work out. A lot of motors that couldn't. We needed to make sure they didn't run into gears and chains and sprockets and things. And so this is sort of the first feature in the sketch here. I guess, yeah, it's the first feature. And really, the profile of the gearbox isn't even there. It's just like a box that's kind of like a placeholder. There's a lot of stuff that's packed in here to try to make sure we get all those, so that we can leverage SolidWorks to get all those interdependencies. And, some of the things is, down here, it was actually important where the motors went, based on where the wheel is. So we modeled the wheel in there, put in the arm motors that are going to get added in and, kind of made official later. Sketched in where the drivetrain motors were, because the the third arm motor was located relative to those two drivetrain motors just for kind of a clearance issue. Modeling in the chain paths to make sure that the chains are clearing all the motors and the gears and stuff, and showing in the sprocket. So a lot more things got that's kind of some highlights, but a lot of stuff packed in here. And really, SolidWorks was a real partner in figuring out how the heck can you get all this stuff to fit and not run into each other. And this is a key part of being able to do that. And then, another thing, I'm not showing the base sketch here, but here's showing us kind of a moving sketch on top of a linkage sketch. But you can also use the sketches to figure out, to lay out how linkages work, and make all those trade-offs there. Another thing, kind of moving on from there, one of the things that, as you're making a part, we kind of talked a little on this earlier, but really as you're choosing the dimensions, you want to choose dimensions based on what you care to control, not based on what's easy, or, what's necessarily maybe the easiest or the simplest thing to be doing. Sometimes it pays to take a little bit extra effort, and go through and dimension it based on what, how the part's used or how it's supposed to function, because then, you're able to capture sort of, it's easier to update it because, you're updating the direct things you care about, and you have to probably update them less often. So here, this is a piece that was in our 2018, one of the pulleys that we made for the cable drive, and the cable will terminate. There's a block that terminates cables, and they're basically wrapping around the outside, coming into the middle, and going there. So what are the key functionality of the parts? Well, we need the cable to fit through a gap. Well, we should probably control the minimum width of the gap. So that mention that directly. We have some minimum bend radius of the cable, so we're trying to respect that, and we're mentioning that explicitly there. And then we're thinking about, we have the OD of the part that's going to determine what your ratio is there. And then last we have the thickness of it, which is determining both the strength of it, and how much it weighs. So trying to balance the two of those. This is the one on the left, is what we actually, used in the robot. This is kind of a hypothetical exercise of showing how you can get to the same answer at the end. But the same geometry, you get the same piece made. But the one on the right, really is kind of not capturing the core intent. And it's going to be a lot harder to update. You'll notice that the gap is kind of controlled by the combination of this, this center to center distance on the radius, or on the two circles, and this, semi, arbitrary distance between the 2 points of the circle. And likewise, we have an inside and an OD. I'm going to postulate in this side, we actually don't really, we're not trying to fit anything in the ID. So if we actually want to try to thin out that wall, or if we want to change the OD to make it a 6.5 millimeter or 6.5 inch diameter pulley, we have to go and change 2 dimensions to keep that up. So to make that happen. So really, both would get the job done, but the part on the left is going to be more robust and easier to work with. Another thing, kind of mentioned this briefly before, but as you're going through, we've been talked a lot about dimensions. Dimensions I see as our secondary control feature. Often we're trying to figure out how to use relationships to capture how the geometry of the piece, how it all relates together. So here on the left, same thing as last slide. We have 2 parts that are doing exactly the same. The 2 models that are doing exactly the same thing, creating the exact same part, but they're doing it in different ways. So the one on the left is using a lot of relationships to capture that, all of the circles are the same, the same diameter. The part is centered in here. It's set. The holes are centered left, right, and on both the top and the bottom. And then also, these top holes were designed to be, on the outside of the part. Well, you could define all of those things with dimensions. It's just going to make it and you get the same thing, but it's going to make it a heck of a lot harder to keep track of things as you update things. So if we wanted to change the size or anything, most of the design intent is captured in the dimension, or sorry, in the relationships. A lot of it will update automatically. Where when you end up with a lot of dimensions that are kind of where you should have had relationships, you end up having to change a lot of things to make sure stuff works out. So multiple dimensions to make sure that you keep the same relationship intent. Like a good example of that would be, well, if you wanted to space these bottom holes further apart, you'd have to change both of these 2 dimensions, and remember that the left was supposed to be equal to the right. So better to use relationships when you can. And this is kind of showing another, further example of that. We're kind of cutting this relief profiling that doesn't really come through super well here. But using a lot of relationships to kind of show that, like, you have parts that are concentric to each other. You have each of these patterns are similar to each other, and then they're spaced out even to each other. And so not many dimensions driving this. Most of the control in this part is coming from relationships. Another thing that that helps in making robust parts is using construction geometry as a tool to sort of lay out where your profiles and everything comes. So we'll use construction geometry to kind of you can use it to provide relationships and in between things, and capture some of those the things, stuff like that making 2 things even. You can use that's what's happening on the left here. These construction lines came in to help locate and down the holes, and you can also use it to reference or to demonstrate what the part's interacting with, and create a reference point that you can interface to. So this here is a tensioner block that was used in our 2019 drivetrain, or a template used in our tensioner system, and it's interfacing to the drive rail, a 1x2 drive tube. So we can, what we've done here is we've just put the drive tube in there as as an construction line, and there's a lot of stuff that then gets referenced to that. Like you have the location of the the location of the center bearing hole is referenced relative to where that tube is. You have the location of the bottom, the standoff that's mounted on the bottom is referenced to the bottom of the tube. There's this plate here that goes in here that's that you need a gap thickness. And it's just a lot more convenient to be able to these dimensions are these parts interface to the tube, so it's easy. It's about that easier in the design if the dimensions also interface to the tube. So here's that's a good example there. And then kind of as you get more complicated in here, you can do, you can do a lot more. This is, maybe a similar, example to that gearbox I showed earlier, but actually taking the alternative decision of, we need to put, the profile and the gears and stuff actually in the same sketch. And really, I think that the reason that drove that in this model as opposed to the other model is that really the outside profile and the location of all the gears and everything are intercoupled to each other. And so it was important that, to be able to relate them together, they had to be in the same sketch. In order to interrelate them, they had to be in the same sketch. And you can see sketch geometry here is being used for putting in place, like, we have all the pulleys and the belts and the motors and the gears, and we're able to lay out the location of all those components and make sure that they're not going to run into each other. And then there's a lot of iteration that happen, and tweaking of numbers to try to figure out the size and the shape that would fit everything. And then there are other things. This intake was designed. We thought this was for our 2018 robot. We thought that we might have boxes on the top of our robot that we'd want to be able to spit through the robot. I can't remember why we didn't actually use that feature, but we were trying to really keep the profile of this such that when the intake was folded in, that the boxes could clear. So that's really, what's drawn here is showing that constraint and that relationship there. And then we also wanted to make sure that the corner of the box couldn't catch on the plate, that it would always contact the wheels. So that's showing this relationship here also. And then obviously, we had to make sure that all the as I mentioned, to make sure nothing intersected. But here, really, the power of sketch geometry is that, or construction geometry, is that you can bring in all of these things that are kind of virtual to the part and create references to them and work through a lot of, the intricate math of or the intricate optimization of how things are located. So another thing that is I think important to pay attention to is that as you're building your part, you want to place the origin and by as a consequence of that, the planes, the major planes of the part, you want to place those in a spot in the part that's logical. And that's kind of I guess a subjective term, but really if there's symmetry in the part, you want to be able to take advantage of that symmetry. And also, if there's a, if there's a, and you also would like to have the origin sort of, first I look for a symmetry, and if there's symmetry, then that should drive where things are. And then failings, if there's no symmetry to base off, then you kind of look for what's a key feature of the part that you can then ground it to, like, maybe the wheel, or, the center, the bearing hole of, the output of the gearbox. Those are things that are kind of, everything gets referenced to, or a lot of things get referenced to that. So putting that as the origin makes sense. And the reason that it helps to put things, put the planes in the middle of things is that as you go through, then you can, as you're doing your sketches, you can put in a, like a construction line and make it, have it go through the origin, and, put the midpoint through the origin, and, now things are, balanced. They're naturally, they're naturally symmetric about the part. Or you can use the planes and create mirrors off of things. It gives you a lot more options, and, often is you can make more robust parts if you kind of think deliberately about where you put your planes. And then a couple of and this is kind of helpful, I guess, with placing your planes. But one sort of thing that I find helpful when laying out parts is that as you're doing the boss extrudes, or some of the features, pay attention to all the different options that are in there. And there's a lot of different options in both this from option, which is talking about where does that feature start, and there's also a lot of options in the direction, which just talks about where does the feature end. And you can use these options to kind of really go back to capturing the design intent, and making the part easier to being able to put those features into the part with fewer features and less complexity. So often it starts from sketch plane, but really depending on what you're doing, you could these other three all make sense too, and we'll use all of the different options on the other side. So example of what that looks like here. This one's pretty straightforward. This is one of the parts that we showed earlier. You want to take advantage of the symmetry in this piece. You'd like to put the one of the planes right down the middle of the part. But you gotta start with the extrude. And if you just left it at sketch plane, or sorry, if you just left the direction as blind, you wouldn't end up with that. So a very common option here is that you will use mid plane a lot when starting things, to be able to put put the origin in the middle of the part. That one's helpful. And then another example here is this one's actually using the from option, and we can choose. We can choose where we choose an offset to start with to really this is what this is capturing, is that we have a nut pocket in this piece. This is going to be a printed piece. We want to hold a nut pocket to capture it. We'd like some thickness left to be able to for the nut to actually be able to clamp to something. But we started the sketch on the bottom of the piece, so just a straight extrude cut would leave us with a nut hole, not a nut pocket. But by using the offset, we're able to start that feature up a bit. And do it without having to create an additional plane or something to do that. Another thing that helps here, that helps with making robust parts, is a piece that we saw earlier. But you want to when you put adding in dimensions, we talk about adding dimensions to capture really what's important and what the intent is. Well, one way to do that, one thing that helps with that is using appropriate arc conditions for dimensioning circles. So the example is right here. This wheel to tube gap. Really what we're doing is we're directly dimensioning the gap here, rather than dimensioning the circles. And you'll note if you use SolidWorks much, you'll note that the default is if you click on these two circles, it's going to put a dimension between the center one and center two. Well, that does constrain things. That means is if you decide to put a different tube in the front of the robot, or if you decide to put a different wheel size on, it's going to change what that gap distance is. It won't automatically update. And also you have to do math to figure out well, what is that actual gap, and if I want to control it. So it's easier to be directly dimensioning that. And the way that you can do that is you actually just you can dimension between the two circles. It will default to going to the centers. And then you go place the dimension, you go click on the dimension itself, and then under the second tab of the dimension thing, go down to the arc conditions, and you can change the first and the second arc condition. And in this case, both of them are min. You can do the same thing between a circle and a line, and you can choose the min there. And then a shortcut to putting this in is if you hold down the shift key while you're selecting circles, it will give you an option. It'll kind of you'll toggle between them and let you place it down. So that's and I use that feature. It's pretty quick for doing that, and it becomes second nature. So a lot of things we went through there on capturing design intent. A lot of things to go through. Just a summary here. You can look through it afterwards. Now I'll talk a little bit about more about making models easy to update. And the most important thing in this is that really make sure that all of your sketches are constrained. This is coming back to that part from earlier and showing the first two, these curves are not constrained. You may say, well, it doesn't really matter what these curves are. They're just put in place because it looks want some transition there, and this looks reasonable enough. Why does it matter? Well, what can happen, if you don't constrain it, what happens is that someone could open it up. They could be clicking around, looking at what's going on, changing maybe one of the dimensions down here that's not relevant up here, and they could accidentally just drag it and save the part out of that, and you don't know what happened. It was an accidental change that ended up with a bad effect. So really, it doesn't take that much work to constrain it. If you don't know what you should constrain, we'll just make something up, take some liberties on what to do. That's called intuition. And you'll kind of get a sense of what works well as you go. And another key thing here is if you make it easy to update, if you pick what you pick is wrong, like let's say you go into the assembly, you're like, oh shoot, that this curve is going into the plate. Well, you can just easily change it there. And I think that one, having no blue dimensions is good from the perspective of making it so the part actually doesn't accidentally get changed. But I think there's a secondary thing that happens that actually forces you to think through sort of how all the part is, what the part is doing, and sort of the cascade of the different constraints of why of what its functions are, and going back to that theme of working through from the most important thing to the least important thing, and you're done when you have no more blue lines. Another thing that makes parts easier to update is that when you're adding, often you add fillets in. You certainly need to add, or for most manufacturing methods, you need to add internal fillets to be able to make it manufacturable. And then often we add external fillets so that part looks better and we don't like cut ourselves. And there's different places you can add the fillets. You can add the fillets in the sketches using even the sketch fillet tool, or sketching them in yourself, or you can add them in as features. I like to, I think that it's more robust if, and easier to update if whenever you can, you add the fillets in as features. It makes the sketch simpler. I think it makes it a little bit more robust from just a solid perspective, although you don't really run into those problems these days. And it's easier to kind of isolate them out if you wanted to sort of change them or delete them. And it just, I think the main thing here is it doesn't clutter the sketch as you're building things out. Another thing, kind of, they'll take, this part here, you look down at the end final part here, you could have done that in one mega sketch. And, it would have worked. But really, that doesn't create a part that's easy to maintain. And really, as I think about building out parts, you try to chunk things out into, the things that, based on, are they interrelated? You have interrelationships between the different geometries, and also thinking about breaking things up by function. And kind of, if you have multiple different functions in a part, sometimes it's easier to have them, or I find it's often easier to have them, implemented in different features. And this means that, as you're kind of debugging them, you can go through and you can focus in on what's happening as you're changing things. And also, if you decide to change how a part works, and you need to delete something, well, it's probably, often one feature, and you can kind of, and you can just go and delete it directly. So, the balance here is that, if you have too many features, then it becomes, it becomes unwieldy in the feature tree. If you have too few, it also becomes unwieldy in the sketch. So here's showing us walking through. We started with the outer shape, added some spring mounting holes, added the bar mounting holes, and at the end, then lightened and added fillets. So kind of broke it up into 4 steps there. Here's an example with adding in vent holes for a motor, and adding in this, this pinion axis hole. They could have added them in the previous sketch with the gearbox, but it's just simpler to add them in afterwards. And then, in this case, both cases using a circular pattern to kind of interface them through. Another thing is that, kind of along this vein, is that, the lightning should always go last in the part, in my opinion. You should do it after you're sure that the part works, because, it's kind of, lightning doesn't always update when you change the geometry. It doesn't, sometimes it'll break, and then you kind of end up stuck in this position of redoing work. And also it's kind of distracting, because it doesn't, if you do that, and if you do it too early, and then you start changing major things, you spend all this time lightening it, and then you change the major thing, and then you figure out it didn't actually do what you needed to do, you just kind of wasted all that time. You kind of go back and forth. So, we'll leave it to the end, and then you'll see that, in this case, this is, the parts are all done, and then in the feature tree, there's all the lightning comes there. Another thing that's great is, it makes parts robust, is if you can use, if you can use sketch, mirror features and linear features in sketches, but I find it to be more robust into using those in features. So this is kind of showing an example. If we want to put in all these notches, put in one notch as a feature, and then did a revolve to put the rest in. Here's an example of putting holes in a tube. Put one set of holes in over, I think it was, they're over here, and then wanted to put them at a consistent spacing. And so we use a linear feature, and notice even, use the skip feature to be able to skip the bearing hole, because, we didn't want holes there. This one is one of my favorite, linear patterns, and it's a curve-driven pattern. I think this is a great way to put in interfacing mounting holes. Let's say we have a part of a certain length, and we want to be able to have, a certain number of holes distributed along a length. And so, we can draw that in. This is actually the sketch that's in the hole wizard feature. And then when you go and you can add a curve driven feature on that, and you select that sketch that you select the sketch or the line in the sketch, and it will put as many holes as you want along that line. And this makes it really easy. You can actually, you can define things based on the end. Let's say you wanted your line to set it to be a certain length. You could say, 0.3 inches from both ends. If you make the part longer, the holes automatically change with it. And you can also, it's also easy to go in and say, hey, I want more holes or fewer holes. It updates well. Here's an example of mirrors. using mirrors is a good way. If the part has symmetry, it's best if you put the feature in only one side. Don't use the sketch feature to do it. Or the sketch tools. Just use the features. It takes a little bit of discipline, so I think people usually like to see their part kind of like come to life in the sketches and in the feature tree as you go. But with a little bit of planning, if your part really is symmetric, I think it really does help to go and put all the features in on one half, and then use a mirror feature to put them in on the other half. I think that it makes parts. I think parts become more robust if you use Hole Wizard whenever you can, rather than using a cut extrude. And really, the reason on this is that it separates the decision between what type of hole to use and what location the hole goes. And I think this is particularly helpful for students who are new to CAD and learning mechanical design. Some people, you'll get to, I guess, where you recognize all the hole sizes, but really you kind of know what screw you're putting in, and you know about what fit you want. So why not go and decide that directly? So here we have, a tapped hole with a 1032. Let SolidWorks figure out what tap size hole or what hole we drill or cut in the part to be able to tap it. And then you use, you can dig into the feature, but you use points to be able to locate that, and you can use sketches to help position that. Stepping back to assemblies, as you're building assemblies, I think it's really helpful to make sure that the planes in the assemblies are in logical spots. That's helpful as you're mating things together. You can reference those planes, make things symmetric to them or make things coincident to them as you're doing that. And it's also really helpful when you're doing the cross sections to be able to look at things. This is a drive tube. It's natural to kind of natural midpoint is the wheel, and if we wanted to see what's going on that wheel axle, we can just cross section off that right plane there, and it's a lot easier than having like a plane randomly somewhere. Another thing is to make models easy to update is really, as you're getting bigger assemblies, I think it takes diligence, but be mindful of the if you have errors and broken mates and things, fix them as you go along. Makes it a lot easier to kind of keep good hygiene that way, rather than getting to the point things getting worse and you're like, oh shoot, it's really broken, and now you got to dig through it and figure out how to fix everything. This is an example of the kind of at the end of the season of just, I guess I say that, but just examples right at the end of the season, we usually end up with more broken mates than we'd like to admit, and the stuff looks wonky, but and it kind of becomes becomes unwieldy. This is what is a caution of what we try to avoid there. And I guess really the main reason that I think that it makes sense to avoid broken features and broken mates is that sometimes it's just that's we deleted a thing and the old ones aren't needed, but sometimes something actually really is broken, you change one part and the holes don't line up. It'd be nice to know that before you cut the pieces and try to put them together and figure out they didn't work. So take the broken mate as a sign that, well, maybe something is wrong. Let's figure out what's wrong, fix it, and then we'll move on. So just a summary here. I guess you guys can come back to this later if you want. I'll go through. So this is kind of a big question, as it's a style question within CAD, is how do you create robust references between the different parts? So what's the problem here? You have a lot of parts in a complex assembly. That's basically called a robot. How do you make all those parts, and all the different holes and all the different features line up so that everything fits together? And really, we're looking for something that's easy to create and then easy to update and maintain. And there's really a balance here. Something that's the easiest to create may not be the easiest to update and maintain, and you could spend all the time you save putting in the feature that way could easily get sucked up in the time that you spend chasing down problems and maintaining things. And that's actually, over the years, we've tried a bunch of different things. Particularly with SolidWorks, we've been driven to the simpler solutions because we find that they're the most robust, and that's the most important thing. So what's more robust than just physically update it by hand? So we have a part here, this is 2019 stilts. We've got a tube, we've got this clamp for a belt. The two got to line up. So how do we make sure they line up? Well, we put the holes in the same dimensions in the tube and with the same dimension as in the clamp. And really, the reality is that you don't change this that often. It's not that hard to go through and just put the dimensions in. And you know what? You can never, you have to, it takes a pretty deliberate act to be able to change these so they don't line up. Now the gotcha is you got to be careful and like make sure that you get the right dimensions in the same place, and kind of, be careful as you're looking over things. We tend to find that in general this works out well. Another example of this, this is built out into a more complex assembly. We'll use, so this is sort of the main sketch in the tube that, or in the main sketch that kind of drives all the linkage geometry in that part. It's actually, I think, captured in the tube here, or I can't remember, it doesn't matter. So we have the main sketch that captures everything. And then you'll notice that like inside are some pretty key dimensions. That are sort of the key geometry features that interface into other parts. And so an example here is that we've got this one of the link members up top is dimensioned explicitly with this link here. This link dimension here. And then another one is sort of the key thing is where the pivot is located relative to the tube. And when you in your base sketch where you're sort of laying things out, if you kind of make the things, the key dimensions, defined deliberately and easy to kind of, easy to see, when you build the pieces that are kind of based on this sort of strategy that you laid out, it's pretty easy to just take that number and just copy it over from here. And if you go back and you change your, you change your linkage geometry, let's say you want to make this 1.3, well, just come into the plate and make it 1.3 also. You change it in one spot, so you go and you change it to I find this pretty easy to be able to do if you're paying, once you get the hang of it, and it's pretty hard to, it's pretty robust to like big complex assemblies. Another thing that we've been doing more recently, as have more interdependencies between things and interrelationships, been using a lot of multi-bodied parts. This is nice because this puts all of the constraints and relationships are in one piece. So these are actually two designs. One is over here on the right is the 2019 intake, and this on the left is the 2018 mega gearbox. I think that from in terms of this strikes the balance between having relationships between different pieces, but not having a mess. As compared to maybe in context features or in assembly context features. All of the things in the relationship that you care about are in one place, and it's easy to sort of keep track of them and not accidentally screw something up. But kind of the downside is that at least in SolidWorks, it's harder for people to work together. You can't have one person work on the outside gearbox plate and the other person work on the inside one because they're in the same part file. Onshape actually, is great for this, and I know a lot of teams are moving to that. Onshape's great because one of the core philosophies of Onshape is using part studios, and part studios are basically glorified, fancier multi-bodied parts. And the natural advantage of Onshape is that multiple people can work on that same part at the same time. So it's kind of solves all the problems, and honestly puts things in a nice spot. But in SolidWorks, we kind of we'll kind of work through with this. And so just sort of key features of one, how do you do multi-body parts? Well, the main thing is that as you're making an assembly, when you down at the bottom of the option tree, or when you make a part during the options, there's this box that says merge results. Most times, that box is checked. Well, if you uncheck it, well, it creates another body, and that body is basically like a part within a part. And then once you have the different body and you start adding features, like let's say we want to put this hole, but we only want the hole to go through one plate. Well, then when you do an extrude cut, there's down at the bottom there'll be this feature scope box, and you can select which bodies it acts on. And then when you get to drawings and making cam files or things like that, what we'll do is we'll create multiple configurations within the part sub configuration, so they link into the main configuration, and then add a feature down at the bottom that's a body delete keep, and then we'll just keep the different bodies and just sequentially go through each of the different bodies and create that. Another way that's somewhat reasonable about creating relationships or references is by using different configurations. This one, it's great if there's a small variation between two different plates. Like let's say you have two gearbox plates and one's only slightly different than the other. When you have larger variations, like this is showing a pretty large deviation here, I find that you just kind of lose track of you just miss things at some point, and it's kind of get lost in that. And so, it's probably easier to switch to multi-body parts. So this is kind of a summary thing. These three that I went through are really the solutions that we find work the best. The multi-body parts and the updating by hand are, they got the green checkbox. Configurations are okay. And then things we tried that we don't like, in context features, master parts with split bodies, equation linked dimensions, and layout sketch blocks. Those are things that, they technically work. They maybe are faster to do, or they update faster, but we find that the time spent chasing down the brokenness does not outweigh the time that is spent that you spend updating things. Now I know I'm running out of time, so I'll quickly run through these last things. Tips and tricks for working quickly. Main one is learn to use the shortcut keys. Really, this enables you to work quickly. This is not the first thing I do if I was to teach. I was learning SolidWorks, but really, it's about once you get comfortable with design, this is letting you about this sort of minimizes the time that you spend working with a tool, and maximizes the time that you spend, or minimizes the time you spend using the tool to make the part exist, and maximizes the time you're thinking about what part do you want to make and how is that part going to work. Because really, SolidWorks is a tool for bringing design thinking that's in your head and putting it into design and then making parts. Another one, going back to the theory of linking things with dimensions, it's really easy to update dimensions by double clicking on the face that created that dimension, or the face that created that feature that had that sketch in it, and then you can double click on the dimensions and you can update them. You can do this in the assembly. So going back to that, just update things. This makes it really easy. You just double click on both of the parts and you can boom, boom, change both dimensions, and it updates it well. Probably saw this through a couple places. Future self really appreciates when past self labels things, because then you can figure out what's going on. Like this is labeling, like, hey, that's a motor, that's a gear, that's a tube. Helps you figure out what's going on when you go back to the sketch and be like, okay, I want to make the tube bigger. Which one's that? It's like, oh, that's that one. And same thing with features. You can label them also. If you want to change, let's say, the side rib holes, well, now you have a pretty good idea of where that is. When looking at assemblies, first thing, if someone asks me to review an assembly and see what's, if I think it's good, one of the first things I'll do is I'll go to all the axles in the part and all the in the transmissions, and I'll do a cross-section view down the middle of that. If your planes are in the logical spot, it should be really easy to do. And then it really gets you to the guts of what's happening in a transmission or anything with a revolute motion, and lets you see if there's gotchas going on in there that you want to address. So here you couldn't really see from the outside, but there's actually a spacer in here that's extra, that's overlapping with a gear. And if your account, if that spacer was half overlapping, you'd probably be in a problem, because you build it and you're like, oh shoot, stuff don't fit together. So this is great tool for checking what's going on. Another thing is, build out a parts library, and use that. A lot of ones out there. I like the one that we've built over the years. We have I particularly like the fact that we've got common fasteners and bearings, with configuration, drive, that are configuration driven. Makes it really easy to put screws in and then change the length of them and say, oh, I want 2.5, 2.25. You can change the length of the screw well easily. As you're laying things out, think ahead on sort of what the assemblies are and segregate it out. It really kind of keeps the things from becoming unwieldy on all the mates, and lets it, makes it easier to work with. Here you can see how this is blown out by assembly, but you can see the different places that we, the different sort of subs. There's a tube, there's a foot. And that's basically, I guess we're at time right here. So there's a summary of all the tricks there, and that's all I had. So thanks for joining today. Hopefully that was helpful. Hopefully you learned something that you can take back and use with the CAD work that you're doing, and make it so that you're building parts that are not just doing what you need them to do, but are doing them in a way that's easy to create and easy to maintain.
All right. Thank you, Travis. That was a great presentation. So I do have a couple of questions for you. Does 971 CAD everything on your robot? Or do you have any advice for young teams about how much of your robot should be done in CAD?
Yeah, think about CAD as a tool to a tool to building the robot. Do what you're comfortable with. We have so much complex interdependent things that pretty much anything that goes on the robot is CAD'd. And that at least, and that plays well to our manufacturing methods, because they all use, we use 3D models for, as the source for everything, be it making drawings for the lathe or making parts on the router. But I would say that as we get later in the season, we'll just take something and cut something out on the bandsaw and see if we got a ball jam. And well, instead of doing it in CAD, we'll like use Lexan and tape and stuff and solve it, and we may or may not convert that back to CAD, or we just could just run with it. So I would see, based on, I think CAD's a tool for planning. If you're going through it, and think about what level you need to plan at, and what's worked well in the past or not worked well, and kind of play with it from there. Oh, you're on mute.
Sorry. What is your favorite part about CAD design?
I really like the design part. I like thinking about how mechanisms work and how to make cool things happen. And I think I see CAD more as it's like the word processor to someone who's a journalist. They probably love the journalism rather than the word processor. I like the design rather than the word processor, than the CAD tool.
All right. How does your team collaborate on CAD designs while working remotely? So are multiple students working on companion parts, or do they work together on the same parts?
Yeah, well, to do that, we switched to Onshape. So over the pandemic, that accelerated our. We've been thinking about doing it for a while, but we did that because we had a lot of new members, and they couldn't really, not everyone had Windows computers, and people were, hadn't installed things, and it was just easier to get everyone onto Onshape. And I think it will really, I think that from talking to people, Onshape really increases the number of students that engage with CAD, and makes it easier to collaborate and move quickly. So I'm looking forward to getting to where we've done a few projects with them, but I'm looking forward to like being in a season and actually designing a robot with it.
Yep. So are there any resources that you would recommend for students that have no CAD experience but would like to start learning?
Gosh, there's a lot. If you go to the Compass Alliance, they've got links there of different series people have done. Yeah, I'd say. Oh, and you can also go through the default tutorials, and the tools are pretty good. I recommend that, like for learning CAD, go through some of that stuff, but then pick things to design, like CAD, like choose things around the house, and like just it looks cool to you. Figure out how to use a tool to make it. And make it show up in the model, in the 3D. And then, that you asked about CAD, but really as a new student, the thing you need to learn is design. The CAD's actually the easier piece, and the learning design's a little bit harder. And that's really, pay attention to what your teams, listen to people, ask questions, look at robots that have worked in the past, try to figure out why they work, and how do they work, and why do they work? What are the different trade-offs that people made, and build up a catalog of things that you've seen that you might do yourself. And then there's also, resources out there where people talk about different design, like walk through how to design drivetrains or elevators or things like that. You can go through those resources and learn some of the fundamentals from that too.
All right. Well, thank you, Travis, for presenting and starting off our stream for the 24 Hours of STEM. We now have our next presenter coming up. Our next presenter is...
Thanks for having me.
Oh, good, Travis. So our next presenter is Jim Ostrowski from FRC Team 971, who will be presenting on camera calibration and helping robots to see straight. Jim, are you there?
Yeah, hi there.
Hi, Jim.
Hey.
How you doing?
Good. How are you?
Good, yeah. All right, so do you have slides to share?
I do, yep.
All right, would you like to bring those up?
Yep.
All right, so if you're ready to start your presentation, then you're good to go.
Okay, awesome, thank you. So my name is Jim Ostrowski. I'm with Team 971 in Mountain View, California. And what I thought I'd describe today is some of the work we've been doing this past season to work on camera calibration. So we've titled this Helping Robots See Straight. The idea is cameras, when you are taking pictures, can do all sorts of things to distort the image. And what we do with camera calibration, the one that I'm going to describe today, the part of it I'm going to describe today is to kind of unwarp things, make things so the robots can see things in the right locations. So just a quick outline of the talk. I'm going to talk about what camera calibration is, and there's a couple different types of camera calibration, so I'll go into that. Talk just a little bit about why camera calibration is important and where we would use it, and then spend most of the time talking about how we've been setting this up in 971 to do one particular type of camera calibration called intrinsic camera calibration. And I should maybe just mention a little bit of my background. I've been working in robotics for a number of years, I guess a couple decades now, and in particular have been doing a lot of work with computer vision for robotics and working in startup companies, working in academic settings, and currently work for a company called Blue River Technology, which does agricultural robots. So a lot of fun, and cameras are kind of central to this. So a really important area for my work. So starting off, let me just talk about what camera calibration is, what I mean by this term. Whoops, excuse me. So there's really two types of camera calibration. And so I'm going to focus on one of these during the talk, which is this first one called intrinsic calibration. But there's also something called extrinsic calibration. And I'll give a deeper description of this, but very simply, intrinsic calibration is talking about what happens inside the camera. So between the glass of the lens and the sensor of the camera. And extrinsic calibration is really about where the camera is in the world with respect to other things. And that might be other objects, might be where it is located with respect to, say, a robot coordinate frame, but it's external to the camera, so extrinsic. And I did have a quick sketch here that hopefully will help illuminate some of that. And I'll, again, talk about it a little bit more. But intrinsic, again, is the internal parts of the camera, the parts of the calibration. So that's kind of where is the camera centered? What's the focal length? You know, if you think about zoom in and out, kind of how much zoom is being used, as well as lens distortions. And I'll show some examples of this later on, but different lenses, maybe a fisheye lens will distort and warp things differently depending on the type of lens and the quality of the lens. And then there's extrinsic calibration, which again is more external, and that's thinking more about where is this camera located. So if I have some reference frame and some origin, it's saying kind of where is this camera located with respect to that origin. So I might put a reference frame on the camera and have a reference frame that might be my IMU or some location on the robot like the center of the drivetrain, and saying where is the camera located with respect to that. I also just want to give a shout out for the OpenCV libraries. So it's a set of open source libraries that is really a cornerstone for a lot of classical computer vision, and camera calibration is a great component of this. And so this is a pointer to some of those libraries, and I'll mention a few of the things along the way of tools that we're using that come from OpenCV. And then, like I said earlier, I want to talk just a little bit about why is camera calibration important. It's a lot about accuracy. So with good camera calibration, you can figure out where things are in the world relative to the robot with a higher accuracy than if you have poor camera calibration. For intrinsic calibration, you're very often compensating for things like cheap lenses. So, you know, we don't have the highest quality, expensive, large glass, you know, multiple lens configurations. So there's going to be distortions that are introduced by those lenses. And those distortions, if we don't correct for them, really can influence and lead to poor quality estimates of where things are in the world. So detecting where a ball is or where a goal is in the FRC world. And although I won't talk about it really much, but intrinsic calibration is also critical for stereo cameras when we're trying to, like we do with our eyes, try and triangulate things with two cameras. It's really important to have accurate estimates of where things are so that I can get the right estimates of, in this case, depth, how far something is away. And then on the extrinsic side, it's of course really valuable to know where the camera is located on the robot, right? So in particular, knowing a translation is important. How far it is distance-wise from say an origin of the robot to a camera. But really important is the rotation. Just a few degrees of rotation error can translate to a lot when there's something that might be 3 or 4 meters away. So it can really lead to a large error if you don't have good extrinsic calibration. It also is really nice to have everything brought into one central coordinate frame, and that's what you use extrinsic calibration for. And then I just wanted to mention, maybe not everyone wants to calibrate their cameras, especially the intrinsic calibration requires some effort. So what do you do if you can't do that? And I'll give a little bit more detail on this later on, but you essentially can use hand measured values. Think about CAD. A CAD model will tell you where the camera is mounted with respect to some point on your robot, and you can have the extrinsic calibration calculated that way. I'll talk a little bit about intrinsic calibration, how you can estimate some of these parameters from just an ideal model of a camera. So it's certainly possible to do without getting into a sophisticated kind of experimental setup to calibrate your cameras. And then I won't spend a lot of time on this. Just one more look at kind of extrinsic calibration. Really, again, thinking about if I want to know where an object is with respect to my robot. So I've got some object in the world, and I want to know where it is with respect to this robot. But I'm measuring it with the camera. Then in order to place that object with respect to the robot, I need to know where that camera is with respect to the reference frame for my robot. And so that is the extrinsic calibration. So just to mention that one more time. And there's some really good references on this and just a reference to the figure in this slide. Okay, so let's jump into intrinsic calibration. So that's what I want to focus on. The rest of the talk really is around intrinsic calibration. As I mentioned, that's kind of from the tip of the lens all the way back to where the sensor reads the image, what happens in that. And so there's what's typically called a perspective projection model, and that's what we are using, where you think of a camera as taking a point in the world and projecting it down to the sensor. And the model is one that just basically does some ray tracing. So if I think about a point, and here I've called a capital P in the world, so it has some X, Y, Z coordinate with respect to a camera frame, which is over here C. The place that it ends up in my image is found by just projecting that line, drawing that line to see where it intersects some image plane. And so that's what I'll talk about as an image plane. That's basically the sensor plane. And so for this perspective or pinhole model, we often call it, that has this ray tracing as its attribute. The point capital P projects down to some point in the image. And then some of the things that I'll reference, we usually use coordinates U and V, as I've done here, to reference the point in the image that this object is projecting down to. And that's measured usually relative to from the top left corner of the image. So 0, 0 in our coordinate frame for the image is usually the top left. A couple other things to mention. If I think about this projection model, there's a center to the image. That's taking the camera and projecting the line that goes just straight out from that camera. And that will have its own coordinates. So we call that CX and CY. So that's the distance in kind of the X coordinate direction, which is usually left to right, and the distance CY in the Y coordinate direction, which is top to bottom of the image in traditional computer vision. And then finally, there's the focal length, which is also really important. And that's the distance from this kind of projective point, the center of projection, to the image plane itself. And so that's just a single distance. We call that F, the focal length. And if you've worked with cameras at all, you've probably come across focal lengths, for example, measured in millimeters. You might have a 25 millimeter lens, or a 200 millimeter zoom lens, or an 8 millimeter wide angle lens, or 6 millimeter wide angle lens. So these are the focal lengths of the lens, which are measuring exactly this type of value. And so I'm going to go into some more detail on this, but this idea of perspective projection is that it's going to map this point, again, P, in the real world that has 3 coordinates, down to these image coordinates that are the 2 coordinates, U and V. And so how do we do that? Well, a good way of thinking about that is think about similar triangles, and that's really what's happening when you do a projection. So if I think about how I could set this up, here what I've done is taken that projected view and I'm just taking a slice of it. So let me circle back. So think about just taking a slice just in this case, the YZ plane. So don't worry about X right now. Just think about taking a slice in this kind of YZ plane. And so I'm taking kind of a side view just to make it a little bit simpler to talk about. Again, if I think about that point in the real world, it has some coordinates X, Y, Z. I'm ignoring the X part for now. So it's got some coordinate Z, which is the depth out of the camera, and Y, which is where it is kind of height-wise above the camera. And then if I think about this projection through the image plane, which is kind of where I'm moving the cursor right now, where the V is marked, that's at a distance F from the camera center. And we said the image coordinate, we were going to call that was V. So that's the height of the in the image. And if I just use similar triangles, I know that the ratio between Y and Z, excuse me, needs to be the same as the ratio between V and F. So Y over Z is equal to V over F. Or if I want to talk about what that V value is, it's the focal length times the Y, the height of the object with respect to the camera, divided by the depth. And we think about projection as normally dividing by the depth, and that's the projected part of it. And similarly, if I did it in the X direction, it would be the image coordinate U, which is that kind of the X value, is equal to the focal length times the X in real world coordinates divided by the depth Z, distance from the camera. And that's how projective coordinates work for a camera in this perspective projection model. Almost. So there's going to be a few of these caveats and little twists that we need to add to make it a more complete and realistic model. So a couple more adjustments. One is that that the way I described it, if I had Y equals 0, that would correspond to the point that goes through the center of the image. But I said to begin with that the origin 0, 0 for my image is the top left corner of the image. So I actually need to shift the origin center from being the center to the top left. And I do that by shifting by the pixel value, the coordinates of the camera center. We call this the principal point. It has coordinates CX and CY. And I'll show you how that plays in a second mathematically. And the same, or one other twist is focal length typically is measured in pixels in order to make the units play out here correctly, right? So I have Y and Z are measured in meters or some distance metric, but V is in pixels, it's an image coordinate. So F needs to be in pixels also. So we need to be able to translate from what I typically think of, I mentioned, a 8mm lens or a 200mm lens, which is a metric value. Putting that in pixels, I do that by rescaling this by the size of the pixels themselves. And so there's a little bit of math behind that, but basically the idea is that I can get a focal length that's now measured in pixels that just is by taking the size of the pixel and dividing it by the actual millimeters or depth of the lens. And what's interesting here is because the pixels themselves in a camera don't have to be square, they can be different sizes in the X and Y direction. I end up with two different focal lengths, FX and FY, one in each direction based on the relative size of the pixel in the two directions, because they can be rectangular pixels and very often are. And so that leads us to these modified equations that are the typical ones that you'll see for perspective projection. Sorry, I'm having a hard time with that. Which is that my X value in the image is equal to my X focal length times X over Z, same as before, plus the center, the principal point in the X direction, CX, and the similar equation for V. And that's the projective equations for a camera. So if I want to think about, I know let's say I know the object location in the world and I want to ask, where is that going to show up in my image? Then this is how I could project down to it. The other thing I can do that's useful is if I know all this information about my camera, what my focal length and my principal point are, and I know that accurately, then I can take take a location of an object in image and project the ray out that comes from the camera and do that accurately. And that's what intrinsic calibration is all about, is measuring these parameters for each camera that we've got. So I'm going to want to come up with ways of estimating FX, FY, CX, and CY. And then there's one more thing before we finally get to actually how to do this, and that's lens distortion. Like I mentioned earlier, especially cheap lenses introduce distortion. And you've seen this if you kind of looked at images, you may not have been aware this is what you're looking at, but different distortions introduced by cameras that typically are of one of two forms. And we talk about most of the distortions being radial distortion. So the amount of distortion is proportional to how far away from the center you are, and it may be quadratically dependent or to the fourth power, dependence on the radius. But it usually gets worse as you get out away from the center of the image, and that's very typical of lenses. Two types that we typically encounter are what are known as barrel distortion. So the image gets warped from pure rectangular checkerboard into something that looks a little bit more like a barrel. And that's called a positive radial distortion. So that's one type of distortion. And the second is what's more called a pin cushion. It's almost like I've taken that checkerboard and pushed a pin in the middle, and it's cushioned in. That's called a negative radial distortion. And so you might be familiar with these. The positive radial distortion or barrel distortion is very typical for macro lenses. If you're doing something like very close up with a wide angle lens, they tend to have these barrel type distortions. And negative radial distortions tends to be more of a zoom effect that has just kind of this lowering of the top of the image, so that straight lines don't look quite straight. This image I've given here as an example isn't quite as pronounced, but you can kind of see how that what should be straight lines in this image start to bend down as you get out to the periphery. And so there's a classically used lens distortion model, and I don't want to get into the details of this, but the idea is basically there are a bunch of constants, K1 through K6, and P1 and P2, that you use to scale by the distance R away from the center of the image. And that's what these things like K1, K2, K3 are scaling by R squared, R to the fourth, R to the sixth. So allow you to correct for lens distortion for these different types of models, as well as there's these P1 and P2 are for kind of a skew effect that happens with cameras. And typical for most of the applications, certainly that I've worked on and a lot of work that's done, we ignore some of these parameters. So this, as written, is an 8-parameter model. Typically, we've used more often the 5-parameter model, which is common. Again, there's a reference there for this type of model and how to work with it. So now let's get into the actual work here of how do we estimate these intrinsic parameters. And if I want to know, again, the goal here being that I want to accurately estimate where something is in the world based on the image that I've gotten. So I find out where something like a ball is located in my image. How am I going to figure out where it is in the world? Where I need to know the focal length, I need to know the image center so that I can project back out into the world. And in addition, I want to know the extrinsic calibration. Again, that hopefully next time we do this, we'll talk about extrinsic parameters and how to calibrate a robot for that. In this case, I want to start with just talking about if I didn't want to run any code or do any additional work, how do I just get that from a camera? How can I just get an estimate of the intrinsic parameters that I refer to this as the ideal case, meaning that it's kind of the theoretically what this camera, what the calibration parameters intrinsically should look like for a camera. Well, for the ideal case, let's start with the easy one. The lens distortion parameters would all be 0, right? So if I go back to this picture, that checkerboard would look just like a checkerboard. And you'll see for very high-end cameras, they typically look that way. You get really good fidelity. We often refer to it as straight lines. You want them to be straight lines. So, does a straight line in a camera look like a straight line when you look at the image? If so, then you really don't have much distortion. Your lens distortion parameters are basically 0. So that's that's a model you could use that ignores any distortions that you get from lenses. Again, really cheap lenses tend to have more distortion. So you kind of play this game of cost versus having to deal and compensate with distortion. We've been really, I think, pretty happy with the lenses we've got, but there's still in our robot, but there's still some distortion there. So stuff that we want to correct for. Second point would be the principal point of the camera. So again, the way I described it at the beginning was the camera center. So it's the image center, if you will. So if I want to think about the ideal case, it would be that the principal point or the image center would be at the image center. It's just take the width and the height of the image, divide by 2, and that's your principal point. That's your CX and CY in these equations. And that's the ideal version. And typically, it's not going to be very far off from that. But the reality is that when manufacturers, and sometimes it's us that are assembling a camera, two things are going to happen. One is there's going to be some slop in where the actual sensor chip gets placed on the PCB, on the printed circuit board, as well as there's going to be slop in where the lens actually sits with respect to the digital sensor, the actual physical sensor hardware. And that shift is exactly what leads to the principal point not being right at the center of the image. And so typically cameras will have at least a few pixel error between the ideal center of the image and where the actual center of the image is. And then lastly, the focal length. Focal length can be calculated in a few different ways. The two main ones that I typically have used are either to, like I mentioned earlier, if you know the dimension of the pixels, the pixel might be 3.5 microns wide, micrometers wide, and I'm just trying to think. I think that's a reasonable value actually for a pixel. Just double check, and then your lens might have an effective focal length in millimeters that comes from your lens manufacturer, and so you can combine those two to get a focal length. And so I think it's just divide the focal length, the pixel size in meters, divided by the focal length in meters gives you the focal length in pixels. So that's one approach to do it. The way I've described here just I think is nice, just kind of visually thinking about what this is. Going back to this projective triangle, if I think about how this thing projects, if I draw a triangle that has the angle here as 1/2 the field of view in the vertical direction. So the actual field of view of the camera, which is a spec that you very often can get from cameras, is the vertical field of view. So if I take the whole of it, it would be both pointing up and down. But if I take half of it, it gives me this. And I want to ask, what's the focal length, y, in pixels? Well, if I've got this angle here, which is 1/2 FOV vertical, and I know the height of the image, and again, here I'm taking half the height, so it's h/2. This is the ideal height. Then just using simple trigonometry, I know that the focal length in the y direction for my image is 1/2 of h, so that's just h/2, divided by the tangent of this angle, 1/2 vertical field of view. So I can pretty easily, if I've got that information, the field of view and the image size, I can convert that into focal length in pixels. So it's a nice little trick for getting that value. And I need focal length in both X and Y to be able to do that. Okay, but let me switch gears again towards how are we estimating the intrinsic parameters? And the nice part is we're really leveraging a huge machinery that's already been built. Again, I mentioned OpenCV, but there's also custom targets that have been made to be able to do this type of intrinsic calibration. And they've gotten better and better over the years. When you first had to do this, you were usually using just a printed 8x8 checkerboard pattern on a sheet of paper, and holding that up and waving it around in front of the camera and having to do a lot of manual picking of points. But now these targets are printed on really nice metallic backed acrylic boards that can be very large and fill the field of view. And they have often identifiers on them so that you can really localize and figure out where things are. So I'm going to talk a little bit about that and just how we're using it. Again, this is just a sampling of some of the targets. You can still get typical checkerboard targets. The ones we're focusing on are Truco targets, and I'll give you a lot more information about that. So maybe to start, we get our targets, again, they're called Truco targets. We get them from a company called Calib.io, but you can print your own. There are a couple different places that make them. We've just been really happy with these. They're very high quality, both in the printing and also the just how solid they are and durable they are. They're called Truco, and it's kind of a cool name. Truco is a portmanteau of checkerboard and Aruco. So checkerboard, again, having that checkerboard pattern look to it. And Aruco, that I'll describe a little bit more, are kind of like QR codes. They're not exactly QR codes, but they're basically a N by N binary patterns of black and white pixels that give you a unique pattern that allows you to identify each of the individual target patterns. And you can get them in different sizes. They can be 4x4 or 5x5 or 6x6. We typically are using the 5x5 binary patterns. So it just gives you a nice scale for what we're looking at. Why is this so nice? So the checkerboard gives you really accurate corners. So you can do corner detection in a very fine location, even sub-pixel accuracy on the checkerboard pattern. But the Aruco codes also tell you exactly where each of the patterns are. And so if you happen to miss a corner or only get partial views of the board, you can still get a really good calibration. In contrast to, it used to be that you had to have just the entire board well known and all the corners identified. The other thing that's nice about this is, and I'll come back to this a couple times, is that we know the size of each of these checkerboard patterns and kind of where they're located. And so we can start to do things about exactly locating where this board is with respect to the camera, and vice versa, where the camera is with respect to the board. Okay, so yeah, let me keep going with that. And I just kind of alluded to this, but scale is one of those things that until you start playing with projective geometry, you don't really think about, but maybe intuitively it should be clear. Scale is really important, but also can be really a confounding factor when you're trying to calibrate cameras. And part of that issue is that this perspective projection is a type of projective geometry where you lose scale. And a simple way to think about that is just think about trying to determine, just from, say, using only one eye or one camera, the difference between a checkerboard pattern that's, say, 1 meter from the camera, that's this big, and say it's 1 meter wide, and trying to distinguish that from a checkerboard pattern that's 2 meters wide, that's also 2 meters from the camera. So twice as big but twice as far from the camera, all located just kind of on the same line from the camera. And you should be able to come to the conclusion pretty quickly is that you can't tell the difference between them. You can't figure out where that checkerboard is located. You can't say, is it 1 or 2 meters? Because in projective geometry, they look the same. So you can't tell the difference between objects that are scaled that are kind of proportionally far, distance-wise, far away, which is probably nothing new if anyone's thought about just kind of looking out and seeing something, thinking about, say, a toy car up close versus a big car far away. You just can't tell the scale unless you know something more about the scale of the object. And so this comes back to the point that I was trying to make with the Truco patterns that are really nice, is that you know how big they've been printed, and so you know something about the scale of the object. So not only can you see where it is and understand the projection, but because you know the scale, you can tell how far away it is. And so that scale becomes really critical when you're doing most important for extrinsic calibrations that, again, I'm not going into today, but I just want to really call that out because that becomes an important quantity later. And then just as we jump into this, again, I'm going to mostly refer to OpenCV and I'll refer to some of the functions that we use there. This is pretty well documented, but I do want to just kind of walk people through the process of doing this calibration using these tools. And that's really what it is. This is not anything we've invented from scratch. We've got our own way of doing it, but there's some really nice code and really nice documentation out there for doing this. So using the true code patterns to do intrinsic calibration, the process basically follows like this. First, you take pictures of these boards, and then you do the feature detection of these Aruco patterns, and you use those patterns and the checkerboard pattern itself to do corner localization. So you figure out very precisely where the corners are of your of each of your target boxes with the Aruco patterns. Then you figure out, okay, I know now in my image where those points are. And I know something about, again, the 3D nature of this board. I know that it's printed on a plane, and I know the size of each of the corners. So I'm going to match up the 2D image points that I had with my 3D points in space. And then I collect a bunch of data around that and use some tools. Again, OpenCV tools provides these, but it's basically figuring out what the parameters are that make sense of those matches, that match the 2D estimates that I get from extracting corners from my image with where I know in space that 3D pattern should be. And so that's how I'm going to get to my intrinsic calibration parameters, is basically by taking measurements, image measurements of the board and figuring out these corners, and then running it through some math that allows me to estimate the intrinsic calibration parameters. And then the last piece I'll mention, again, is not really part of the intrinsics, but it also does give me an estimate of where that board is with respect to the camera. Or if I want to think about putting a coordinate frame where the board is, I can invert that and say, okay, this camera is located, a meter away in some X, Y, and Z coordinate system, and with some rotation with respect to the board. And I get all that information out of this calibration routine. And a couple links here about tutorials for doing this. So how does this work? So again, I've shown you roughly what this looks like. Truco target pattern might look something like this. I'll just call out also, this image is of a fine grid that typically is used for higher resolution cameras than we would see in FRC. But it's the only one I had at home. So because of the quarantine, I have this board that sits around in my house, but we would typically use what's called a coarser grid. So it just has larger squares and fewer squares. But I didn't have one to take a picture of. So this is what we get. But again, mostly I call that out just to recommend if you're thinking about doing this type of calibration, I would start with a coarse grid. That's typically more suitable for FRC type cameras, the resolutions that we have. Within this, what we're going to do is take the whole grid. It's just a series of these Aruco patterns. Each one looks something like this. Again, I mentioned it's kind of a 5x5. You can see kind of the pixelation, but a 5x5 grid of black and white squares that each one has its own unique code. So the Aruco pattern detection will tell you which marker you're looking at for each of these cells. And then we can run it through OpenCV tool. This one's called Detect Markers, that will take this type of image, in fact, exactly this image, and detect all the markers. And so it goes through and detects the markers themselves, and then also can do the corner localization to figure out where each of these checkerboard corners are. So I'm both detecting where things are and also localizing down to all the corners that I need for doing this calibration. And you can see what's interesting is it hasn't detected every single one, and that's okay. We just need a bunch of sample points here to get good statistics on the camera. One of the things that we do, though, with this is make sure that we move the checkerboard around and collect lots of samples from different views, because you want to be collecting points not just at the center of the camera, but all around the periphery of the camera, especially to estimate radial distortions, right? They get worse as you get to the edge. So you want to make sure you've covered the full image with this Chirurco pattern. So capturing multiple images that are able to have features detected in all different regions of the image is really important. And we typically will do something around the order of, I think our current code is doing 50 samples of images. And we just wave this board around and move it around in space in front of the camera, collecting images so that we get good coverage of the whole lens. And this a little bit shows you an example of that, taking a few different views of this, both different orientations of the board, but also covering different parts of the lens. And then once you've done that, you can run it through another OpenCV function called Calibrate Camera Chirurco that essentially is going to do this. Take a bunch of these extracted feature points, you collect them all up and bundle them together, and with the knowledge, like I mentioned earlier, of the geometry of the board, how big each of the grids is of the board and how the points are relative. And it's going to do that matching. It's going to figure out what are the intrinsic parameters that best fit the points that I'm seeing from the camera with where the points should be in the real world, in the 3D world. And so here's an example of taking those pictures, and you can see we've covered different parts of the image just by taking multiple samples. And so what does this do? The goal here is to be able to get really good estimates of the camera. And like I said, our camera lens, we've been pretty happy with. It's a good camera lens. You can still see there's some distortion. So if I take an original image, you can see how it's kind of warped along here. So that, going back to this phrase, straight lines aren't straight in this image. And so what we're wanting to do is take the calibration that we get out of this and be able to map the points that we would extract in the image. Again, this might be where a goal is or a ball is, and undistort them so we get a real view of where they are that takes out the distortion that happens from the lens. So I'll toggle back and forth a little bit for that, and hopefully you all can see this. I don't know how it'll play out over Zoom, but hopefully you can see the difference between the distorted image that has some curvature to it and the undistorted image that has that corrected. And I also just wanted to zoom in and show you that. So this is just that same image zoomed in, and I've drawn a straight line to just kind of show you what the straight line should look like. And you can see the curvature that's introduced by the lens distortion. And then when after calibration, we go through and undistort the image, you can see that straight edge, which is the top of the Chirurco board, now looks straight in the undistorted image. So we've corrected for those distortions. And that's kind of at the heart of what we're trying to do with the distortion part, especially of the calibration. Again, you can decide for yourself if that type of distortion is acceptable or not. It's not terrible. We've got a pretty good lens, and that's a good way to judge lenses, is to figure out how much distortion they're going to introduce. It has a lot to do about the quality of the lens. And maybe this amount of distortion is fine. You still have to decide if how accurate you need to know the image center and the focal length. Those are the other two parameters, sets of parameters. And then the output of this type of function is usually represented in a matrix form, but it really just represents the two focal lengths and the two principal points of the camera in this matrix. And what I got out of just doing this calibration on that image that I just showed, or the sets of images that I was showing, were focal lengths that here, the X and Y focal length are pretty close to each other, 390 pixels, which is suggestive of the fact that that our pixels are supposed to be square for the imager we're using. And the camera center at 345 roughly and 234. And let's just compare that to the ideal, right? So if I had gone through and I took the field of view for the camera and walked through the ideal case that I showed you earlier of how I would get to the focal length, and do the same thing for the image center, the principal point, just by taking the center of the image. Let's compare that with what the calibration gave us. And you can see that the focal length is actually quite different. So the ideal focal length from our camera field of view was 457 pixels versus the 390 that we measured during calibration. So it's pretty significant difference. And the camera center, the principal point, is decently off. So the center, which for our image, which is 640 by 480, the camera center should be at 320 and 240. But doing the calibration, we find that the image center is actually at around 346. So about 26 pixels off from where the center should be in the horizontal direction, the X direction. And then 234 versus 240, so about 6 pixels off in the vertical direction. So that could be pretty substantial in terms of where your center point is for your camera. And then distortion coefficients, instead of being 0, we have a set of distortion coefficients. It's kind of hard to interpret these exactly. What you see those is in that unwarping that I showed earlier. And then the idea is that these are used to calculate, again, where things are in the world when you run them through, when you try and project back out from something that you see in the image to where it is in the real world. And then that's actually it. So that's pretty much all that there is to the intrinsic calibration. I do want to just mention a couple other things very, very quickly. One is what's kind of cool here is that because we have this metric information about the target, and we're doing this pose estimation, this estimation of where the points are of the target, we can actually calculate the pose, the position and orientation of the camera relative to the target or vice versa. And that comes directly out of some of the functionality. There's this function called estimate pose of the Truco board. And then the function I've used in here is draw axis. So what I've done is called that function draw axis on the pose that comes out of that estimate. Again, the idea is we're taking a bunch of corners that we find in the image. We know how far apart they should be in the real world, and then we can figure out where the camera is relative to the Truco board. And in this case, the draw axis basically is saying, pretend that there's the origin of the Truco board is in the lower left corner with X and Y axes and the Z axis pointing out towards me. What I'm doing is saying, I know then where the camera is relative to that, and I can draw the axes virtually on this board because I've just computed where that board is relative. And so I could track the board as it moves around. I can use that if I wanted to attach the board to some location and know where that location, where the camera is relative to that location, I can use these types of routines. So, as an example, if I wanted to know how far a goal was from the camera, if I posted up this Truco board, I could then estimate very accurately where the camera was relative to the target, to the goal. And yeah, so maybe I jumped the gun here a little bit. So some of the cool things you can do is figure out where things are on the field using this type of information. So kind of figure out where a target is with respect to the camera and the robot. Other parts that are really cool is if you've got multiple cameras, you can start to share points in the world, and so you might see it only with one camera at a time, but you can start to share information and track that information across the cameras by having these pose estimates of where things are in the world, and also just track where the robot is with respect to the world. Especially if I'm tying it in with an IMU sensor to give me inertial measurements. Then I can track both where use the IMU motion plus estimates from where the camera thinks it is and tie those together. And that's something we've been working on, is fusing that data to give you really good estimates of the robot as it moves through the world with respect to some world reference frame. Okay, and I'm going to wrap up there. Hopefully, take a look at time. Yeah, so we made it in time, which is good.
All right. Thank you, Jim.
Yeah.
Awesome presentation.
Thank you.
So I have a list of questions here for you.
Okay, great.
How do you tackle the issue of lighting when it comes to camera usage? So in an FRC environment, there's normally a lot of harsh white light, and there's not always conductive to cameras.
Yes.
So how would you tackle that?
Yeah, I think we're still working on that. It's always a challenge. I think there's a number of things that we do to address it. One is getting high dynamic range cameras. So you want to have a camera that works they call it dynamic range, but across as much lighting variation as possible. So very bright lights down to very dark shadows. There's only so far you can push that, but there's a number of things you can do. And modern cameras these days also have what are called HDR modes, high dynamic range modes, that sometimes will even take very quick bursts of pictures and fuse them together and take a burst of picture with a long exposure and a picture with a very short exposure that gives you even a higher range of on the image. The second thing we do is, so within that, you can also do adjustable adaptive gains. So change your exposure time, change your gains on the camera based on what you're seeing. So depending on how much light there is. And then the last piece is using routines that are robust to illumination changes. One of the things we've been focused on is using what are called SIFT features. They're called scale invariant feature transforms. And they're generally very robust to lighting changes overall, right? So if the lighting changes or the color changes on something, these features typically are very robust because they focus on things like corners that don't require getting exactly the right light and contrast between things, but are just, like I said, a little bit more robust. Having said all that, so there's a few ways that we approach the problem. It's never an easy problem. So if someone shines a flashlight in your face, it's really hard to see until you adapted and adjusted. And it's the same thing with a robot. If you stare, suddenly you're facing a bright spotlight, then that can cause problems. I think the goal is to just be as robust as possible in most of the situations. And maybe one more thing, it's a great question. One more thing is also what we've been focusing on is having multiple cameras so that you'd be looking at different parts of the field and potentially getting information from different locations, different headings, so that if one camera, let's say, is blinded by a spotlight or something, you can still get information from other views. Hopefully they're not all blinded at the same time.
Great answer. All right. So you were talking about the calibration procedure for your cameras. Do you have to use this procedure to get good results when you're using cameras?
I'd say no. I think it really does come down to how accurate do you want the system to be, and how good are the cameras that you've got, right? If I buy a $1,000 Sony SLR, that's a really high quality camera. The lens is really good. They've corrected for a lot of the distortions. It's going to be really well calibrated, and I probably don't need any of this. But most of us aren't putting those types of cameras on robots, right? So the reality is that you're going to typically have more lens distortion. And I think it comes down to just figuring out how much distortion is tolerable, right? You're going to typically, especially for intrinsics, I think you can get away with a lot there because the distortions can be smaller. You might be missing out in it's likely going to be causing errors that are at least centimeters, if not tens of centimeters, in things that are far away, but it's probably not on the order of meters. And so my guess is that you can get away with it. I think we've been using it as just part of an overall calibration procedure. I think where you get stuck is more the part of calibration I didn't talk about, which is the extrinsic calibration side. And with that one, the biggest issue there is around rotation. If you don't get the rotation right on the camera, things that are even just a few meters away and a degree or two away, you can be off by a meter very, very quickly in your estimate of where things are in the world.
Yep. All right. So obviously sending images over wireless uses a lot of bandwidth. So doing image processing on a laptop is not always possible in an FRC match.
Yep.
While the RoboRio is a powerful tool, it also has a lot of limitations when it comes to things like processing power. Yep. So is there a particular co-processor that you would suggest for processing vision data, such as a Raspberry Pi or an Arduino?
Yep. Yeah, I think there are lots of good choices there. We are using the Raspberry Pi, Pi 4, and have found that to have enough horsepower for what we want. Just to be upfront about it, it is a lot of computing power, and we're using one Pi for every camera. So it's a dedicated Raspberry Pi per camera to do these computations. But then because of that, we can do them all on board. So, there's no, you don't have to be sending anything off board to get the computation done. It can be all done all on the robot. And the calculations are expensive, but a lot of them been optimized pretty well to make them so that you can do them on board something like a Pi. I think everybody has probably their preference for what they want to use. A good ARM core based system is going to give you a lot of computation. I think what's going to be really interesting is there are a bunch of dedicated processors for running things. Actually, this is moving a little bit more even into like machine learning and deep learning, but doing really hardcore image processing on relatively cheap and low power components that are coming out. So it'll be interesting to see where that goes. But I would typically recommend, let's start with, just a nice off the shelf compute platform like the Raspberry Pi.
All right. Are there any limitations to OpenCV that people starting out should know before going in?
That's a really good question. So, I'll call it a few things that jump to mind, and maybe I'll think about some others as I go. One thing just to be aware of, OpenCV is a big library. So there's a lot of stuff there. It's bulky. It brings in a lot of dependencies. And so just be aware of that going in, that you need to make sure that you're okay with that, that it doesn't mess up with anything else in terms of code deployment or anything else that you're working with. You can carve out the libraries that you want to use, and you don't have to bring everything in, but it is a very big set of libraries. With that, it's also, I think, there's a learning curve to it. It's a very powerful set of tools, and with that type of kind of power, there comes complexity in terms of the interfaces that are available and being able to handle some of the data structures that are involved with it. So it's just always a caveat that there is a learning curve there. There's some great books on it. I'm trying to remember the name of the book. Anyway, I can't remember off the top of my head, but there's some really good books around OpenCV that I could put a recommendation out for if people are interested. I think in general, if you're looking to get started with computer vision, it's something that really allows you to move quickly and get started fast. Once you get over that initial learning curve of just how to import images and manipulate images, you can start doing things that are very powerful, advanced, state-of-the-art image processing algorithms with very little code and very little overhead. And a lot of it's been nicely optimized. I also would give a shout out, if you're just getting started, they've got really good Python libraries for OpenCV that just make it that much easier to get started.
All right, so what are some of the applications for Aruco points in the real world? Or is the usage of a 5x5 matrix with binary coloring limiting? Or could this be expanded to use multiple colors? What are some of the applications?
Yeah, that's interesting. It's a good point. I think I've a little bit got blinders on. I think it was very much a calibration and kind of either referencing, or we call it ground truthing, where you're kind of trying to find, here's an actual point in the world. But there's no reason you couldn't use it for other types of markers. In fact, these types of codes have been used a lot. We worked in my last company, we worked with the Sony Aibo robot, which is a little dog robot that we were building the vision system with it. But one of the things Sony did was build a charging station that had essentially like a binary type code of black and white markers on it, and used it for localization. So it used it so that this little dog robot could wander around and play, but when the battery started running low, it could look around and from across the room find the station and wander back to it, know how to get back to it, and know where it was oriented with respect to it. So there's those types of applications. I think there are different types of Chiruko or Aruko patterns. There's also kind of a diamond cluster pattern that allows you to have a bunch of markers that you could throw out and put in different places if you wanted to not just have a single board, but have individual markers that you marked up, say, a room, if you're trying to run experiments there and have something that you can see. We've even thrown out the idea to FRC to say, hey, what if you put these Aruco diamonds out around the field, and then people could localize off of that and be able to use that rather than the reflective tape, as an example. I'll have to keep thinking about that. It's a great question. I think any place where you want a good marker that's easy to process and get processed and localized out of the image, that's a great opportunity to use these Aruco patterns.
All right. Well, that's us. So thank you for presenting with us today.
Yeah, thank you. It's been great.
Right. Okay. Our next presenters that we have are Apurva and Mohammed from FRC Team 1678, and they're going to present on auto development. So how are you guys? How are you going, guys?
Hi, we're pretty good. How are you?
Yeah, going good. All right. Do we have some slides to present?
Yes.
Yes.
You want to go ahead and share those?
Yeah,
Yes.
I'll do that right.
All right. So once those have loaded, whenever you're ready, you guys can start.
Awesome. Thank you so much. Hi, everyone. Thank you for coming. Today we'll be presenting on auto development on Team 1678, the citrus circuits. My name is Mohammed Elmashad. I am the software robot lead on the Citrus Circuits robotics team. This is my 5th year of FRC with 1678, and I was the citrus service programmer for the 2020 season.
Hello, everybody. My name is Apurv Mishra. I am a 4-year member of 1678, and I was also a citrus service programmer in 2020. This year, I was leading new programmer training on the team. So a quick outline before we dive into the rest of the presentation. Today, we'll be talking about auto development on 1678. So we'll start off with what is an autonomous program, right? What constitutes a good, robust auto? Then we'll dive into how 1678 gets started with auto development, how we do our plan development and formulating what autos we want to actually write. Then we'll go into the execution of the plan that we have created, and some considerations that our team goes through before sharing some resources with you guys.
Awesome. So to kick us off, I'll be going over what is an autonomous program. So in FRC, there's a 15-second period, typically the first 15 seconds of a match, where the robot moves by itself using only sensor feedback. So no operator, no driver controlling it. And the only control that we use is any input from a sensor, so any feedback device. This includes any type of encoder, any proximity sensor, vision, etc. So the robot uses what it knows based off the sensor information it gets, and then it moves based on those that feedback. In addition to the first 15 seconds, there's also automation in FRC. So during the teleop period, many teams can opt in to automate tasks. And we'll go over later on why it's good to automate tasks. And those two aspects of FRC, autos are really important. So there are 4 things that make a good auto. So robustness, time, efficiency, and score. So the first category, robustness, is how well the robot auto can adjust based on any external factors. So for example, if it got pushed over an inch, can it readjust back on its path? Does it wait a second for the balls to settle if you have an indexer? Does it use sensor feedback and utilize it to the max to make sure that you get the most out of it? Time. So time is the speed at that the auto runs. So you have 15 seconds to run the auto. If the auto goes over 15 seconds, it will not run in that period. And then there's efficiency, which is what you do in that time. So, for example, if you do a path that is 5 meters compared to a path that's 2 meters, and you get from point A to point B, you want to take the shorter path more likely than not, unless there's a constitution that something that like is there that like a reason you would take the longer path. So efficiency is a really important part of what makes a good auto. And then obviously score. So you want an auto that scores points. There's different ways to score points in auto. We'll go over that when we review the strategy of creating an auto. So there are 3 steps when creating an auto. There is the formulation of the plan, the execution of the plan, and then repetition and reliability. So each of those 3 aspects are actually really important when creating these autos. So formulation starts off in our strategy subteam. So we have a strategy subteam that creates the initial drafts for the autos. These autos are really vague. They might not necessarily have the drive paths unless the drive path is important. And it's really vague because once it goes from strategy to the software robot subteam, software robot is able to adjust the paths to fit in like the ways they see fit best. So for example, if the path seems too sharp of a turn, it's not going to work because as the programmers know that they can't do that type of turn. After the plan is formulated and you know what your auto is going to do, I start executing the auto. This is a really big part of the auto. So the execution of the plan takes time because you are testing the auto. This is code that gets written, and the auto gets tested a lot. So if you're executing your auto, you usually do a lot of testing because it's code, and when you write that code, it's when you write the code, it's not gonna work always. So executing the auto, making it work is the execution aspect of it. And the repetition and reliability is when you test out, like make sure the auto works consistently. So if the auto works 5 times, test it 10 times. Works 10 times, test it 15 times. So the more you repeat an auto, the more reliable you see. So in 2020, we had a rendezvous bar. Initially, we had our first 10-bell auto draft actually went over the bar, and we got to the formulation and the execution. But when we got to the repetition and reliability, we figured out that the bar made it not reliable at all, and we had to go back to the formulation and start over with our 10-ball auto. So those are the 3 steps to the auto development process on 1678.
All right, so now we'll be jumping into, the actual plan development for creating an auto and how specifically on 1678 we do this. So, so something that is really important to do when you start developing your auto, right, is first make sure that you thoroughly understand the game, right? Once you understand the game, right, for the year, it's really easy to be able to understand, where are places that you can take advantage of the game, what are significant aspects of the game for that year. And, that helps tell you not only, what are the most effective things that you can do in your auto, right, to, earn the maximum number of points, for example, but how you can, utilize your auto to do really important things for the rest of the match, right? Because in the end, your autonomous routine not only, earns points on its own, but sets up your team for the rest of the match in, an actual competition. So the first part to doing this, right, to understanding what the game is, right, and especially, what aspects of the game are really important towards developing an auto are developing these point objectives, right? Point objectives are, simply, what are important things to look out for when you're writing an auto, right? What do you want to actually accomplish in your autonomous routine, both again for actually scoring points and setting up the rest of the match, right? So, simple point objectives, for example, in 2020 were things like, making sure that you cross the initiation line. The fact that the point value was doubled for power cells in any goal that you scored them in, right? The fact, again, that there's a 15-second time limit on the autonomous, And really important that we were able to start with the possession of 3 power cells, right? So if you're able to develop these point objectives, you can, you can start to look towards, what are things that you want to accomplish in your auto from the get-go, right? And then start understanding, these are the list of tasks we have. How can we now take these tasks and prioritize the ones that we know we want to accomplish in our autonomous routine to make it, as Mohammed had described in the end, robust, time efficient, task efficient, and high point scoring. So plan development on 1678 really begins with our strategy subteam. Our strategy subteam on 1678 goes through an entire process of creating an auto draft, right, where we actually come up with, different, possible paths that our autonomous routine could take as a team and discuss it together as a large group, right? I would say that this is, an extremely important aspect of developing our auto as a whole, right? Because in the end, your auto and execution can be really great, but it depends on how quickly you can get a head start into understanding, what makes your auto more effective for the entire season as a whole, right? You want to be able to have such a discussion, right? A really healthy discussion from the get-go instead of realizing 3 weeks into competition season that, oh, this is something that we can do with our autonomous routine. Because, the faster you're able to develop these plans, the faster you're able to get to, the actual execution aspect and make sure that your auto is completely prepped for competition through testing and, reliability. So the actual discussion that our subteam does, right, the strategy subteam does, is that it encourages all of the team's members, right, and really anybody who's not in the subteam too that might have an idea to, join this discussion, right, and come up with their own autonomous paths that they can share as a large group. And together, you're able to share these, and we come up with an auto draft, right? And this auto draft helps, this auto draft is important because it says, okay, these are the different paths that people have come up with. So for example, this was one thing, right, that we had in our auto draft. Somebody had the idea of going to the trench and then going back from the rendezvous bar to ending at this point right here to score into the goal. And so, that way our strategy subteam comes up with, a draft of all these paths that we might take. And, as we go further, as we continue discussion, we hone down on the paths that we really want to have. So a really important part of the strategy discussion that I think gives you a really, a really strong advantage when going into competition is coming up with multiple paths, right? And coming up with paths that have high flexibility and are still effective to some important level, right? This variance is really important because it allows you to take care of multiple situations, right? For example, last year, right, we wanted to do a 10-ball auto, right, as Mohammed mentioned, but at the same time, we wanted to make sure that we had other autonomous routines that worked, that, weren't as, ambitious in case we wanted to go with something that was extremely steadfast and didn't want to take up the entire field. So we actually came up with 4 smaller autos that were 8-ball autos. And this was a, near side, right side auto, far right side auto, near left side auto, and far left side auto, right? And we'll go through a case study later on in the presentation that goes through, what actually was this 8-ball autonomous routine. But by having these multiple situations, right, you allow yourself to be flexible in the sense that if something goes wrong during competition, you still have more autonomous routines that can be effective and still make sure you have a successful autonomous period during the match in which you're still able to score something, right? And at the same time, it allows you to have flexibility for your alliance members because it's really important to think about the fact that your alliance members are also going to have their own autos, and you have to come up with a way to be flexible for them too, so that your autos don't collide with theirs, for example, or there isn't any conflict over there. And yeah. So a really good example of considerations that the strategy subteam makes in our early discussions for autonomous is quals versus elims in 2018. every year, actually, 1678 wants to make sure that we understand what are the differences between the objectives that we would like to have in our qualification matches versus what we think is really important to get done in elimination, because there are important factors that separate the autonomous routines that usually are within these two separate, aspects of the competition. So, just a quick review for anybody who may need to rekindle their memory a little bit. 2018 Power Up had a field where we had a scale in the center and two switches off to the side. Each of these was able to, tip over to one side or the other, and one side was designated to one alliance, the other was designated to the other alliance, and it was time-based scoring. So, you would obtain points, you would score points for however long the scale or the switch was tipped to your side of the field. And so, keeping this in mind, in 2018, we actually had we had a lot of different considerations that we wanted to make in our autos. One of the most important things was that in qualifications, 1678 really wants to make sure that we focus on the ranking points, right? Because in the end, you want to win the match, but you also have to make sure that you're optimizing the number of ranking points you can get in a match too. So, in 2018, this was making sure that we cross that auto line, right? And making ourselves well set to win the match, right? But also be self-reliant, right? Something to think about in qualification matches is that you don't actually know who you're going to be partnered with, right? A lot of teams have a lot of different single objectives that they're able to accomplish within an autonomous routine, right? And so you can't really, rely on another team to do exactly one task while you do another, because while one partner of yours might be able to do one task, another partner in a later match might be able to do the same one as you. And that means that you might miss out on an opportunity to score points when you should, right? So a really good example of this was the fact that in qualifications, we wanted to be self-reliant for controlling the switch and the skill, because we wanted to make sure that regardless of whether an alliance member of ours was able to score on the switcher skill, we at least got 1 or 2 cubes on the switcher skill ourselves. So our autonomous was focused on getting at least 1 cube into the switch and then 2 cubes into the skill for that year. For eliminations, however, we don't actually need to worry about being self-reliant in this way, because we know our partner's capabilities. And so in elims, we really hope to just focus on maximum scoring, and by collaborating with our alliance members, seeing what they can accomplish in their autos and how we can work with them to make our auto as effective as possible, right? And so in elims, we actually had an auto where we attempted to get 3 cubes all into the skill, because we didn't need to worry about the switch. We expected our first or second alliance member to be able to put a cube in the switch themselves and ensure that we have control over it for the beginning of the match. And that way we could focus on obtaining the scale, which would, obviously allow for the match to be tipped into our favor. So this is, a really great example in my mind of, distinctions that could be made between different, types of matches that you might face throughout the competition, right? And you have to be able to make these considerations the moment you get started with auto development, to be able to ensure that you provide yourself enough time to actually develop these autos going forward. So the next thing we'd like to share is actually an auto case study from 2020. As I mentioned earlier, 1678 went with an 8-ball auto at our LA North Regional, and we used this actually quite a lot because we found that it was effective, it didn't take up the whole field, and we could collaborate with our alliance members well with it. So I will play a short clip of the autonomous routine first, and then go into some discussion about it. Here's what it was like. So our robot is right here. You can see that we picked up some, we intaked some power cells here and we scored them, and now we're intaking 3 more for a total of 8 that we're scoring from the same location to get into the high goal. before we move on to our teleoperated period. So I'd like to just, look at the starting of the actual match again, so we can take a look into, what the field was like last year and how that supported our considerations. So the first thing was that we wanted to decide, right, in the match whether we wanted to use an 8-ball auto versus a 10-ball auto. For 1678, the thing with the 10-ball auto was that it actually took more of the field, right? For our 8-ball, we knew that we could intake 2 power cells from here, score them, and then just intake 3 more from the rendezvous bar right here. If we wanted to obtain more power cells, however, we need to go to the other side of the field and risk making contact with some of our other alliance members and, for example, cause conflicts within the auto. So our 8-ball auto in this sense was a lot more reliable. The next thing that we wanted to decide was whether we wanted to do a far auto versus a near auto. What I mean by far versus near is that we thought for our auto that we would either score close to the goal. So I'll, if I play this again, you guys can see that our scoring location is right, is right there on the field, right? And so that's right next to the actual goal. But another location from which we scored was just behind the rendezvous bar. So we had this gap of space in between. And the reason we had this space in between was because we knew that an alliance member could be there at that time. And we didn't want to have any conflicts in the movement with them. So by having this space in between, right, we were able to decide that, okay, we wanted to either do a near auto or do a far auto. And that way we were able to be flexible with our alliance members at the regional, right? Then the last thing we wanted to decide was simply, whether we wanted to do the auto on the right side versus the left side, right? In the end, 1678 actually came up with an auto for both sides because we wanted to make sure that if our alliance member had an auto that they could only do on the right side of the map, for example, we could, help their needs and do an auto from the left side. And so I think the case study is really important because it shows all the considerations that our team had to make to get to this 8-ball auto right here, right? We had to choose where we wanted to intake the balls from, right? Where we wanted to actually score from, how we would be flexible with our alliance members, etc. All right, so now we can dive into creating our auto. So when creating an autonomous routine, right, it's really important to be able to identify common point locations that you're going to use throughout your autos and start building them, right? So you'll find that, when creating an auto, there's actually a lot of different locations on the field that are going to be similar, right? If you're creating similar, but somehow different autos, right? So for example, again, with our 8-ball autos, whether we did the far or near auto, our first intake position and our rendezvous bar intake positions were still the exact same, right? So those were common point locations that we were able to use. And by making sure that these point locations are known to be common, we can, reuse them in different places. And if we want to, make any tweaks or make any changes to the point locations that we find work best for our trajectories, we can change that in one location only. So we don't have to worry about changing that entire location in multiple areas of the auto. So next, we actually have trajectories and actions for our autonomous routine. So on 1678, we organize our autos by first creating these trajectories, which will be the paths for our autos, right? By plotting out these different points, seeing which ones work well for our paths, and then combining them with actions, which are basically the commands for what our robot should do in an autonomous and in what order they should be done, right? So your actions are, drive to the intake position, score, into the goal, intake, for example, right? And by organizing your entire autonomous into the paths that you want to follow, and then the actions that actually go through with these paths and your intaking, etc., it's a really easy framework that you can apply to all the autos that you create to make sure that they're robust, that they're easily testable, and that this framework can be used when you create multiple flexible versions. A really important thing in our autonomous coding is making sure that your code is very organized, right? This code needs to be organized for multiple reasons. One, it's really helpful for testing as a whole, right? Because you're able to identify where the problem is in the auto, right? Isolate perhaps an aspect of the auto from which you can do further work on it, and simply easy readability, right? So you can understand what is going on in your auto and have easier time with testing and making sure that your auto is safe and you know exactly what it's doing in the moment. So 1678 usually groups our positions by the auto that we have. So here in the example to the left, you can see that we've actually labeled our positions as REB and LEB. REB stood for right 8 pole, LEB stood for left 8 pole. And we used this kind of code organization to make sure that it was clear which positions were being used for which autos. And then we split our autos into different test files, right? So we were sure of which auto we were running at a specific moment in time, and we knew exactly what was going on with our robot. Again, for testing and also safety purposes, so you know exactly where on the field your robot is moving at a given point in time for the safety of any team members that might be around, right? And then the last thing, again, when organizing code as in general, right, is make sure that you use your code styling guidelines. Again, for autos, your positions are going to be constants, right? So 1678 with K right here before our variable names. And by having this code organization, it really makes the entire process of auto execution a lot easier because it's easy to understand where you are in your auto, where you're going, and how you can do that. The last thing that's really important to do, or at least that's really helpful in assisting with the formulation of your auto is using path tracking, right? So something that's really important to implement in your autonomous routine is robot odometry. Odometry is essentially, using the sensor values on your robot to understand its position and where it's going. This can be really helpful and can be utilized really well to understand how exactly you want your auto to be run. It helps you understand, how fast your auto is running, what path it's taking, and it makes your trajectories really easy, right? Because it makes them accurate. A really important thing that you can do while using robot odometry is using some sort of visualizer. 1678 definitely uses a visualizer when we're creating a framework for our different autos because we don't want to go into testing blind, right? We don't want to test out random values. By using a visualizer, we're able to plot points on a field according to some coordinate system. And using this visualizer, understand, what is a likely path that our robot could take, and then use those positions in our code. It's important to note that, the visualizer might not always be accurate, but it's a really good start for understanding what you can do with your auto moving forward. This right here is an example of the robot odometry that we had on 1678. So this actually right here is a plot of real live data that gave the location of our robot at different points during the autonomous routine. And this type of tool is really important because it shows what exactly our robot did in real time, right? It shows that we started right here, we intaked, and it shows what trajectory we actually took, how we scored, how we turned, etc. This was a path that we actually took for our 8 ball to try to intake 5 after we shot 5 already into the goal, right? And by having this sort of odometry, and being able to plot it like this, not only can you understand, what actually happened with your robot, but you can compare it to your predicted path, right, from your visualizer, see what you have down in your code. And it makes the testing a lot easier because it helps you isolate the part of the auto that is not working and functioning exactly how you want it to, and what part of the auto you can change, right? What is causing variance, what is making it perhaps less reliable, etc. So having this sort of path tracking, having odometry that you utilize on your robot is a really essential step to executing your auto formation and later testing.
So an important part when you're writing your auto is to keep in mind that when you're doing it, you want to do everything step by step. So when you're testing, you want to do it atomically. And what that means is any little change you make, you test in smaller steps. So for example, if we're looking at an auto, you have a first intake, a shoot, a second intake, a third intake, and then another shoot. You have to test each of those trajectories and actions independently. So first you verify the first intake works. Once that works, you move on to the second step. Once you know the first intake and the shooting works, you move on to the third step, which is the second intake. Once you know that works, you move on and so on. So when you do that, it helps you make sure that anything you're adding on top of works. So for example, if the first step worked like maybe once or twice and you're like, oh yeah, let's go, it works. And then you move on. And then later on you figure out that, oh yeah, the first step like wasn't how we want it to work out. Then that means your entire auto might need to get rewritten because that's how autos work. You have points on trajectory. If those get messed up, even if you have some sort of readjustment, it won't work out as well as you intended it to. So atomic testing is really important. In addition to that, a benefit you get out of it is that you're able to identify problem areas like really well, and you're able to isolate where possible issues can be. For example, at some point in the season, we had an issue where one of our control modes, it stayed in velocity control mode instead of position control mode, and that messed up the second half of our auto. And then we were able to isolate it because of atomic testing. We figured out that that happened after a certain event in our auto, and then based on that information, we were able to debug it and go forward. In addition to that, upon over the viewer and the spline viewer, usually that's not going to be accurate to like in real life, mainly because it's like a simulation, right? Like a simulation can't simulate every little variable. On top of that, for this year, the rendezvous bar really messed up the viewer. So that was an issue that we had with the viewer and using it, and it was really hard to tune the autos when we went over the bar. So testing step by step is something really important because you get a lot of benefits from it, and it also helps you identify a lot of problems. In addition to that, you want to account for external variables. So any physical factor that could affect the auto path, you want to account for it. So for example, if you have a swerve drive, I'm pretty sure Madtown Robotics did this. They had a constant, a factor for carpet scrub, and then that would be used based on the angle of their swerve modules, and that helped them make their autos more robust. They were accounting for friction. A lot of teams don't really do this; they just rely on sole PID, but that was a really good example of a team that used other physical factors to improve upon their autos. In addition to that, other alliance members, you have the possibility of getting bumped. So, for example, if you move 5 meters and then you get bumped an extra half a meter by accident, and your robot knows where it has to go, the robot can readjust based on its trajectory and based off the odometry. So, on our team, we have our paths are constantly updating. So, for example, if we get thrown off the path for any reason, for some reason we time out for like half a second, and the robot drifts a little bit, and it's able to keep reading the encoder data, we can readjust our trajectory to get back on track and try to continue the auto. Although this might not always work, it's better than continuing the auto with an offset that the robot doesn't know about. So accounting for external variables really helps when you're creating a robust, consistent auto. In addition to that, you want to have various cases, various paths for different situations. The case study that Poor went over at LA North was a really good example of the use of having multiple autos and why it helped us. It helped us be have good synergy with the gray bots at the time. So at the start of the presentation, I mentioned that autos aren't just the first 15 seconds. It can also be applied during teleop. So task automation is really important when you are trying to have a robot that's consistent and reliable and scores points efficiently and is real. Yeah. So your task efficiency basically means that you're utilizing the most out of your system. For example, if you have a motor, you are pushing it to its max. You're not using 20% of its power. You're using maybe 90% of its power to make sure that you're fast. You're not wasting any time. So that has to do with task efficiency. In addition to that, mechanism reliability adds consistency. So if you have a subsystem, let's say an elevator, you want that to be reliable. So if you have 3 different heights, back in 2019, there was a rocket with 3 different heights. If you had a human trying to go to those heights manually, it would not work. Mainly because those heights are very specific. And if you go over, I think like 6 inches, the hatch panel would not stick. So if you make it reliable by relying on encoder data to control the elevator, you get an automated elevator that works way better than one that's controlled just by going up and down with a controller. In addition to that, it also adds ease to the operator. Many of the tasks we automate on sensor circuits helps the operator do things that are either inhumanly possible or things that just make it go faster or easier. For example, our triple climb in 2019, most of that's automated. So the first half, the winching up, that's manual because we winch different heights depending on who we're picking up. And then after that, all the operator had to do that year was press a button. The elevator would go up. Once it reached the very top, it would start going forward, and then it would stop once the operator pressed the same button again. So climbing was really easy for the operator in 2019 because all the operator had to do, he would winch it, he would press a button, wait until it got to the end, and then he would just drop the robot because you want to not touch the ground in 2019. Another example of operator ease was in 2019, we had the robot actually self-align with the rocket and self-align with the intake, on the side. That really helped us be consistent with picking up our hatches. It also helped us go really fast because we use a PID loop that changed its velocity based off the distance between it and the goal. And we'd always use, again, earlier I said it's efficient because we're using as much of the motor as we can. So it would use the maximum output possible based on the distance between it and the goal. So if a human were doing this, they might not want to go full speed because they can't control it as well. But if the robot's controlling itself and it's reading the data from the encoders, reading how fast it's going, adjusting based off that, the robots will always be more efficient than its human counterpart. So PID was something I just mentioned. PID integration, PID stands for proportional, integral, and derivative. So when you are controlling a linear, anything linear, you're going to have an error. So you have your current position and then where you want to get to. And the difference between those is called your error. And then that's what PID is based on. So proportional is proportional to the error. So the farther the distance, the more output you're going to put on. Integral and derivative do the same thing. So you take the integral of the error and the derivative of the error. Derivative helps us slow down as you get closer. And yeah, so with PID, it adds efficiency and reliability. It also does what was mentioned previously in the automating tasks. It helps us stay consistent and get the most output out of out of our system. A really nice thing about PID now is that it's actually built into the CTRE and Rev controllers. So CTRE makes the Talons and the Victors. Rev makes the Sparks and Spark Maxes. That's actually built into the libraries. And if you set all the variables correctly, you can implement PID pretty easily. Just make sure you are setting all the variables properly, and your PID will be better than just using like voltage, for example. The thing with PID is you don't want to use it for everything. For example, an intake, there's no point of trying to add in velocity PID. You just want to give it 12 volts so it can run max power, or 9 volts, depending on what you want to do. So PID, try to only use it for linear systems. So like an elevator or a wrist or a drive path even. So being prepared. So being prepared when running an auto is really important because as you go into the season, issues come up or challenges come up that you want to like be ready for. So auto flexibility was mentioned a few times, but we'll mention it one more time. Try to be compatible with other teams. So our autos, we had 2 different versions for the left side and 2 different versions for the right side, a near auto and a far auto. And as the case study which showed, it really helped us at LA North because we were able to stay on, have good synergy with the Greybots. In addition to that, different matches need different autos. For example, our 10-bell auto was not used mainly because we had different priorities at the time. It also was not as consistent as we wanted it to be. But we had 4 other autos that we used. We had our left 8-ball near, our left 8-ball far, our right 8-ball near, and our right 8-ball far. And each of those were used in different matches based on our alliance partner. And it also saved us time because if you're doing this at a regional, you don't want to rewrite an auto from scratch. If you have it ready to go, you can make very little changes to it and have it work. So auto flexibility is really important. It provides synergy for you and your alliance member. And if you have different priorities, so if you want to score, if you want to get a ranking point, depending on what you want to do, you can take out different autos from like your toolkit and run them. So being ready for any anomalies. So basically, like when you're testing code in your lab, in your shop, a lot of the time the fields shift compared to your practice field that you have at your shop. So when we do this, we actually have a variable, a constant, a shift that we add on top of all of our XY points on our coordinate plane. And then this helps us get the auto working really fast as long as we figure out what the offset is. So for example, if we're in the first trajectory and we see that it's off like 3 inches, we'll add a 3-inch offset and then move on. And then this helps us like get our autos ready really fast at regionals because we are ready to add in that variable that shifts over the X and Y points. In addition to that, a vision offset. So our autos depend on vision. We use vision to reset our position sometimes. And if the target's wrong, like the distance reads a number that doesn't make sense, it could mess up your entire auto. And always remember that anything can go wrong. So always be ready to have a backup. Always make sure you're checking all your systems before you run any auto, and make sure that when you're running your system, you are double checking that anything that could go wrong, you're checking for. So for example, vision, you want to make sure that the distance is reading a proper number before you use that data. So if the number reads 1,000 inches, obviously that doesn't make any sense. Like you're not gonna be 1,000 inches away from the target. So don't use that number. So for example, you could be like, oh yeah, if the vision distance is greater than 500 inches, then don't use that number and move on, and don't use that number to reset your position. So always just be ready to make sure that anything in your code that can break won't break. It always goes for anything you write, obviously, but with auto specifically, you want to keep that in mind.
Yeah, and then before we wrap up here, a really important note is that a top priority in creating an auto, right? From formulation to development to through testing should be safety, right? You have to make sure, for example, that when you're testing, everyone is aware that your auto is running. Nobody is, going across the field at that exact moment. And you have to also, make sure of, a lot of other things too, right? Like you should make sure that your system works before all of your systems work before you run them, right? That you calibrate your robot, for example. I remember something last year that 2020, for our 2020 robot that we had to always make sure of that was that the turret on our robot wasn't actually over twisted because if it twisted too much and then twisted more during our auto testing, then it would disconnect the wires, right? Or it would break some wires. And then that would cause electrical problems, right? At the same time, if our turret or even our hood, right, that angled our shots, right, wasn't calibrated correctly, then when we were searching for the target during vision, then it would go out of control, right? And that is another safety concern, right? Because you want to make sure that your mechanism is fine, but anybody who might be in the field is also all right. And as a general rule of thumb, make sure that nobody is actually around the auto at all when you're testing it, and make sure that you know exactly what is happening in your autonomous as well, right? You need to make sure that by having good code organization, by doing strong testing, you know exactly what is going to occur in your auto, right? That if you're running a certain action, running a certain trajectory, you know where that trajectory is supposed to take the robot. By using, your visualization, for example, you know that you plotted reasonably correct points, right? Even if they're not entirely correct, to make sure that your robot isn't, for example, going to slam into a wall, right? Or something else nearby, right? So by being able to make these considerations, by making sure that everything is well before you start your testing, right? You can make sure that you're safe, that your autonomous routines are safe, right? Because in the end, you have to make sure that everybody around you is safe during the auto and nothing dangerous is occurring during your testing. So yeah. These are, 3 resources that we'd like to share with the entire audience. First, we have here our WPI-lib trajectory tutorial, right? This is just a tutorial that goes through writing trajectories, right? And forming trajectories for autonomous routines. In addition, you can look at 1678's code releases on our GitHub, and see how we managed to do our autonomous routines in past seasons. And lastly, you can look at a blog by Wesley AC that actually goes through, control, right, PID, as Mohammed mentioned, and other aspects of, coding that might relate to an autonomous routine to, if you want to get, a bit of an overview of that or are interested in it. Yeah, and that concludes our presentation. Thank you guys all for being here, for listening. If you guys have, right now we'll be glad to take some questions, but if you have questions later, then you can also just shoot us an email at software@citruscircuits.org. Yeah, thank you guys so much.
Thanks, guys. So I do have some questions for you. What language did you guys use for 2020?
So for 2020, 1678 actually coded in Java. For our robot, we found that, Java was really, it was an easy language to code, and we were able to do a lot effectively with it. In past years, we've actually used C++. I think we actually made the switch from C++ to Java in 2019. Before then, for 2018, 2017, etc., we used C++. But yeah, now we use Java, and yeah.
Right. Why did you guys make that switch?
We want to make our team more sustainable. C++ was really hard to train new members in. In addition, we didn't use Jetsons anymore, and with the addition of Limelights, the use for C++ and code running fast wasn't really as needed. So switching to Java just made more sense because we were able to get code that new members would understand better, it also made new members on our team understand the code better than they did if they're taught in C++. So yeah, I think the biggest reason is probably just sustainability of the team.
Makes sense. All right. What did you prioritize in your auto routines in 2020?
So yeah, so we went over this a bit in the presentation, right? But something that we definitely prioritized in our autonomous routines was making sure that we were able to be flexible with the rest of our alliance partners, right? Something about the 2020 game that we had to think about is that there are definitely, these two other robots that could very surely interfere with you, right? Because there are very similar, they're shared intaking locations, right? So flexibility was something that we definitely wanted to focus on when we were forming our different autos. And besides that, we had a keen interest in trying to do our 10 ball auto, right? So that was actually the first one that we were able to do. We realized later that we wanted to do some 8 ball autos because they would be more reliable and wouldn't take up the entire field the same way as the 10 ball auto did. But yeah.
So did you think that this 10 ball auto was achievable at the start of the season? Was this something that you always set out to do?
So yeah, we definitely aimed to do a 10 ball auto because we thought that if we had enough testing, it would be reliable, right? That we could get it done. Our main concern was, one, the amount of time that it would take, right? We spent a lot of time discussing the exact path that we would want to do our intaking in so that we utilized the entire 15 seconds and didn't go over. But I think our main problem was, the rendezvous bar, because we knew that the most effective way to intake the balls for the 10 ball auto would be to cross the rendezvous bar. And we weren't entirely sure at the beginning of the season how that would play into our development. So yeah.
All right, very cool. So how have your auto processors contributed to your team making it to Einstein for so many years?
So our autos give us a good head start at the start. Obviously, the points in previous games are usually doubled or have some sort of factor on them that lets us score more points in a short amount of time. In addition, usually some sort of auto ranking point. So in 2020, it was crossing the line. As long as every team did that, we would get a ranking point. And that would help us seed higher, which helped us, if we were alliance captain, seed higher and pick, have more priority in picking. In addition to that, as I mentioned earlier, the ranking points for the autos, we have a team called the Citrus Seals who actually go help teams make sure that they're ready for competition, make sure that they're ready for their autos. So we had like a treadmill that we put the robots on, to see if they would move off the line, and that helped us like secure that 1 RP. We also have the task automation. I feel like that helps us a lot because it takes off a lot of stress off the operator and driver, and it also helps us have a very reliable robot.
Awesome. So when you make your initial auto plans, as you go through the season, how much do these initial plans change?
So I would say these plans change quite a bit. Our first 10 ball draft definitely was very different than the one we published online. In addition, all our 8 ball autos got changed quite a bit. It really has to do with how your robot reacts to the spline you give it. If it, like, sometimes you might think that, oh yeah, like this spline works really well, and then you're like, oh, but this might be better, this might be faster, this might cause the robot to jerk less, or this path when we tested it actually caused the robot to jerk a lot. So yeah, it really changes a lot throughout the season. Like from like week 6 to week 8, we had very different goals and very different plans for our autos. So
Yeah, I would definitely say that, when you get started with creating an auto, a lot of it is ambition, right? And the objectives that you hope to achieve. And throughout the season, through testing and understanding of how reliable your auto trajectories are, you get more of the reality, right, of the situation that balances out your ambitions to ensure that you can get what you want to get done in the auto. But some of the setbacks that you will face that will, lead to your end auto. So yeah.
So it's a balance between the ambition of what you want to achieve versus the reality of what you can achieve.
Yeah, exactly that.
So thank you guys for joining us with your auto presentation. Do you guys have any final words before we start to wrap it up?
Thank you so much for joining us. I hope you enjoyed the presentation. As always, feel free to contact us at software@citruscircuits.org. We'll be more than happy to help you out. If you have any more questions, we'll also answer them. Just thank you for coming. Have a great rest of your event.
All right. Thanks, guys.
Thank you.
So thank
you.
you all for joining us for the past 3 hours. We'd actually like to thank our sponsors. So today's event wouldn't have been possible without all of our incredible sponsors. And we would like to thank Boeing, Google, and Macquarie University for their generous support. So just a reminder, if you haven't already had a chance, please check out the 24 Hours of STEM challenge at our website. So 24, that's the numbers 2 and 4, hoursofstem.org. The challenge is open to all ages and groups, and 4 lucky teams will have the chance to win a LEGO Mindstorms EV3 kit. So for the next shift, we will be handing over to FTC team 18003, who will be hosting the stream. Hi, guys.
Hello, how are we?
Good.
Awesome, awesome, awesome. Fantastic. Hello, so welcome back to 24 Hours of STEM. My name's Caleb from FTC Team 18003. That's the Paladins of St. Paul's, coming at you from Adelaide, South Australia. Thank you very much to FTC Team 3132 for the wonderful job of hosting 24 Hours of STEM. For the next 3 hours, we will be joining you, and we are very excited because we have 3 amazing guest speakers who are very excited to talk to you. So first off, we'd like to welcome Christina Rolfe from UC Davis to give us an introduction to musculoskeletal biomechanics. Hey, how you going?
Great. How are you?
Oh, I'm very good. It's great to have you here. Thank you for joining us.
Yeah, happy to. Excited.
Awesome. All right.
Cool.
So, got screen sharing on? Wonderful.
Yeah, so my name is Christina Rolfe. I got my bachelor's degree in biomedical engineering from Texas A&M University, and I'm currently working on my PhD at UC Davis. So my field or my specialty is in musculoskeletal biomechanics. So I was going to go through today, talk to you a little bit about what I study, talk a little bit about my research, and give you sort of a brief overview of where musculoskeletal biomechanics fits into the field of biomedical engineering. So to start off with, what is biomedical engineering? So this field of study is dedicated to improving human health and well-being. And what we do is we use engineering and physics and chemistry and all of the different sciences to support medical industries and create products for the healthcare system. Within this field, usually like in your first 3 years at university, you will be doing general engineering classes. So things like statics and dynamics, your standard, engineering curriculum. And then when you get to the end of your junior and most of your senior year, you decide to choose a specialization. And some of the possible specializations include imaging or bioelectronics. So that's creating things like CT machines, X-ray machines, ultrasound machines, like improving those. You could specialize in biomaterials, which is focused on creating materials or using materials that already exist in order to replicate functions of the body. Cell and tissue engineering, which is a really cool developing field, which includes things like 3D printing new tissues or creating like scaffolds for cells to grow on to like grow new organs. And lastly, the field of biomechanics, which is what I chose for my specialization. And so then even within biomechanics, you can come up with other specializations. And this is true for the other fields as well. But since we're talking about biomechanics today, biomechanics breaks down into musculoskeletal biomechanics. So that's looking at muscles, bones, tendons, and ligaments, which we'll talk about all of those. Or cardiovascular biomechanics, which is looking at how blood moves through the body. So as I said, my focus is on musculoskeletal biomechanics, and that's what we're gonna talk about today. But it's really cool that the biomedical engineering field offers all these different specializations if you're interested in any of them. Okay, so what is musculoskeletal biomechanics? With musculoskeletal biomechanics, we study the mechanical principles of living organisms. Specifically, we like to figure out how they move and how the structure of these systems supports their function. So for instance, like how does the structure of the human body support a bipedal organism? So bipedal means you walk on two legs, versus how does the structure of like a cat support a quadrupedal organism, versus how does the structure of a bird, who mostly uses its wings to move rather than its feet, how does the structure of their system end up contributing to their function in life that we know? And so that's what this whole field of study is trying to understand the structure and how that relates to the functions which we know from common knowledge. And a lot of what we do is looking at the energy production and forces. And I know we talk about that a lot in robotics as well, where we're looking at how different forces impact our subsystems for our robots. That's something that we deal with a lot, but of course focused on the human body. So in musculoskeletal biomechanics, as I already mentioned, the three tissues of interest to us are bones, muscles, and tendons and ligaments. And so I'm going to go through a brief introduction to what we look at for each one of these, and then talk briefly about my research into this field, and then open it up to any questions you might have. So with the musculoskeletal system, the goal is to provide form, support, stability, and movement. So this is your bones, your ligaments. These are the things that let you walk around. A couple of other functions that a lot of people, I guess, don't think of as much. So the musculoskeletal system is your primary storage of calcium and phosphorus, which are important molecules that you need for producing energy and stuff like that. And it also contains components specifically in the bone marrow, which produce your blood. So typically we think of the musculoskeletal system as just allowing us to move around. And in general, that's its primary function. But there are secondary functions that are important. And other people, I would say, probably focus on the study of those things a little bit more than I do. I mostly look at how the forces that are on the body are related to like moving or playing sports. So here's just like a quick little simulation of a person walking, and you can see these green arrows are the forces on the legs as they're moving. So I look at those forces, I look at what those forces do to the bones, and then to also all these muscles and ligaments, which are in blue here. Okay. So the reason why we care so much about musculoskeletal biomechanics is because musculoskeletal disorders are actually the greatest cause of disability worldwide. So back pain, typically, like from recent numbers, affects about 632 million people in a given year. Neck pain affects about 332 million people. Osteoarthritis, which if you've ever had a grandparent or something that needs a knee replacement or a hip replacement, that affects about 251 million people per year. And other musculoskeletal conditions, including sports injuries and things like that, affect up to 561 million people worldwide. So there's a lot of people that end up being affected by musculoskeletal disorders. And although these typically aren't deadly, they do cause a lot of disability. And we see that actually over here in this chart, where musculoskeletal disorders contribute to 27% of workplace being out of the workplace due to disability. So we really care about understanding how this system works, partially because we want to reduce the numbers of these disorders in other people and give them a better quality of life. So when we think about this, we're going to start by talking about bones. So bones are sort of the framework of the musculoskeletal system. Everything sort of attaches to them. They're the beams, like if you have like a bridge or something, the bones are the beams of the human body. And they have a structure that is broken up into many different molecules. I'm not going to really focus much on that. But one thing that I kind of do want to point out is that there's two types of bone. One is called cortical bone, which is a pretty dense bone that surrounds the outside of all of your long bones. So this is like your femur, which is attached to your hip. So this would be like your hip joint. And this cortical bone runs all the way down the shaft of your bone. It is really thick, dense bone and supports most of the loads. So when we apply, force of the human body, that's where a lot of the load is supported. There's also these regions of cancellous bone. We call that spongy bone. So this is bone that's actually very porous, has a lot of different like holes in it. So like if you've ever seen like foam, that's kind of what cancellous bone looks like. It's like a foamy type of bone. The really cool thing about cancellous bone is these lines right here are where the densest portions of the bone are located. And those lines perfectly correspond with where the greatest forces are in this bone. And we'll see that in a moment when we look at a free body diagram. But basically, the bone has formulated into this structure so that it is densest in the places where it needs to support the most load, and it has gaps in places where the loading is actually very small. So bone is very adaptive to its environment, and that's one of the really cool things about this structure. So if we look at sort of like the forces on the bones, typically we have some sort of force coming up from the ground. So we'll talk about that a lot when I look at my research. We call that ground reaction forces. So there's always some, force or load from the ground onto the body. There's also the body weight of the leg, or the body weight of whatever structure you're looking at. There's forces from muscles and tendons, which we'll talk about in a little bit. And then there's also forces on the bone from other bones. So this is like the joint reaction force. So at the joint where the hip connects to the pelvis, there are forces at that point within the joint capsule. And within that capsule, there's something called cartilage. And we're not going to talk about that a ton today, but this is what usually wears out with osteoarthritis. So cartilage is sort of a shock absorber within that joint capsule that absorbs some of those forces that are transferred from bone to bone. And this is just another illustration of what I was talking about with the cancellous bone being oriented along the axis of most force. So in a radiograph, so that's an X-ray, typically anything that is really dense will turn white. So the more density, the whiter it is. And anything less dense is gray or black. And so in this case, we can see that these regions of high density would actually mimic where these, like if you summed up all these forces together, the greatest forces would be along all these axes. So once again, this is showing that bone is extremely adaptive and based on the forces on it will orient itself along those directions. Okay. So when we're looking at biomechanics, we treat bones typically as rigid bodies or beams that have the capacity for repair and remodeling. So if you think about an FRC robot or any robot in first, Usually at some point we think of, okay, what are the loads on, this structure of our robot? And we have to calculate what the forces are and make sure that the robot is able to support those forces, and that at the different joints and stuff, there's not too much force. That would be like our joint reaction forces. So a lot of the stuff that we do in biomechanics is actually really applicable to FRC. And I think the perfect example of this is from a couple years ago, sort of this cantilevered climb system that a bunch of teams developed would be a perfect example of when you really have to calculate and see what the forces in these beams are, just like you would need to calculate the forces in the bones for biomechanics. So just like a robot mechanism, we consider stress in the bone. So that's the force divided by the cross-sectional area of the bone. So basically it's just how much force is on it. The strain. So strain is related to how much the bone is, or how much the system is being deformed. So if you think about like a rubber band, the more you pull it, the more strain it has. And also we consider things like moment of inertia. So that's looking at like torques and where the bone is going, like if the bone is going to end up rotating about its center or around some other axis. So same things that we would do when we were calculating if our robot is able to make this climb successfully, we would look at with bones. The one difference is, unlike robots, bones do have a capacity for repair and remodeling. That's the one difference that we have to consider within biomechanics. And so I just want to briefly talk about that. So when a bone accumulates damage, it has the capacity for repair. So if you have like a beam on your robot and over time it's starting to get warped, it never gets better, right? Like it continues to break down. Eventually you have to replace that mechanism. With bones, we usually don't have to replace them. Over time, they do get better. That goes away a little bit with aging, which is why sometimes you need like hip or knee replacements. But in general, bone has a capacity to repair itself. And as long as we don't load the bone too often within a short amount of time, that repair process can take over. And in addition to repairing after like a fracture, so if anyone's broken an arm, that's a repair after a fracture, or a repair after micro damage. So that's like small breakdowns that happen in the bone when you like exercise. So let's say I'm jogging on the treadmill, my bone is taking load and there's going to be small itsy bitsy little cracks that develop in my bone. And that's okay because my bone can repair and take care of those cracks. We also have processes that occur that are not related to repair, where let's say that we do start exercising a lot after sitting on the couch during the coronavirus. And so we go out and we're able to do things again. So once we start exercising, we actually gain bone. So it's not repairing bone, it's just that more bone is being formed in order to withstand the higher loading. Again, wouldn't that be nice if after, several times of doing a specific climb in your robot, all of a sudden your shaft gets bigger so you don't have to worry about it breaking down? That'd be really cool. Of course, a robot can't do that, but your body can. And same thing with when you're growing, your bones get longer, they get stronger, they increase in diameter when you grow. The reverse kind of happens when you age. So that's one of the problems with getting older, is that you do lose bone mass. You get frail and weaker. And those are just natural processes that happen within your bones. So long story short, in general, bones behave very similar to what you would think of with beams on your robot, with this added capacity for repair. So let's take a minute to compare how bones are different based on what function they need. So over here we have a human bone, or a human leg, a horse leg, and a bird leg. And so I think the most interesting thing that I learned when I was studying different bones from different species is that the names of the bones are actually similar. So we have a femur, so does a horse, so does a bird. We all have a patella. So the horse's patella is up here. So this is actually their knee joint way up here. Our patella is here. They have a fibula and tibia. That's here on a horse, and that's here in a human. And then we have phalanges. In a horse, they only have one phalanges. So that's like one of our toes. So if you think of a human versus a horse, the only difference, they have all the same bones, but they're different lengths. So like our first phalanges is like here and is very short compared to a horse's first phalanges, which is quite long and takes up about half their leg length. But we have all the same bones. And then same thing here with the digits. Birds also have phalanges. In this case, they have 4 phalanges instead of 5. So we have 5, horses have 1, birds have 4. But in general, all the bones are the same. They're in the same orientations. The knee's always bent forward. And the ankle, so this is the horse ankle, is always bent. Or sorry, this is the knee. This would be the ankle. So the horse ankle and our ankle and a bird ankle are all bent back. And then these are the toes. So I thought when I was going into studying biomechanics that I would have to learn totally new bone systems for different animals. And that's just simply not the case. We all have the same bones. It's just that a horse has obviously longer and stronger, like greater diameter bones than we do. And a bird has smaller and lower diameter bones than we do. And the reason for this is horses have to support a lot more load than we do. We already talked about this. Bones get bigger the more they're loaded. And in contrast, for birds, they have a much lower load than we do. Usually they're using their wings. They're just perched on their legs at certain intervals for rest. And so their bony structures don't need to be as large comparative to their body mass as ours. So really cool stuff about bones. We're going to transition into muscles. But if you have any questions about bones, hopefully we'll have some time at the end to get back to any of those. Okay. So again, bones are our frame of our robot, if our robot is the human body. In contrast, muscles are like our motors. So the muscles are the ones that are producing the force and making us move. And just like with bones, there's a whole, we call this a hierarchy of muscle, where it goes from, a larger structure down to like the smallest structure. Again, I don't want to get into this a lot, just to show you that it exists. And where all the force production occurs is in something called a sarcomere. So sarcomeres are like only a couple nanometers in length. They're very, very small. And there's these filaments called myosin and actin, which allow the muscle to produce force. So we're going to watch this short video. So this is a myosin molecule. So it has this weird, like, sort of ovular shaped head on it. And this is an actin molecule. And there's like hundreds of thousands of these in a given muscle. And this head is able to bind with these little globules. And then as the head moves, it produces a force. And so we'll actually see that on the small scale and then also the larger scale in this video. So first, the head will come up and bond onto, so the head will come up and bond onto these actin molecules. And as I said, there's hundreds of these, or hundreds of thousands of these. And as they move along, the whole muscle, which is illustrated here, will actually contract and get smaller. And that's how, like, if I'm doing a bicep curl, it's all those little proteins binding to each other that allow me to generate a force to move my arm. Cool. So when we look at muscles, there's a couple of typical curves that we look at. The first is the force length curve. So long story short on this, there's a region of maximum tension that these little myosin and actin molecules can produce the most force. And so usually in the human body, we have established that all of these sarcomeres operate at their optimal range. Typically, they don't operate where they're too short or where they're too long. And as you can see, when they're too stretched out, only a couple of these heads are able to bind. Whereas when they're too close together, there's overlap, so there's not as many binding sites either. And that's why this is sort of our optimal place where there's the maximum number of binding sites between these two molecules. And again, every bond generates a certain amount of force. And to give you an idea, each one of those bonds, the force that each one generates is about 15 piconewtons, which a pico is like 10 to the minus 15th. So if you imagine like moving your leg or something, you're actually, have to generate about 500 newtons. So if you think about that, you're creating like 500 times 10 to the 15th different bonds in your muscle, which is a huge, huge number. That's 10 to the 15th. It's like beyond trillions. And this is all happening and you don't even have to think about it. So the other thing that we look at with muscles is something called the force velocity curve. And basically what this one is saying is that the faster the muscle is shortening, so like the faster you're doing your bicep curl, the less force you can actually generate. And the reason for that is, again, with these small little molecules that are binding to each other, like the faster that they're sliding past one another, the less likely they are to actually bind and generate that force. So over time, the faster you're doing bicep curls, the less weight that you can actually curl when you're doing that. And I don't know if this looks familiar to any of you, but this is very similar to how motors work. So if we look at this power curve of a Falcon 500, which is a pretty typical or a common FRC motor after last year, we have this similarly shaped power curve where the faster the motor is going, the less torque the motor can generate. And that's very similar to this curve that we have here. Though with motors, they're going to be a linear curve, whereas with muscle, we have sort of this nonlinear shape. But in general, we have this sort of same idea where there's a power curve where our maximum power that we can generate from our motor or our muscle is somewhere where our velocity or RPM is balanced with the force or torque that we're generating. And I guess the one big difference here is motors are typically doing torque because they're doing a rotational motion. Whereas with muscles, the way it's structured is it's creating a rotational motion around a joint, but the muscle is moving linearly. So it's almost it's like a motor behaving as a piston, which is, I guess, a weird way of putting it. But essentially, what this goes to show you is that a lot of the things that we learn about in FRC can be applied to biomechanics. And this is just one example of that. So when we're looking at muscles and how they perform, we're really looking at two different things. The first one is something called the physiological cross-sectional area of the muscle. And really, this is related to something called the pennation angle. So if we have a muscle where these are like little muscle fibers within the muscle, if they're all lined up vertically in parallel with each other, the cross-section of this muscle is actually small, so it can only generate a small amount of force. But these fibers are very long, so they can change a lot in length. So your biceps is an example of a parallel muscle. In contrast, if you look at like your quadriceps, they are something called pennated muscles, which means that the fibers are oriented along a given angular axis. And if we're looking at the cross-sectional area of this muscle, it's actually much larger than this muscle because, like if you consider one of these red arrows here, that would be the true cross-section of this muscle because each of these fibers is able to generate force. So pennated muscles have a much larger force potential in about the same volume, but they have a smaller length change. So that's the one disadvantage. So you can either have muscles with small forces but large length changes, like the biceps, or large forces but small length changes, like your quadriceps. And that's one thing that differentiates one muscle to another, which we'll talk about in a little bit. The other thing that differentiates different kind of muscles is something called the muscle fiber type. So if you've ever eaten a chicken, there's both white meat and dark meat in that animal. So white meat is going to be mostly found in like the breast region of the chicken. And that white meat is a type of fast glycolytic fiber. So it's this type 2B fiber. And essentially what that means is the muscle responds very quickly to input and allows the animal to generate force quickly. So if you think about a bird, that typically makes sense that in their breast region, which is where their wings are attached to, they might need to be able to generate force in those muscles quickly. In contrast, slow oxidative fibers are usually colored red. And so that's our red meat in our chicken. And we see that in like the legs and the thighs. And again, we talked a little bit about birds where their legs don't really do much. It's not like chickens do, but they don't typically run around on their legs. If they really need to get away from something, like fleeing something, they would use their wings. So this idea that the leg muscles are slow oxidative fibers, which means they respond slowly to a given input, actually makes a lot of sense when we're thinking about birds. With humans, this can determine the type of running you're best equipped for. So everyone's born with a certain amount of these different fiber types. So type 1 fibers are typically related to long distance running. So if you were training for a marathon, you would do a certain training type in order to increase the diameter of your slow oxidative fibers. In contrast, if you wanted to run like the 200-meter dash or 100-meter dash, you would build up your type 2B fibers, which are your fast twitch fibers. So an interesting fact that I learned when I was taking a class on this stuff is they've actually tested Usain Bolt, and he has a higher percentage of these type 2A and 2B fibers than most normal human beings, which is actually why he's so fast. So to a certain extent, what you're good at doing comes down a little bit to what you were born with. To another extent, through training, you can slightly change the composition of these fibers, or at the very least, make the fibers that you have that are slow twitch or fast twitch fibers, you can make those fibers larger, which does help you out. So it's not like Usain Bolt is incapable of running long distance. It's just that he's more competitive at running shorter distances because of his biological and biomechanical makeup. And so understanding, how this sort of muscle structure affects function, again, allows us to do some comparative analyses between humans, horses, and birds. And so I specifically picked the gastrocnemius and the soleus, which are two muscles that contribute to flexion of the ankle. So flexion just means movement of the ankle. And we see the gastroc and soleus in both the human and the horse, but in the bird, the soleus is missing. They only have the gastrocnemius. So we can assume that the soleus maximum force is 0. And so if we look at this table, there's a lot going on. But essentially, in the chicken, which again, the legs in the chicken don't really do a whole lot, as a proportion of body weight, the maximum force that the gastrocs can provide is very, very small. It's like 1/14. Whereas with the horse, it's about half. And with the human, it's about 1.5 times the body weight. And so that's actually like a really interesting thing. So the gastrocs are not very powerful in the chicken. And we also talked about the main fiber percentage is these slow oxidative fibers, which is why we consider this to be red meat, or dark meat, I guess. So it's a darker color than the breast meat. So if we look at the difference between the human and the horse, we see some other cool things. So in the human, the gastroc does produce a lot of force, but not nearly as much as the soleus. The soleus is the main contributor to producing force about the ankle joint. Whereas in the horse, most of it comes from the gastrocs and not the soleus. So that's kind of flip-flopped. This makes a little bit of sense because in the horse, the gastrocnemius has a high percentage of these fast fibers, which makes a lot of sense because horses typically, like at the competitive athletic level, can run extremely, extremely fast. So the horse gastrocnemius typically allows the horse to be faster than a human, whereas with a human, we have a higher percentage of the slow oxidative fibers in general along both of these structures. So just some interesting things that once we understand how muscles work, we can start making sense of, okay, why does a horse do what it does? Why does a human work the way it does? Why does a bird work the way it does? We can explain a lot of these things. So that's pretty much the story for muscles. Again, make sure if you have any questions to post them and we can come back to them. But I'm just going to move right along to our last piece of the puzzle, which is our tendons and ligaments. So tendons and ligaments basically connect the bones and the muscles, which we just talked about, to each other. So tendons connect muscles to bones, and ligaments connect bones to other bones. These are very similar structures, and in general, I'm just going to talk about them as one unit, but they do have slightly different properties. So for instance, tendons typically are stiffer than ligaments, and ligaments typically are more elastic than tendons. So you could stretch a ligament further than a tendon, which is related to this failure strain here. So a ligament you can stretch about twice as far as a tendon before it breaks. And then in contrast, a tendon can support more load than a ligament. So, but in general, very similar structures. We can talk about them sort of in the same way. So if we continue looking at our lower leg here, so we have the Achilles tendon, which connects our gastrocnemius that we just talked about to our bone, which is our calcaneus right here. If you've ever heard of someone like spraining their Achilles tendon or like shearing their Achilles tendon off, that's typically a really bad thing, because unlike bones, and I guess we didn't really talk about it, but muscles also have a huge capacity to repair. Like anytime you work out, you're literally breaking and ripping muscle fibers, and you do even more damage to your muscle when, like, on a daily basis than you would to your bones. And that's why you're typically like really sore, or you can be really sore after working out, is because you're actually breaking down those fibers and your body has to repair them. So sorry, I guess we didn't really talk about that, but muscles and bones, they are repairing themselves constantly, they're breaking down constantly. With tendons and ligaments, that's not really the case. The amount of blood flow to these structures is really, really small. So they're not able to repair themselves as much. So if someone like tears their Achilles tendon, that typically requires surgery because they have to like actually go in and fix that. So tendon and ligament injuries are very bad for that reason, that they're just not structures that have a huge capacity for repair. So yeah. And these structures, when they connect bones to each other, they provide stability in the joint. So they keep the bones from translating too far away from each other. And the best correlation I could think of this in robots is surgical tubing. So think of these tendons and ligaments as surgical tubing that you have, you know, supporting a mechanism, helping to supply some force so your motor doesn't have to do as much work, and help to stabilize a joint. So that's the same thing that the tendons and ligaments do for us. So I'm going to talk a little bit about tendon and ligament mechanics. I think this is like the toughest one to really wrap your head around. And that's something called viscoelasticity. So viscoelasticity means that a structure behaves as both an elastic structure and a viscous structure. So elastic is pretty easy to understand. Elastic structure, that would be like a rubber band. So a tendon could behave like a rubber band where you stretch it, and then as you stretch it, the force increases. So if you've ever shot a rubber band at someone else, the more you stretch it, the further it goes. That's the elastic part. So the viscous part, I have this video here. If any of you have made oobleck, so it's a fun little Dr. Seuss thing, but essentially this is a mixture of water and cornstarch. And so if you like poke it, like what this woman is doing, it appears really hard. But if you like slowly insert something into it, so she's going to do that in a moment. Like, so if you slowly pull it, it's able to move more. And so that's a viscous structure. So basically the faster the strain rate, so like the faster you're poking it, the more force it applies. And then the slower you're poking it, the less force it applies. So if you pull it slowly, it's able to move really easily. If you poke it hard, it feels like a stiff surface. And so with tendons and ligaments, it combines those two ideas into one structure. So essentially at low strain rates, it has low stiffness. And as that strain increases, the more you pull it, the tendon gets stiffer. So if you think again about, you know, doing your bicep curl, your tendon is elongated and stiffest when your arm is fully extended. And then as you pull your arm up, the stiffness is actually decreasing. So another thing that's interesting is the stress actually in the tendon will actually increase as the strain rate increases. So again, the faster you're doing your bicep curls, the more force you're able to apply with a tendon or ligament. So that's like the opposite of the muscles, where the faster the muscle's going, the less force it is. Now we have the opposite phenomena here. So I just wanted to do a side point that understanding how springs, and this is called a dash pot, which is the viscous one, behaves is something that actually is really important for a lot of things. So I talk about it in my field for viscoelasticity, but if anyone has done a PD loop for programming, it's this same idea where you have your spring component and your dash pot component. So the spring component is changing based on a constant variable, whereas your dash pot component is changing based on the derivative of that variable. So that's just a fun little correlation between mechanics, I guess, and things that we use pretty often in programming. So just to kind of show you that just because we're doing mechanics doesn't mean if you're in programming, you don't need to understand it, because a lot of these principles apply across different fields. So comparing tendons and ligaments between different animals, again, this is kind of like bones, where the tendons and ligaments that we have are pretty much the same. The length scale is just different. So in the horse, the tendons and ligaments, again, are going to be bigger. They're going to be helping to apply more forces, thicker diameter, smaller in the bird, and then sort of in the middle for the human. So the muscles are the one that really change a lot based on the function of these animals, whereas the bones and the tendons and ligaments are pretty similar. So in the last 5 minutes here, I just wanted to briefly give sort of an application to what we were just talking about and talk to you a little bit about my research. So I work specifically looking at show jumping horses. So show jumping is a timed event. Usually horses are looking at both speed and accuracy, so you get points off if the horse hits and knocks down a rail. And with this event, what we really look at is tendon and ligament injury. So that's kind of a nice transition there. So when they land, there are forces. So that's these blue arrows right here. There are forces that act in both the vertical and shear or horizontal direction. And these forces act on the hoof, and these are our ground reaction forces. So we talked about those right in the beginning with those green arrows that come up as a human's walking around. So the reason why this is so important is that 48% of elite show jumping horses usually become injured within a single season and lose days because of these musculoskeletal injuries. And usually this is tendon and ligament injury. And we're specifically looking at the tendons and ligaments on the back of the lower leg here. So I'm not going to talk about them in like great detail, but these ligaments at the back of the leg that we've kind of been looking at this whole presentation are the ones that are most commonly injured. And we really care about this partly because of animal welfare, partly because elite show jumping horses are expensive. They can be up to $15 million. That's US dollars, so even more than that in Australian dollars. And then there's also a risk of injury to the rider. So if the horse gets injured, the risk of injury to the rider greatly increases. And I just want to clarify that actually in this image, nobody got hurt. Both the horse and the rider were okay, which that's why I feel like I can use this image, because I can assure everyone that in this example, it was okay, but that can happen where it's much worse consequences. So I'm going to skip ahead a little bit here. Oh, sorry. Okay, cool. So I wanted to talk a little bit about how we look at injuries to these horses. So usually we put on these markers along the leg, and we're able to track the markers over time while the horse is jumping. So here's a quick little video showing where we have our horse with all the markers, and we're able to record those marker positions with a video camera. And based on that, we can create these graphs showing what the angle of the different joints was over time. We then can put this into a computer model and actually line it up so that the motion of the computer model and the motion of the horse's legs are perfectly correlated with one another. And notice in our computer model, we have, so these red lines actually represent both muscles and tendons and ligaments. So that's all three of those. And then we have our bones. And by doing this side-by-side sort of matching, we are able to figure out what is happening in the tendons and ligaments and what the forces are without having to do anything invasive. So this is totally non-invasive. These markers are just on the surface of the skin. There are some disadvantages of that, but in general, a very easy way to figure out what's going on the inside. And from this computer model, we can look at all sorts of things if this loads. Yeah, so we can look at tendon ligament forces, we can look at muscle forces, we can figure out when muscle is activated. So this is looking at what the muscle forces are at landing. We can, as I said, compute the strain. And I know it said tendon strain, but this is actually both tendons and ligaments. And do a lot of cool things with computer modeling to try to figure out what's going on with the body, why these failures are occurring, and explain that a little bit more. So in addition to doing this with horses, we do this with people too. So we can use similar computer models to analyze how a human would spike a volleyball and what those forces would look like. And on the same token, we can look at, what the forces are from swinging a baseball bat. So again, you can see there's these little markers that we're able to put on specific joints, and it tracks this motion. And then we can use these motion profiles to study things that would normally require invasive procedures in a non-invasive manner. Cool. So in summary, biomedical engineering is a really cool field, at least I think so, that incorporates a lot of different principles that we learned in FRC. There's tons of different specializations. I'm partial to musculoskeletal biomechanics, but I greatly encourage, if you're interested in any products that would support the medical industry, to check this out and maybe find a specialization that is more interesting to you. And now I'll open it to any questions, and here are my contact details, so you can feel free to email me or find me on Facebook or LinkedIn if you would like to discuss more.
All right, thank you very much, Christina. That was a fantastic presentation. I reckon everyone watching learned an awful lot. It was a wonderful introduction to the world of musculoskeletal biomechanics. Sorry, I've been practicing that many times. It's a bit of a mouthful, but that's all right. We actually do have some questions from our YouTube viewers that I'd like to push through and hopefully get some nice answers. So given the complexity of the bone structure, one of the bone structures you demonstrated, do hip replacements or joint replacements come close to the same level of effectiveness as regular bones for the purpose of load bearing?
Yeah, so actually, before, when I was doing my undergrad, I studied a lot about knee implants, specifically doing some research there. And the thing that we find a lot with knee implants is we can't figure out how to create something that is as strong as bone, but only as strong as bone. We end up having to use metals like titanium or aluminum that end up being a lot stronger than bone. And this can lead to a lot of potential problems, one of which is called stress shielding, where the titanium or the aluminum implant are taking so much of the stress away from the surrounding bony tissue that the bone actually ends up disintegrating. So we actually talked about how bone, it's like use it or lose it. Like if you don't keep stressing that bone, keep applying force to it, the bone will get smaller, and that sort of thing. So there's this problem within the field where we can't exactly replicate the modulus of elasticity of the structures, and we end up using materials that have a much higher modulus and thus are not able to mesh completely with the bone tissue. So that's absolutely, if you're interested in that area of study, that's absolutely an area of study that's getting a lot of interest right now, is trying to figure out new materials to use for that.
Okay. That's actually really interesting to think about concepts in the way of, because that's a big thing, like you said. One of the other questions we've got is, do the density lines in bones change significantly between person to person, or are they fairly similar between everyone?
So in general, they're pretty similar between people. You'll notice slight changes actually between women and men. So women have a wider pelvis just because typically childbearing, you need a wider pelvis in order to do that. So you'll notice some differences between gender, and then there will be differences as you age where just the bone density is getting lower. But in general, if you were to take those changes, like the wider pelvis, and run it through like a finite element analysis, you will find that the lines with the highest density are always along the maximum force for that person, which is, I think, really fascinating that the bone is able to know that and adapt that way.
Okay, that actually is really interesting. Another question we've gotten is that biomedical engineering seems to be a mix between engineering medicine, sort of like the name suggests. And actually, one thing that I really enjoyed about the presentation is, at least I've found that physics and chemistry go hand in hand, and then physics and biology go hand in hand. But I love how this sort of merged biology and physics instead of chemistry, which is quite interesting with all the calculations and the physical aspects of it. But the question asks, how much of biomedical engineering is engineering and how much is more medicine, in your opinion, at least?
So it depends totally on what specialization you go into, I think, is the best answer. Like on a day-to-day in my lab, like I'm running, like I'm doing free body diagrams constantly. Like I'm doing the physics and the mechanics, because actually one of the things I didn't get to, which I can show, is in addition to looking at these horses, we also looked at the ground that they jump on, because the higher the ground reaction forces, the more forces in these legs. And so I actually used my robotics knowledge to design this testing equipment, which measures what the shear forces are in the surface, and then also a piece of equipment that measures the vertical impact forces. And so for me, like, this is the stuff I do. I'm, finding motors, running electronics, stuff like that. I would say that for the rest of like my peers in grad school, that's not the typical. Most of them do stuff with cell work. They're more on the tissue engineering side of things. And so they are a lot more interested in the chemistry of what's going on. They're doing wet lab work, whereas I'm out in the field with dirt all over me, looking at how horses move. So I think that's one of the cool things about biomedical engineering, is that depending on what you're interested in, you can go into any of it. Because I know also that there are people, even within my veterinary orthopedic research lab, that instead of focusing on like sort of sport performance like I do, they're more focused on, okay, how does bone change on a like molecular level? Like if we put different chemicals into like a person, like if we give people a certain drug, like what does that do to the bone? I know one of my colleagues even looked at how smoking affects bone disintegration in mice. So I would say that there's not a great answer. The field is sort of open to any of it. It just depends on what niche you want to do and where you want to focus.
So, from what I understand, you would have had some experience with, I believe, FRC, or at least one of the first programs. Am I correct in saying that?
Yeah, I am an alumni of an FRC team actually based out of St. Louis, Missouri. So
Okay, awesome. And would I be right in assuming that your experience with FRC is what got you into at least engineering?
yeah, so originally I actually wanted to just go into veterinary medicine. And then after my participation in FIRST, I decided that I definitely wanted to start in engineering somewhere. And I thought biomedical engineering was sort of a great specialty that sort of, uh, you know, combined my love of medicine, my ability to work with medicine and animals specifically, and then also engineering skills. Like I've actually shifted. So instead of going to vet school, I want to build like orthotic and prosthetic devices for animals. So that is my dream job, I guess you could call it.
That's incredible. So you really you can really tailor at least biomedical engineering to what you want. You wanted to go into veterinary studies, then you want engineering. Put them together. That's incredible. That's really awesome.
Yeah. There's a lot of flexibility. Like I would say that of all the engineering fields in biomedical, like in your general curriculum, at least what I did, I had to take like 4 mechanics classes, 4 electronics classes, 2 imaging classes, and like 3 materials classes. So I'm getting the material engineering, I'm getting the electrical engineering, I'm getting the mechanical engineering as my background. And then, in those last 2 years, you really get to choose, okay, which one do I like and which one do I want to pursue further?
Okay. Going back to some of the viewer questions that we've got, one of them asks, so you've mentioned that there are 3 different types of muscles. So what type of muscle would you say an organ like the heart is? And what type of muscles do the automated systems like moving food through our digestive system?
Yeah, so I guess I was specifically talking about skeletal muscle. So there is cardiac muscle and smooth muscle. So smooth muscle is what's like in your digestive system, and then cardiac muscle is obviously for the heart. And those have slightly different structures. I know enough to be dangerous about both of those, but I would not call myself an expert in them because they're not really part of the skeletal system. But in general, very similar in structure. Smooth muscle, they have different contractile properties. So we call skeletal muscle a striated muscle, and that's because of those sarcomeres that are lined up perfectly, and that's those actin and myosin molecules moving against each other. So in smooth muscle, we typically don't have that striated appearance. Like if you looked at the muscle of the stomach or the large intestine, it would just look smooth. And the reason for that is not all the muscle fibers are aligned perfectly in those muscles. So they act differently, but in general, same idea. They have myosin, they have actin, they contract. It's just how they do it is different.
Okay. One last question for the moment, I reckon. What advice would you give to a young engineer that's interested in studying biomedical engineering?
Yeah, so I would say the best advice I would give is find a university that is like that has specializations that you're interested in. Because I know that like there's a ton of different universities and some of them might specialize in one thing more than the other. So like at Texas A&M, they were very focused on biomaterials. And I was able to find plenty of biomechanics research even there. But I know for like going into grad school, I wanted to find a university that was even more heavily focused into biomechanics, which is why I switched over to UC Davis. And I would say that just like if you want to go into this field, try out different specializations. Like you can do rotations through different labs during your undergraduate studies to see which one you like. But then if you decide to, continue your education in grad school, I would really recommend finding a university that has the specialization that you want to continue in and is really strong in that specialization.
Fantastic. Well, thank you very much for speaking with us today. Would you mind just quickly popping that slide that had the contact details on it in case any of our viewers would like to get in touch with you?
Absolutely.
Fantastic. Now that was incredible. We learned a lot, and I think probably the thing that I loved about that presentation the most was how you linked it into FRC and robotics, because obviously as a member of a robotics team, starting to get into that mechanical side of things, but then seeing how that can apply to not only humans, but I guess biological parts. That's really awesome and really cool to see. Thank you very much for sharing today. Thank you.
Absolutely. Thanks for having me. I had a blast. So.
Oh, it's fantastic. You enjoy the rest of your time, is it?
Yeah, it's 1 a.m. So I'm probably
1 a.m. Okay, I think we'll let you go to bed now. I think that sounds like a great idea.
Take care.
Have a great night.
Bye.
All right. We've been having a great time over here at 24 Hours of STEM. 24 Hours of STEM would like to give a quick thank you to our sponsors, Boeing, Google, and Macquarie University. Just a reminder, if you haven't already had a chance, please check out the 24 Hours of STEM challenge at our website. The website is 24, that's the numbers 2 and 4, hoursofstem.org. The challenge is open to all ages and groups, and 4 lucky teams will win a LEGO Mindstorms EV3 kit. That's incredible. Would now like to welcome our next guest, Gary Law from the Creator Academy. He's going to be talking about designing FLL challenges with fun. Gary, how are you today?
G'day, how's it going, Caleb? I'm great.
Very good. Awesome. You're ready to start whenever you like.
Sure, I'll just get my thing set up.
Awesome.
How are you going? Have you been staying up for a long time?
No, it's a pretty normal, reasonable time at the moment. 7:30 in Adelaide. You're in Sydney, am I correct?
I'm in Sydney, yes. So I just taught my last class. So.
Oh, righto. Yeah. Awesome.
Bear with me.
All right, no worries. I'm very much looking forward to this as, getting started with FLL this year. Volunteering as a referee, seeing the amazing stuff that happens. It's a cool game. I can't wait to, hear about what goes into the design of different challenges and just making it fun, because that is what FLL is, in my opinion, at least.
Absolutely, absolutely.
Awesome.
Cool. Can you see my screen and can you hear me properly?
Well, you can see your screen and we can hear you.
Cool, fantastic. Thanks very much, Cal. So is it okay if I just get rolling?
Yeah, fantastic. We can't wait.
Cool. So, hello. My name is Gary, and today we're going to talk about teaching children FLL challenges with fun in mind, and something that I learned as a coach and also as someone who is a computer programmer practitioner is that fun is really an important part of your learning journey, and FLL. First LEGO League is a learning experience. Even though it looks like a game, it really is about challenging kids to be very creative and also going through a bit of a learning journey, as well as having fun. And sometimes there are challenges with teaching kids. Teaching children, I consider, is actually a major challenge. Children come from all different sort of personalities, just like how adults are. And I have taught a lot of adults how to code before I started teaching children how to code. So what I find is that children have shorter attention spans. They are less familiar with dealing with stressful situations. And some kids have an aversion to setbacks. Sometimes they might grow up in an environment where it is constantly sort of rewarding in a way that they see setbacks as a very like a barrier where they can't overcome. And that is what I am talking about today. It's about making challenging situations fun challenges, a way that makes it so that kids can accept difficult tasks, and also receive feedback in a way that makes learning fun. Okay, so I hope that today after this presentation, you'll go away a little bit more inspired and hopefully have some more ideas about how to design challenges for children, especially for FLL. Okay. So a little bit about me. This is a picture of me with Professor Michio Kaku. He's an American scientist who very famously advocates string theory. It's a very, very cool dude. I was at his book signing when he was in Australia a couple of years ago. And I actually graduated from university with a film degree. I was very much an film kind of expert at the time. I thought that this was the kind of avenue I'd be going down. But then somewhere along the line, somewhere during that film degree, I picked up animation. And that sort of carried me through to my first job, where there was a company that needed an animator, but then they also wanted that person to learn about making interactive animations as well. So that's how I sort of picked up making video games. And then I was a video game designer and developer for about 12 years before I left my job and started to think about how I can sort of share my knowledge of video game design and development and teach the next sort of generation of kids. Because my experience with programming is probably going to be very different to a lot of the experiences of what kids can have now, because I had to read a lot, read a lot of like textbooks and consult a lot of experts in order to sort of get started down this sort of computer programming kind of role. As you can imagine, when I was sort of studying for film, there was no sort of precursor to sort of saying, yeah, I need to learn sort of any sort of programming when I was in high school. So I only really started after I learned animation, and then sort of trying to pick up programming languages, trying to learn things like, if statements, cases, classes, all that kind of knowledge I had to sort of learn myself. And it wasn't a super fun experience. It was really, really difficult. And I thought that once I sort of got to a certain point in my career, I decided that I wanted to start teaching children so that they would have less of this kind of difficulty. And luckily, we have wonderful programs like the First Lego League and all sorts of software and hardware solutions that kids can use to learn science and technology in a really, really fun way. So that's very fortunate. So yeah, since starting to teach kids about robotics, I've been running FLL programs for the last 3 years. And that's why I am here today. Whoops, going a bit far. So what we're going to talk about is gamification, or making, using game mechanics to make tasks, non-gaming tasks, more fun and more engaging for people. Gamification, when I was studying, was a bit of a buzzword, and a lot of people might have heard of the term gamification before. But hopefully I'll be able to offer some of my unique insight into how gamification is applied in FLL as a context for making learning challenges more fun. Why does gamification matter? It makes tasks more enjoyable. This is true for FLL. This is true for everyday life when you are going through your job or going through an arduous kind of task. Making it more enjoyable is very high on the priority list as humans. As of course, if you're if you're a robot working in an assembly line, you don't need to be doing a fun task. But as humans, we rely on tasks to be engaging, to be fun, in order to make ourselves more productive. It improves student focus and engagement. And like I said before, teaching children is difficult because they have these shorter attention spans. And when you use gaming mechanics, you are making things more engaging, more fun, and it keeps kids more focused on that experience. And finally, it also encourages structure and consistency. This is really good for teaching kids who might not have a very a regular sort of pattern in their lives yet. They might be studying at different hours in the day, or they might be not as regular in their tasks as normally the adults would be. So by gamifying a challenge, we are encouraging them to be more consistent by giving them a consistent experience. So the gamification term was defined in 2002 by a man named Nick Pelling. And even though that the name is new, the idea is a very old one. The first time I came across gamification was through a book by a lady named Jane McGonigal. She wrote a book called Reality is Broken, and she argues that a lot of the human sort of the daily lives of humans can be improved by making it more like games, or to sort of add some sort of game reward theory into the way that we do things. And this applies into your everyday life, your work, your study, and she has written and made a lot of really cool talks about the subject. So for an example, one of the most famous stories about gamification is the idea of the famine game. So you've heard of the Hunger Games, right? This was, the famine games is a real life history about 3,000 years ago in a place called Lydia in the Mediterranean. And during that time in this little country, this little kingdom, they were experiencing a severe drought and famine. There wasn't enough food to go around. This was an existential threat to this whole society where there's not enough food to go around. And some point along the line, they decided that society needed to change in order to combat this famine. And the best idea they could come up with at the time was that they will develop a series of dice games. And these dice games will be run every week, and they would substitute eating. So they would play these games on like a Tuesday and Thursday, and they'd say, all right, instead of having any food during this time, we're going to play this really engaging dice game that the game developers have developed. And they were able to survive for 18 years through this entire famine just by playing games and trying to suppress their need to eat on certain days of the week by playing this really engaging game. I'm not sure if you've ever played a really addictive video game, but imagine if we had a situation like that today, where we said, we don't have enough food to go around in your country, and the only way we can stop this food shortage is if we restrict the amount that people are eating. And everybody needs to play Among Us every day on Tuesday or Thursday instead of eating. That is the equivalent of what the Lydians did for 18 years, okay? These guys were able to survive an 18-year famine by not eating for 2 days a week, by playing games. So this was a game that was so popular amongst the old people, the young people, that it just eclipses anything that you would know of today. So like, just forget World of Warcraft, forget Dungeons and Dragons. These games were amazing. And this is how the theory of gamification really started, is the idea that we are doing things that are hard, but making them enjoyable at the same time. So this was one of the first very literal examples of gamification. And how it works is that basically we implement game mechanics to enrich non-game tasks. For example, there are things like reward systems. So a very good game or a very addicting and involving game has a very regular and patterned reward system. What people don't like to do or think things that are boring is when rewards or feedback comes back in a irregular manner. So imagine if you're doing a very, very tough school assignment and it is due at the end of the year, and you have this this several month period where you have no feedback, no indication of where you are, and no kind of consultation with the teacher. This becomes a very boring task because kids don't feel like that they are making any progress, because not because they're not making any progress, it's because the person who set the assignment has made it so that it is not gamified. It is not a system that encourages regular feedback, regular reward. To have an assignment that is due after a long time with no sort of check-in times in between becomes a very arduous task. Also it makes, to be able to have achievements and milestones, a lot of games nowadays that are very addictive, they have ways where you can sort of show off your achievement. So a lot of games that are on like PlayStation or your Xbox, they will have things like badges and achievements that get unlocked. These messages that constantly come back and tell you how well you are doing. Even sometimes how bad you are doing, they'll give you cool achievements and unlocks as well, because that keeps people interested in their own progress, and that gets people to understand how they are going in this game, and it keeps them interested because it shows them that the game developers are sort of looking out for you. Hey, we made an achievement when you lose against this boss 3 times in a row. So that's kind of cool, even though it's like you're not technically winning. To make an achievement for losing, it's still something fun for people to be receiving. So feedback is a really important part of gamification. We also have things like leaderboards, where like in FLL, you would see when you have a scoreboard pop up and then you see, oh, your team is at a certain level compared to other teams. That's really fun for people to look at and say, wow, that's kind of cool to be ranked like in this sort of way. Even sometimes when they're ranked high or low, the experience is different for each team. The experience is that, you know, they might be looking at one leaderboard that sees that, oh, maybe we're not doing too well this time, but they might look at another leaderboard and they'll see like, oh, well, actually this is one of our team best, personal bests for our scoring. So the way that you sort of display this information in a way that shows progress is very, very important in gamification. One of the very sort of the latest sort of examples of gamification, probably not the latest. I mean, this was the latest when a few years back, but Fitbit does a very good job in keeping people obsessed with doing 10,000 steps, right? Fitbit had a very basic design where they put a pedometer in a device on your wrist, and it measures every step that you take. And why it is so addicting is that when you reach a 10,000 step threshold, it makes a little sound, it makes a little vibration, and it tells you that you have done your recommended exercises for the day. Of course, it's not completely scientifically accurate for each person, but what it does do is that it makes people gamify it. It makes people understand that I want that little feeling of reward at the end of the day when I do my 10,000 step. and it's a really strong motivator, even though it's very, very simple, to make people do a lot more exercise than they normally would if they didn't have this device. They also use achievements to make sure that people can unlock different things, like maybe you have a 2-day or 3-day streak where you have done a certain amount of exercise. Or maybe there's an achievement for doing exercise after a long break from exercise. That way, Fitbit is constantly rewarding people, no matter if they are doing exercise or not doing exercise. They're still reminding people, hey, we're giving you an achievement, just to remind you that this is the kind of level of activity that you have done. And even though it might seem like a very, very small reward, it might seem like very shallow, but it is proven to be a very strong motivator. And of course, it has leaderboards and standard fitness tracking as well. Because like we said before, when you're able to sort of see your progress, see your name in a list, ranked like several thousand among like however many tens of thousands of people, you feel like, man, I'm making some progress. I am doing a lot more exercise than I normally would have if I didn't have this device. And then fitness tracking in general is very, very good, because if you were doing all sorts of exercise and you never sort of check your weight, or you check the calorie counter, or your step counter, then it's very hard to sort of judge and reward yourself for how well you are doing. So feedback is a great reward. Another example of gamification is this software called Foldit. And Foldit is a puzzle game developed by scientists who need to crowdsource help to develop proteins to help fight certain diseases and viruses. And Foldit has been credited with solving a lot of very complex problems to do with curing serious diseases, things that would normally require a supercomputer to be running many, many months on. Foldit is able to do by making itself a video game and then giving it to people to try and solve. So these are very tough challenges. These are 3D models that needed to be like folded in certain ways. But even though it's super complex, there are still people who want to play this game because they want to be recognized as someone who has helped develop a vaccine or a certain kind of medicine for science. So the scoring and the high scores are very important in this game, and to have the real world impact is very, very important in this game as well. And Coinland is an example that I put in here because this is one of the games that I built for a bank in Australia back when the Dolomites were a really big thing. So a while back, this bank had an idea to build a game to teach kids about financial literacy. And the thing that we wanted to teach kids about was that you can earn money through doing jobs, and the way they represented jobs in this game was these were these mini games that weren't very fun. Okay, so these were a little bit more repetitive games, but you earn money from these games, and then you can also spend money on these other games which are more fun, like you take a water pistol or play a roller coaster kind of game, which is more fun, but that costs money. So this video game was designed to teach kids the benefits of making choices that are very similar to real life. It's like you need to do a lot of tasks to earn money so that you can do other things that you want to do. And another cool thing about an addicting video game is the idea of creating decorations or avatars. So in this game, people can buy hats or clothes or dresses, much like an RPG game like Warcraft or some other games that allow you to sort of change your appearance. So when you earn enough in-game currency, in-game money, then you can change your avatar to look really different to other people who haven't been earning as much money, or who have been spending money on other things, like going on roller coaster rides, for example. So this game is designed to reward kids with more patience and learning about financial literacy. And then this is another game that that I developed before starting an FLL team. It's called Soundstorm, and this is designed by the Macquarie University. They developed a software that helped cure something called spatial processing disorder. So some children will actually have this auditory disease where they aren't able to isolate messages from people who are further away. So what this manifests itself in the classroom is that a kid might be sitting at the back of the classroom, and then the teacher might be talking in front of the classroom, but they can't physically hear the teacher because someone else is talking next to them, and they can't isolate the signal from somebody who is further away in the classroom. And sometimes this gets misdiagnosed, and people might get misdiagnosed with things like ADHD or an attention deficit disorder, when in fact it's an actual spatial processing disorder. So it's an auditory issue. So Soundstorm was is a reskin of the software that or the auditory health expert would use to train kids to listen in a better way. So this software is very hard to do. You can imagine that if you are a child, you're trying to listen to a very faint message in the background when there's all these other noises or people talking around you. It becomes very frustrating. But what we do is we created a reward system so that if kids persist through these exercises, then they get rewarded with these cool drawings or these cool little videos to sort of recognize that they have just completed a very difficult and arduous kind of challenge. So how does this apply to an FLL challenge? Well, FLL is divided into the four categories. We have the robot game, the robot design, the innovation project, and the core values. And the great thing about FLL is that it is not focused just on the robot. The learning experience is really very diverse, and it encompasses a lot of skills that you don't actually require in some other kind of robot challenges. And that's what I really like about FLL. The robot design, the innovation project, and the core values is also an integral part of this experience. So the robot design and the robot game portion of FLL is about using your robot to score points on a map. And this is probably the most recognizable and the most easy to understand portion of First Lego League Challenge. It's because there is a very clear scoring chart. The rules are very straightforward. Like, your robot has 2.5 minutes to complete these challenges. The more points you score, the better you do. So this game is probably the most gamified part of FLL. But even though it is already a game, it still pays to make it more fun for the whole team. Especially if you have a large team, you might find that not many people can operate the robot at the same time. So it's important to make this experience as fun for all teammates as possible. What I like to sort of look at the robot game is that it's like a pit crew, right? We have some 1 or 2 people who are controlling the robot, but then there is a dedicated support network for the robot. People need to be placed in positions where they are responsible for important parts of the robot. So in a pit crew, there's a person for each tire. Every single tire has a dedicated person, or sometimes two people, to concentrate on replacing the tires. And there's a dedicated person to look after the refueling of the car. That's why Formula One race cars are so efficient, is because everyone has a very specific and very focused sort of responsibility on the car. It's not just the person who's driving the car. So for example, when we're doing the robot challenge, we have people who are responsible for doing the code, but then someone else is responsible for turning the code into my blocks. And it's very important that these people are communicating to each other, because the person who's turned code into my blocks has a lot of trust in the person who original coded the robot. So so there's a lot of communication skills that are going on in there. And then there's also someone who will design the robot based on, you know, their real world observations, and also maybe some sort of research that they've done. They say, okay, we should use a gyro sensor in this part of the robot because it is going to be more centrally positioned on the robot. Or maybe they'll say, we need the color sensor to be positioned this way in the robot so that light doesn't interfere with the robot. And then there'll be a separate person who is looking after the actual build of different parts of the robot. So it's important that everybody feels like they have a very crucial part of building this robot. And it is more important that the team is feeling engaged in all aspects of the robot, rather than to sort of have your expert robot designer design the entire robot, for example, because that will make it really fun for the one or two people, but then the rest of the team will lose interest, or they will not feel ownership of this project. So it's more important to make sure that the team is involved, rather than to build the robot with experts. Setting missions as quests. That's another thing that a coach can do to make the robot game more fun, because the robot game can be quite overwhelming. They'll, especially in August when you receive the brief, you might see that, you know, there are so many missions. I don't know which one to do. What the coach or the teacher can do is they can make suggestions and isolate certain parts of the map. You can say, don't worry about these hard missions. We'll concentrate on them later. Let's just focus on this, and set it as a bit of a quest, just like a video game would. Like in a video game, if you jump into World of Warcraft or Dungeons and Dragons or some sort of game, you don't get offered the entire sort of experience and pick out a mission. You get a choice between very few missions, and what you can do as the coach or the educator is to have that insight and make it so that the kids are focused on these quests instead of getting overwhelmed by too many details. Then it's also important to have team discussion and collaboration, of course, like we said before, and to make it so that when we have those different roles, then hopefully it means that your robot can be built in a modular way. So some people can focus on building the robot chassis. Some people can concentrate on building things like attachments or certain sensor positions. Some people can be involved with just the decoration of the robot, making sure it looks cool, so that we can get a crowd reaction on the day of the tournament. So yeah, that's how we can sort of gamify the robot building experience. One of the examples that we have from this season, this last season of Replay, is that we introduced the idea of the big audacious mission. It was about, so the coach and the team would talk about which mission on the map is the most impossible mission to do, right? It's the one that we feel like is like, nah, it's like you design a robot, there's no way you can sort of do this mission. And then we set ourselves a task, a quest, where we say, okay, after we've done all these other important tasks, I want the team to try and do this big audacious mission. This is the mission where we ourselves feel like there's no way we can possibly do, but we'll do it because we feel like this is going to be our personal challenge. This year, it was the mission about the pull-up bar. We thought that this was the most incredible challenge, that there's no possible way that any robot can do it. And we decided that this is the one that our robot was going to do. And it may not even be the part of the scoring strategy. We might even score less points if we attempt this mission. But the reason we did it is because we set it as an audacity mission. It is about making a statement for ourselves to say, yeah, we did the impossible mission. And we want to make it so that when other people see it, us do this mission, we want them to sort of get this kind of awe that we initially had when we were doing the mission. So that's just a mission that we did for ourselves to gamify. For the innovation project, it's probably the most overlooked part of First LEGO League Challenge is the innovation project, because a lot of people focus entirely on the robot. And what we find is that the innovation project can be as hard or as simple as the team makes it. Of course, your team will get rewarded with things like trophies or sorts of champions awards when you do a great innovation project. But sometimes, your team may not be interested in doing much of the innovation project, and that's actually okay. What it means is that as the educator and as the teacher, it is important for you to sort of make it a choice that the kids have made, because they need to know that whatever innovation project that they do, that they present at FLL, it is their choice and what they have come up with. Because the last thing you want is to sort of set them a very amazing innovation project to go and research on and to do, but then the kids have no interest in doing it, because that's not very fun. That's like if you were at school and you get set this assignment that's not due for another 3 months, and you have no interest in doing it, right? So we can apply gamification ideas to make innovation projects more engaging as well. A difficulty setting is something that happens in a lot of video games, because why would people why would developers or designers give you a choice to set the difficulty setting? It's because not all people want to play the game that the designer wants you to play, right? So even though we as coaches know that First LEGO League is about the robot game and also the innovation project, if you find that the innovation project is causing a lot of disinterest in the kids, or a lot of anxiety, then you can set them or allow them to choose what kind of project that they want to do. You can inform them. You can say, hey, we can focus more time on this innovation project and make it really cool, and then you can win all sorts of maybe some sort of recognition later down the track. But hey, if you guys are only concerned about the robot, then I'm not going to be the one who stops you. I can only sort of inform you, because the last thing you want is to sort of be the educator who says that, we need to spend just as much time on the robot as the innovation project, but then they don't want to do that part of the challenge. They just have no interest in it. Then you make it so that they do what they want to do. It's about keeping kids interested in learning. And hopefully, if you can set them a project at an effort level that they can sort of accept, then later on, as they go through this FLL journey, after 1 year, after 2 years, after 3 years, they'll realize, wow, this project, this innovation project, is actually an important part of this experience. A lot of people that we see at different sort of meetups and different sort of videos, they're spending a lot of effort on these innovation projects, and they're really, really cool. Sometimes they're really cooler than the robot that they built. So I think it is important to let kids sort of understand how their choices matter in the team, because it builds their character, and also it keeps them interested in the kind of experience that they want to have as well. I can tell you right now that my first year of FLL, our team spent very little time on the project, and they scored very well in the robot game. But of course, they didn't win any prizes because they didn't realize how important the different parts of FLL were. So I think it's important to sort of give kids the informed choices that they can make, but then let them drive the project, let them drive the experience. The greenhousing is a term that we thought up. It's a no-no environment, so that when someone comes up with a project idea, nobody says no to the idea. We greenhouse it, which means that we keep it in a greenhouse and we keep bouncing ideas around to grow the idea, and then we see which ideas grow to a point where we decide that, yeah, that's something that everybody wants to do as an innovation project. And also scaffolding is another idea that we use to make sure that past progress or past experiences don't get lost. We make sure that kids write a lot of work in journals or in shared folders, and it makes it so that they build on their knowledge, so that a third-year team like we have now is going to be much more experienced and have accumulated a lot more knowledge than one of our sort of rookie teams. And finally, to make their innovation project experience more engaging, make sure you connect them with pros, professionals, right? To get people to talk to people who are in that field of knowledge is very important. For example, we connected with one of our local airports for City Shaper last year, and we sent our kids to have a look at what they do behind the scenes when they're doing running an airport, and also here's a picture of one of our teams just checking out one of our local scaffold hire places, just learning about how cranes work for City Shaper. So we find that as a teacher and as an education provider, a lot of local businesses want to be involved with your teams as they're going through this learning journey. So definitely reach out to as many professionals as you can, and make sure you get your kids to engage with them, so that makes their experience very memorable. And finally, we have our core values. So it's for us, core values is an overarching theme across both the robot design and the robot game, and also the innovation project. It's about making sure that we have ideas for side quests all the time, right? So yeah, sure, we're going to make this robot really good, and we're going to do a bit of a presentation, but what are these sort of side quests? What are things that we can do as a team together to learn that is nothing to do with what is like traditionally scored in First Lego League? Well, it's about identifying different sort of learning experiences, and identifying team building experiences as well, and also making things fun and lighthearted, making sure that there's plenty of opportunity for people to get together after school to design a poster together, or design some slides together, or learn something new together. Maybe some people haven't put slides together for PowerPoint before, and then you sort of say, okay, let's have a session where we'll just learn how to use PowerPoint, or let's design a session where we're going to just eat pizza and watch a very educational documentary or something like that. And these opportunities build up the core values of the kids by making sure everybody feels included in the activities that they like to do, making sure that we encourage teamwork and team building, increasing fun, and making sure everybody can do things that are fun outside of just the robot in the project. For example, we had a lot of restrictions with COVID this year, so our kids learned how to use camera equipment, how to use some really dedicated sort of broadcast equipment by borrowing bits and pieces from different parents and families. They wanted to make their Zoom calls and their Zoom meetings more interesting. So this was like a whole period of time was spent for just the kids together, learning how to use different sort of media equipment. And that turned out to be a really, really fun exercise, and it really transformed how presentations sort of worked with them throughout the season. And that's really it from me. I hope I provided a lot of things that you can think about, and some insight into gamification and how we can apply it into First Lego League. Yeah, if you have any questions, then feel free to contact me.
Oh, look, thank you very much, Gary. That was a fantastic presentation. You talked about FLL, and I believe that's a fantastic learning opportunity, and it's just some of the modern ways that we can teach STEM that you're talking about, and obviously all the content on gamification. Very interesting indeed. We actually do have some questions for you from the YouTube chat. So first up, you've effectively provided a detailed, structured approach for learning complex tasks. Do you find that this approach is particularly effective for teaching children with special needs?
I think it's important that people, that kids with special needs, it's important to talk to their families first. I find that we do have a few children who may have special needs, and talking to their parents about what works for their kids, what are some sort of learning patterns that they found have worked is really important. And we find that planning especially for the kids with special needs is very important as well. So of course, like all kind of learning plans, there's no one size fits all, but it might get a lot of insight by talking to the families of those children beforehand, and that will hopefully inform you in terms of what kind of content you can design for the kids in each session.
Okay, so the bottom line, everyone's different, and different people work with different things, and catering to different people. That's awesome. Yeah. So you mentioned that teamwork is an important part of gamification, and that particularly relates to FLL. What achievements or rewards have you utilized to encourage good teamwork in your team?
Absolutely. So what we like to do is that we don't reward just for completing tasks in FLL. So what we do is we have a lot of badges and stickers that we love to give out. We have a very, very popular one is the communicator badge. I don't think we have any around here, but these badges that we have like a big stack of, they're very exclusive because we only give them to kids who participate in FLL teams for a certain period of time. So for their second year, and for the first time that they do a presentation, they get their communicator badge. It is quite a hard badge to get because you need to be doing the second year, and also you've done a presentation, which we feel is very important. So when you think about these achievements that people can do at a very sort of reasonable sort of cost, stickers and badges is probably one of those ones that the kids really, really like at this age group. For the older kids, we might want to give them certain cool roles, right? We give every kid in our team a very unique role. So I remember one of them was the core values astronaut. So the core values astronaut is in charge of making sure that all the core values activities are going to be funds and fit into people's sort of school schedule. So this person has a very specific role, and then there's all sorts of really fun, like engineering ninjas and all sorts of like there's project manager ones as well, so that everybody feels like, man, I have a very unique role in the team and nobody can really replace what I do. So making sure that people have cool sounding and also really fun sort of roles is very good for giving rewards. Another kind of reward can be giving people messages on their parents groups as well. So sometimes when we have a first Lego League sort of a season, their mums and dads will sort of get together into a parents group just so that we can sort of share information about their kids. And that's also a place where you can sort of take photos of the kids with their permission and then sort of say, hey, this is just a cool picture of your kids doing a specific challenge and overcoming a specific learning opportunity, learning sort of challenge. And it's something that they can sort of take as a memory of their first Lego League season. Because if the coach is not there to sort of record these memories, then it sort of just lies in those engineering notebooks. And so it's rewarding for the kids when they sort of get these photos or these pictures of the kind of work that they're doing along that journey as well.
That's fantastic. I love that you're taking the whole concept of gamification and applying it to, I guess, a positive learning environment, because badges and stickers and roles, in the same effect, that's almost like playing a video game where you get different titles, different roles for playing for a certain amount of time, maybe getting to a certain achievement. But for using that in FLO, that's actually really powerful. That's fantastic. I love that. Relating to our last speaker that we had, she was a biomedical engineer. Have you ever considered developing games for the purpose of healthcare, such as maybe reflex training as part of a rehabilitation program, for example?
Well, I think that's definitely something that is really close to me, because I do like to spend a lot of time sort of developing engaging experiences for kids. Things like the auditory learning software is something for kids with sort of auditory disorders. So I think to make any kind of rehabilitation program more fun is going to be the benefit of everybody, whether it's sort of musculoskeletal rehabilitation programs or psychological kind of rehabilitation programs. Anything that can sort of be more fun to maintain people's focus and consistency is definitely a good thing. And I think, yeah, in the medical environment, it's definitely a high priority.
That's fantastic. Actually, one of the other questions we've got, which I think is quite interesting, we've obviously been talking a lot about these techniques with children, but have you applied the gamification teaching method when you're teaching adults? And does it differ in effectiveness with the adults and the children, or is it sort of work both ways, or how does that look?
I think that's an excellent question. And I think that adults need fun just as much as kids do. I think sometimes we forget that in the workplace as well. And it is a pity that what I find really interesting about that is that when you are in school or when you're a junior working like in your first job, you get a lot of feedback. You get told how well you're doing, how badly you're doing all the time. But then you reach a point in your career where it stops or it tapers off, where you are a senior or a middle sort of manager sort of role, and the feedback stops coming. And I think it's not necessarily a good thing. I think that getting feedback is a reward no matter at what sort of level you are at. So when I do sort of like when I was developing video games and I was looking after like a game development team, I tried to make sure that the senior developers still get as much feedback as the junior developers, because it's really, really easy to give feedback to the younger people than it is to people who are your equals or your co-workers. in a workplace environment, sometimes you might have a lot of negative connotations to receiving feedback, but it really shouldn't be, because feedback is a reward to be able to constantly know how well or how unwell you're doing. Is important as a learning experience and as a character building experience, and also for your career development experience. So yeah, I think adults need fun just as much as kids do, and I think a lot of newer sort of project management software, things like Trello, like Jira, Clarizen, all sorts of kind of like corporate communication software has a lot of game mechanics built in now. A lot of things like badges, emoticons that people can unlock. You're seeing awesome little like ticks and like green check boxes when you complete a task. These little things, they seem small, but they are little reward mechanics that people have started integrating from video games. So yeah, I think adults do require the gamification mechanics as well.
Okay. Sort of, I guess, still on the topic of the game development side of things, with regard to teaching, have you ever used virtual reality gaming as a tool for teaching, and did you find it effective?
Not as a tool for teaching, but I do think that technology has really progressed really rapidly, and now more than ever, I think the demand for virtual reality has grown. Now that people are more spread out, and the need for people to understand things spatially in 3 dimensions is very important. So I think virtual reality would be definitely beneficial. I think I did do like an augmented reality sort of game, but it was like it was like for the AFL. I remember it was a really fun experience, just because for people who aren't able to sort of get up and walk around, to be able to sort of play, like learn how to sort of pass a ball by flicking their phone and sort of see the ball fly into the distance using augmented reality. That's kind of a rewarding kind of experience, and it sort of gets people to visualize that kind of environment. So definitely virtual reality is another milestone for education.
Fantastic. Pushing the boundaries of technologies, I guess. With the achievement-focused approach of learning that we've been describing, do you reckon there's any risk involved that possibly earning achievements for poor practices could reinforce poor practices?
I think it's important to sort of to understand that how achievements are sort of used in a learning experience is not so much that it is something that you're displaying on your profile, right? Achievement is recognition and feedback. It is when you are, if you, for example, have not turned up to class for 2 or 3 weeks, it is not an achievement per se to sort of go up to the student or the parents and talk about, hey, we're just concerned that this is happening, because it's more recognition rather than sort of an achievement. And the way that games do it for like poor kind of performance is tongue-in-cheek, right? It is saying, hey, we just noticed that you lost against this boss for 3 times, and it's silly. It's a video game. But for learning, it's not so much about displaying your achievement. It's about the fact that your teacher has recognized that something has possibly sort of been disrupted in your experience, and that your educator or your coach is concerned about that. And we're recognizing that. That doesn't have to be like an achievement that the kids sort of display. It's more that, it's an aside thing that you would say to the child or to their parents and say, hey, we just noticed that that he hasn't been paying attention. He's fallen asleep a couple of times in class. Is there something that I can do to change my lessons? Is there something that I can do to make it more engaging for your child. So it is about making sure that the kids know that they are being looked after, they're being cared for, making sure families know that you are looking after their kids as well by paying attention. Because what you don't want is to have, the kids constantly sleeping through class or being very distracted in class, and then not telling them or not recognizing it, not sort of bringing it up in conversation until right at the very end when they sort of say, hey, actually, I haven't been sort of listening for the last 3 months. So it is, so when I say using achievements, it is more about recognition and understanding feedback. And obviously it means that we have to be very sensitive to the way that negative kind of performances are sort of handled. It is important that that we are very sensitive to that. Yeah, absolutely.
Fantastic. I have one more very important question for you. So the famine game you talked about, does that imply that when I go home and my mum complains to me that I'm playing Fortnite instead of eating dinner, can I just say that I'm honouring a proud and noble ancient tradition?
I think you'll probably get in trouble because you're wasting food. But then I think it is definitely a history that we can probably still learn from. It is I think it's something that can be brought up in more conversations. But definitely finish your dinner. Don't upset your mum. I think that would be my tip.
Okay. We're very jealous that you got to meet Dr. Michio Kaku, actually. What was he like in person?
Oh, mate, he was very awesome speaker. It was really, really cool. I was only there just briefly with him to after he spoke, just to take that photograph. But I wish I could say more. But yes, if Michio Kaku is watching, I would love to sit down and talk to him sometime.
Oh, fantastic. Look, thank you very much, Gary, for sharing everything you've shared today. Fantastic. Gamification, how we can use that in education with FLL. Absolutely fantastic. I'd like to wish you a great night. Thank you very much.
Thank you very much, Caleb. Thanks for having me, everyone.
Oh, no worries. It's our pleasure. 24 Hours of STEM would like to give a big thank you to our sponsors, Boeing, Google, and Macquarie University. We've heard from some amazing guest speakers, and now we would like to introduce our next guest speaker coming to us from Tucker Tucker Plastics. That is Paige Balcom. How are you?
Good. How are you?
Very good. Very good indeed. All right. Fantastic. Thank you for joining us today.
Sure.
All right.
Should I start sharing my screen?
You're more than welcome to start sharing your screen. Yeah.
Right.
So we've got a bit of a presentation for us.
Yes.
Oh, fantastic. We can't wait to hear it.
All right.
All right. Beautiful.
It's fun to
Do it.
I need to come and speak. I did FLL and a little bit of FRC when I was back when I was younger. So it's fun to be able to connect back with everyone.
Oh, fantastic. We're so glad you're here. All right. Well, we can see your slides and we can hear you. So you're ready to go whenever you're ready.
Great. Are you seeing the pictures on the side, or can you see the whole screen?
So I see the presentation full screen.
Okay, great. So yeah, I just wanted to share a little bit about Tucker Tucker Plastics, which is a social enterprise that I started this year. So I'm a PhD student at UC Berkeley in America, studying chemical engineering and environmental development engineering. And so for my research, I started researching plastic waste in Uganda because I had been working in Uganda before grad school. And I really wanted to continue working in Uganda. So I asked my advisor if I could change my research project to something in Uganda, and thankfully he said yes. So yeah, I was able to start researching plastic waste and realized what a big problem it was in Uganda and developing countries. So after a few years of research, I wanted to do more than just academic research and publishing papers. I wanted to actually make an impact in people's lives. And my friends here in Gulu, Uganda. So I co-founded Taka Taka Plastics. And Taka Taka means waste in Swahili. And so we're a social enterprise that locally recycles plastic waste into saleable products and creates jobs for vulnerable youth. So this is a picture of a very common site in Uganda. This is the dump site outside of Gulu, the town where we work. So a lot of the plastic waste and just waste in general doesn't get collected, but the waste that is collected gets dumped here and then burned. So in my research, I tried to zero in on what is the core problems behind plastic waste, because we know, I mean, all this waste is like burning it is really bad. It's terrible for the environment and also for people's health. But the core issues are deeper than just waste that's littered and burned. So the big problem that I found is the issue, I call it waste sinks. It's like a town where plastic gets in, but it never gets back out. So it's stuck in this waste sink. And so for instance, Gulu up in northern Uganda is like 6 hours drive from Kampala. Kampala is the capital of Uganda. And so the only recycling plants are in Kampala. So transporting low value plastic waste 6 hours is just not economical or even environmentally conscious. So the plastic is stuck in Gulu, where it's burned, which of course releases carcinogens and toxins and greenhouse gases, and it's terrible for the environment, people's health, or a lot of it is just littered anyhow, and it ends up blocking drains, and which causes flooding and breeding grounds for malaria-bearing mosquitoes. A lot of the plastic also gets into soil, and then it disrupts crops, and it can even be ingested by animals. Actually, a lot of cows and other animals die from eating plastic waste. Yeah. And then in Uganda specifically, the other big challenge is PET, which is a type of plastic that water bottles and soda bottles are made out of. So this is a big problem in Uganda because it's one of the most common forms of plastic waste. But there's no solution in Uganda to recycle it. It used to be that the recycling plants in Kampala could shred it into small flakes and then export it to China, where it would be recycled into like new bottles or carpets. But in 2018, China put a ban on importing plastic waste. It has to be like 99.9% pure, very high quality plastics. And Uganda recycling plants can't achieve that level of purity with their flakes. So Uganda is stuck. There's nowhere for them to send the bottle flakes now. So yeah, when I was talking with the government officials, they said that they're really stuck and desperate. They have no solution for the PET. Yeah, because China is no longer, and other like India, other countries that used to be taking the plastic waste is no longer accepting the plastic waste. They send it back. So we developed a solution to locally transform plastic waste into construction materials. And so this brings environmental and community health benefits, as well as creates local jobs and closes the loop in the circular economy. So the technology we developed is a modern polymer processing equipment fabricated locally here in Uganda. So it's much cheaper than importing, and it's a lot easier to maintain and repair, and it is much easier to scale. Like if we want to set up locations in other places across Uganda, since we can build the machines locally, it's much easier to scale than if we were to import machines. So the process is first, we collect the plastic waste. This is a picture of our recycling bins. We made it in such a way that it catches people's attention and really encourages them to recycle, because it's not a concept that people in Uganda are familiar with. So when they see this bin made of bottles, it like reminds them that, oh, you put your bottles here. And people like it a lot. Actually, we have it in a bunch of hotels and restaurants around town. And yeah, people put their bottles there. And then we go and collect the bottles and bring them to our production facility, where we shred it into very small flakes, and then we melt the plastics safely. Of course, we know that if the plastics they have you have to identify what kind of
Hey, Paige, we're cutting out there a little bit. What's the internet like on your end? Can you hear us at the moment?
take the melted plastic.
No. Technical difficulties. Fantastic. Sorry, can you hear us? Okay, so you can never have a live stream that works 100% of the time. I reckon you're back in. Paige, can you hear us? Sorry, now the mic's muted. There we go. Awesome. Free to continue with the presentation. So, oh wait, you're gone again. Okay, maybe not. Okay, this is fantastic. The joy of live streams. The joy of live streams, everybody. It's absolutely incredible. Oh, I can hear you. Oh, we back in? Maybe.
Yep.
Wonderful.
Sorry, I think my internet is a little unstable.
No, that's completely fine. You're all good to go. Thank you for that.
Thanks. So yeah, and then we focus on construction materials because, first of all, there's a big market for it in Uganda. Like, since Uganda is developing, there's a lot of construction going on. It's a $3 billion market in Uganda, growing 10% annually, and there's a huge need for additional housing and buildings. Gulu in particular is growing because it was just named a city this year. So there's a lot of development and building going on. And also construction materials allow us to use a lot of plastic waste, which solves the magnitude of the problem. Whereas if we were making just like small tourist trinkets or something, then you wouldn't be able to use all the plastic waste that we can collect. But construction materials can really address the scale of the problem. Yeah, so these are some of our products that we're making right now. These are coasters, like for putting underneath drinks or even on top of drinks.
I reckon we've cut back out again. Fantastic. Again, the joy of internet. Internet's fantastic. It works most of the time, but when you need it to work, it doesn't. You back?
Yep. Can you hear
Wonderful.
me now?
Yes.
Okay.
Thank you. Continue.
So yeah, we figured out a way to solve the problem with PET. So these wall tiles on the right, these are actually made completely from the bottles. So yeah, the problem with PET is the chemical structure of PET is very difficult to work with. Like normally when you melt PET, it becomes very brittle, like anything just breaks because a bunch of different chemical properties makes it difficult to melt. But we figured out a way to solve that problem, like change the chemical structure of the PET a little bit, and we're able to make strong wall tiles. So that was really exciting. The first day that we made those prototypes was really awesome. Yeah, a little bit about us. So yeah, I'm Paige Balcom. My co-founder is Peter Akwoko. He was a former lecturer at the university and also just a community activist. He really cares a lot about his community and especially former street youth. And he has started a lot of initiatives to try to help them. Currently, we have actually 12 full-time employees. At our peak, we had 16. We have 3 full-time engineers, and then most of our production staff is former street youth. But then, so we started in January of this year, but then of course COVID hit. So in March, we looked at ourselves and were like, oh, well, what are we going to do how can we help our community? So we heard about the lack of personal protective equipment in the hospitals. We were like helping to deliver food to people in the isolation ward at the local hospital, and the doctors didn't have face shields or enough protective equipment. So we realized, oh, face shields, those are made from plastic, and that's what Taka Taka Plastics does. Maybe we can do something here. So we started prototyping just like whatever scraps we had around the workshop, and made our first face shield prototype and took it to a clinic and got feedback from nurses. And so we did that many times, like over 2-3 weeks, we iterated different designs and prototypes until finally we were able to get a good design of a face shield that the nurses really felt comfortable with. And they were super happy. They loved them a lot. One doctor, he heard about us on the news, and then he called us. He's like, please, can you send some face shields to our isolation unit here in the hospital? We don't have any face shields. And we're working with COVID-19 patients. And so we're like, yeah, sure, we'll bring some this afternoon. He's like, no, I need them now. And so he sent someone to our office and went and picked them up. So yeah, we've been able to distribute more than 10,000 face shields across Uganda in 27 different districts. And yeah, we've been mostly focusing on hospitals, but also first responders like police. And now we're also starting to go into schools as schools are starting to open up in Uganda. Yep, and that's our team. It's been really awesome to be able to work with the former street youth, because yeah, she's been able to make a really big impact in their lives. And at first people were like, oh, you can't trust them to run the machines, like they thought that we were just gonna work with them to collect the plastics, not actually to run the production line. But we wanted to give them that chance, and they do an amazing job. Like it was a little tough at first, the first 2 weeks when they were learning how to do it. Training them was a little bit tricky for them to learn, but once they got it, they're amazing and do a really great job. And yeah, it's really changed people's lives. Taka Taka. There are some quotes from some of our staff. For the engineers, it's actually really hard to get an engineering job in Uganda. And even if it is an engineering job, it's kind of more just like overseeing a manufacturing line. So it's really exciting. I love working with our young engineers. I learn a lot from them every day. But for them, it's also really fun to be able to like design something from the very conception all the way through, and really be able to design new machines and design new products. And that kind of engineering doesn't happen so much in Uganda. Yeah, and then for the former street youth, it's really been able to change their lives as well as their families' lives, and been able to start small businesses on the side and been able to help provide and support their family, and even been like reunited with some of their families back home. Yeah, and the other portion of Taka Taka is also education and trying to raise awareness in the community about recycling and plastic waste and the dangers of burning plastic, because most people just burn their waste outside their homes. So Peter, my co-founder, he's really creative and coming up with ideas of how to help change people's mindsets about plastic waste. And so we made this collection bin in the shape of an elephant, because elephants are the traditional symbol for the Acholi, for the tribe where we are here in Uganda. And so yeah, when people like see an elephant, they get really excited about that. We also showed earlier the picture of the bins at the different restaurants, and yeah, how they're made from bottles. And so it just reminds people and like encourages them to put their bottles there. We also, before COVID, we haven't been able to do it recently, but before COVID, we were doing monthly First Friday community cleanups. And so we started with the main market, and then other months we did other places around town, where we would just invite all members of the community to come and help us in cleaning up a section of town. There's like picking up waste, and it was really amazing just to see how many people joined in and how it just grew every time. This was some of the people at the second cleanup. There was even a lot more than that before the picture was taken. And yeah, just really trying to help change people's mindsets and see like the dangers of burning. The plastic is really dangerous to their health, and just encouraging them to like really want to care for their environment and the place that they live in. So as I said, we started in January, and our goal is to be able to launch a full pilot here in Gulu. We hope to recycle 9 tons of plastic per month. That's about half of the bottles here in Gulu, is what we estimate. That would save more than 20 tons of CO2 per month and create more than 35 local jobs, mostly for the former street development production team. And so COVID has delayed that plan a little bit, but we're starting to get back on track. Uganda is opening up now. And so we hope to have the Gulu pilot fully launched by the end of next year. And then once we prove that the Gulu pilot can be self-sustainable and profitable, then we'd be able to scale and set up locations across Uganda and set up other Taka Takas. Yeah, so that's where we're headed. Yeah, thanks so much for giving me this time to present and can help answer any questions.
Oh, no worries. Thank you very much for being here. It was an absolute pleasure to have you. We actually do have some questions. So I guess the first one we might start at is, so what actually made you decide to start Taka Taka Plastics, and how did this issue come to your attention in the first place?
Yeah. Well, before grad school, I was working in Uganda. I was on a research grant for like 1 year. And so I was living in a village at this vocational school for child mothers. And yeah, it just really changed, like just hearing their stories. So half of them were refugees from South Sudan, and then half of them are uh, from here in northern Uganda. And northern Uganda recently suffered from a civil war, and for a very long time. So a lot of trauma and just has happened and really affected the people here. So just hearing their stories really touched my heart. And yeah, I just fell in love with the culture and the people, and really felt like I was called to try to use the skills that I've been given and the resources that I was blessed with being born in America, and try to use that to be able to help my friends in Uganda. So when the grant ended, I had to go to grad school because they had only deferred my scholarship for a year. But yeah, I was really sad to leave Uganda and really wanted to come back. So yeah, I convinced my professor to let me do a research project in Uganda, and then talk with friends. And yeah, the issue of plastic waste was really a big problem. So then I was able to start researching when I was still back in Berkeley. I started just like reading as much as I could about plastic waste in Uganda and developing countries, and talking to people involved with it. And then I was able to enter an entrepreneurship competition at Berkeley with an idea to help solve the plastic waste problem. And yeah, we were able to win the entrepreneurship competition and get some funding. And that let me go back to Uganda for the summer and do field work research on the ground. And that's when I met Peter. He was lecturing at the university because I was working with the university engineering department. And yeah, it still took like 2-3 more years. But yeah, as I did more research, we started like narrowing down on those two problems of the waste sinks and the PET as the main problems, and coming up with ideas for solutions for that. And then we realized that, yeah, me and Peter, we had a lot of the same ideas, a lot of the same goals of using engineering and technology and business models and entrepreneurship to be able to create jobs and make an impact in the community. So yeah, we decided to start Taka Taka Plastics, and we wrote a grant proposal and thankfully we won and got some money to start. And then it's just been a crazy ride since then.
That's awesome. So if you were to stop driving Taka Taka in Uganda, do you expect that the local community would be able to take over and continue the recycling practices that have been implemented at the moment?
Yeah, I think so. Well, okay, if we stop Taka Taka, then there's no way for the plastic to be recycled. So no, I don't think so actually.
So they end up back in those the pits again, which is obviously not what you want for. Yeah. Okay. Well, how does the cost of the recycling process that you've developed over in Uganda compare to the cost of the processes utilized in Western countries?
Yeah, so the recycling in Uganda is very different from recycling in Western countries because, well, for a lot of reasons, like in the US and probably Australia, waste is separated at the source. So like we put the plastic separate from the rest of the waste. So it's already easier to recycle. The recyclers though, they just have to separate the plastics into the different kinds, because there's like the numbers on the plastic show like if it's HDPE, LDPE, PET, PVC, like different numbers, which all have to be recycled differently. And so you do have to do the sorting of that. But yeah, in Western nations, it's just there's much more infrastructure to facilitate that recycling. And they have the technology. It's difficult now for smaller towns to actually do recycling since the China ban. Actually, like in the US, a lot of the plastic waste in the US was shipped to China, and now the US is still scrambling, still trying to figure out what they can do with their own waste. So a lot of the plastic in the US is actually being landfilled right now. But the bigger cities are able to invest in the technology to be able to actually recycle it in the US. But the technology is very expensive, and it has to be like very, very large scale. It's like millions and millions of dollars to be able to get the equipment to properly recycle plastic waste in the US. Then in Uganda, there's not that infrastructure set up to be able to collect the waste, and like the technology to recycle it doesn't exist, which is why we started Taka Taka. And also the mindsets are different too. Like in the US, people are like, they understand the concept of recycling and like why it's important to protect the environment. And whereas in Uganda, people haven't been very much exposed to that yet. It's starting to change. Like in the last few years, people are starting to talk about it more and appreciate it a lot more in towns and cities, not so much in the villages. But it's also unique, like even in the villages, there's actually not that much plastic waste, because at least for bottles. Other types of plastic, yes, but the bottles, people will find unique ways to reuse them in their own daily lives. So it's cool to see how people are ingenious and using them for different things. But yeah, for the cost, like one of the recycling machines that we build here in Uganda is 85% of the cost of if we were to import a similar machine. So it's much cheaper for us to do it here. Like if we can design, it's difficult to design the machine with the local materials and the local fabrication techniques, because Uganda doesn't have like CNC lasers. We don't have that, and like milling machines are very difficult to find. So we don't have the same tools to be able to build machines. But yeah, working with our engineers here, we try to figure out ways to make it locally, and then yeah, it's much cheaper than if we're importing. And also too, like with the mindsets, we can actually use like what can be seen in Uganda as like almost like a weakness, like poverty, and how people like are not able to make very much money. We can actually use that as a strength to help change mindsets that you can't do in the US. Like if we pay someone like 300 shillings for a kilogram of plastic, it's like 8 cents. And so like in the US, like no one would recycle plastic for 8 cents for a kilogram. So that doesn't have an incentive in the US. Whereas here, that really matters to some people. And so by just giving like a small amount of money, it's actually enough money that it's meaningful and worth something to people in Uganda. So it's actually, you can use that to help change mindsets quickly.
Okay. So from what I understand about the recycling of plastic, sorry, and correct me if I'm wrong, it is a really large economic issue. So from what I've heard, plastic can be categorized based on its value, in a sense that this plastic bottle I've got right here is probably quite value, and we actually have in South Australia at least, we have a 10-cent container deposit scheme. So if I were to start up a recycling company here, recycling bottles then I'd be off to the races making money. But this kind of plastic over here, like your bags and maybe the stuff you get at the supermarket, those really clingy, I'm pretty sure they're banned in a lot of places, but those really clingy, nasty bags that you can only really use once and you can't do anything with, they cost a lot to recycle, and so that's why they end up in pits. So your group primarily works on these kind of plastics, the bottles?
Yeah, we can also do hard plastics like HDPE and PP, which is like basins, like jerry cans, like chairs, tables, like buckets, like hard plastics. That's actually really good plastic and really easy to work with, much easier than the bottles. So we can also do that one. And we've experimented with some things with the thin films, like the bags. And we can do some stuff with that. Like you can actually like press them and make bags from them. They're really good for making pavers, like bricks. Like if you mix them with sand, you can make bricks from the bags. But that's, it's difficult to like get the bags clean and to melt the sand, the plastic together takes a lot of energy, so it's expensive, and then the bricks are not worth that much because people here make clay bricks locally that are very cheap, so it's the profit margins are not as high on the bricks as compared to the tiles. But yeah, so for now we're focusing on the bottles, the PET, because that's the biggest problem in Uganda. But eventually, we hope to get into the bags and work on more scalable solutions for that as well.
Okay, fantastic. So you would say the best, I guess the best thing to do with the softer plastics, the bags and that, you would probably advocate bans in some areas because of the difficulty in recycling and obviously ending up in waste?
Yeah, banning plastic and reducing single-use plastics is definitely a big step in trying to solve a plastic waste problem.
Okay, fantastic. So do you have plans, obviously we're based in Uganda at the moment, do you have plans to expand this operation to other countries that have similar hurdles in preventing the recycling of plastics?
Yeah, we really want to. Once we prove that this Gulu pilot can work, then we hope to expand to other towns across Uganda and even other countries. We've been getting a lot of interest. People like ask us a lot to come to their country. And because our machines are designed to be locally made with basic fabrication techniques, then it's much easier to make it in that location and to be able to start in a new place.
All right, fantastic. So how far do you see the project progressing in the future?
Wow.
I mean, I guess predicting the future is obviously not a possible thing, but I guess forecasting and planning and what you've got in mind.
Our goal in the next 5 years, we hope to be in 5 locations in the next 5 years, and then we'll expand from there, go across the world.
Sure, why not? So you mentioned scalability and potentially like starting more locations in Uganda and I suppose out as well. So do you plan to get more grad students involved or maybe setting up a program of international volunteers, sort of like an Engineers Without Borders thing going on around the world for that?
Yeah, we actually work with a lot of students with the local university here, Purdue University, as well as Berkeley, and we've even worked with students from Stanford, Harvard, Grove City. We work with a lot of students on small projects. Like even this week, 3 of the engineering students at the university here, they presented their final year projects. So like their senior capstone projects. We worked with them and they did it for Taka Plastics. So they designed like a washer and a sorting line and filtration system for wastewater. And so yeah, it's been really cool to work with the students and be able to give them opportunities to work with our experienced engineers, learn them, but also just give the students real problem engineering applications that they can work on that also help Taka Taka move forward to the next level.
Fantastic. Would you say there's any ways that people, just like anyone, can contribute to the project at the moment?
Yeah, we're connected to a nonprofit in the US. So if you feel like you want to help financially, we welcome donations. It helps a lot with getting started, as we're still a young startup. Getting funds helps us towards launching our full pilot in Gulu, as well as help with the education efforts of change mindsets about plastic waste in Gulu. And if you're interested in coming to help, basically, we welcome volunteers as well. Actually, we have a volunteer now, one of my friends that I went to university with. She's here for like 6 months volunteering, and it's been super great to have her and be able to how all of her skills are contributing and helping Taka Taka.
Fantastic. We're just wondering, were there any other alternatives considered, such as importing the manufacturing equipment, even though that's more expensive, to build the processing equipment from local materials and labor, but with the imported Western manufacturing methods?
Come again? Sorry, I'm not sure I get your question.
Oh, that's completely understandable. So sort of taking in equipment, importing equipment to manufacture the equipment that does the production work.
Like importing like laser cutters and CNC machines and that stuff.
Exactly.
Yeah, like is it possible or is it difficult or
like was that considered? Yeah, is it difficult? Would that be a consideration?
Yeah, it's possible, but it's difficult. I mean, international transportation is kind of expensive, and then Uganda has high import taxes as well. So anything that's imported is like 25% or more taxed. And then do you even have the technical capability of running the machine, or do you have trained technicians? Like milling machines, like there's very few people in Uganda who have been trained in operating a milling machine. Lathes are there, but getting good cutting tools is hard. Like a lot of the machines are old machines, and then they can break, and like getting parts to replace them is very difficult. It takes a long time and it's expensive. And like getting cutting tools, a lot of the cutting tools are very old. Then power is often a very big problem. Power goes out regularly. So using like a lot of the machining capabilities that we take for granted in the US or Australia is very difficult in Uganda. But people are also very ingenious in figuring out. Like I'm always amazed about how the machinists and like the technicians in Uganda figure out ways of doing things like machining a gear on a lathe. Like they can do that, and it's like but the biggest there's like a lot of welders, like welding and like fabrication with welding, and there's like basic cutting discs and grinders. It's like the most common in Uganda.
Okay. Wondering, have you considered utilizing local first teams to assist with the project?
There's no first teams in Uganda.
No first teams in Uganda. First Global, I believe, has some teams in Uganda.
Really?
I think that might be a newer initiative. 2017, I think that was started up, First Global. Yeah. That's all right. It's kind of cool. Expanding. Everyone's expanding. No, that's very cool. Just looking at the photo on your slideshow there, on the back of that gentleman's shirt, I see www.takatakaplastics.com. Would that be a website you recommend people to visit if they want some more information?
Yeah, please do check out our website, our Facebook page. You can learn more about us.
Fantastic. Stay up to date with everything. All right. Would you have anything else that you'd like to discuss with us today?
Yeah, I just really encourage students and people that technology and business models can really make an impact. Like if you combine like engineering, I think can really solve a lot of problems in the world, not just like technical problems or even like development or like public health problems, but even social problems. Like when you can combine engineering and an engineering idea with a strong business model, it like making jobs is the best help that you can give someone. And because not only does it let them provide for themselves and provide for their families, like it gives them that pride in being able to be responsible for themselves, gives them pride like back in the community, but also just having the job is a really key part in the trauma healing process. Like as I mentioned, like a lot of the people in northern Uganda have suffered a lot of trauma because of the war, and even like a lot of these former street youth have been influenced by the war and the after effects a lot. So, but just like going through a trauma counseling program isn't enough. Like having that job and like having a purpose to come to work every day and like being in the community that's around you is a very important part in that trauma healing process. So yeah, I just really encourage people to think of ways that they can use their passion and their skills for engineering to be able to help others and really be able to make a difference in the world.
Fantastic. That is a really, really powerful message to end on. That's absolutely incredible. Well, may I ask, what time is it over where you are?
It's coming to 2 p.m. So.
2 p.m. Oh, 2 p.m. That's kind of acceptable. The last one of our last guests was quite late at night, more like 2 a.m. So we're pretty happy to say, yeah, good night. But no, thank you very much for sharing. I mean, what a fantastic project you've got over there in Uganda. Absolutely making a difference. It's incredible. Best of luck with that for the future. And thank you for taking the time to join us and share some of your stories and inspiration to just people around the world. It's absolutely been incredible to have you. Thank you very much.
Yeah, thanks for the invitation. Thanks for listening.
Oh, no worries. Thank you for sharing. You enjoy the rest of your day.
All right, you too.
See you later.
Bye.
All right. So 24 hours of STEM. Oh, I've only been on for less than 3 hours and I've honestly learned a lot. So many messages about engineering. It's just, how many possibilities are there? It's absolutely incredible. If you like medicine, if you like anything to do with biology, how bodies work, biomedical engineering, there you go. Get that going. Our wonderful guest, our first guest, talked about that. How many possibilities are there? My mind is blown by that. If you want to make a social change in places around the world, well, there's heaps of projects that not only get involved in, but start. It's clear that we need many STEM leaders in the future. And so if this is a message to anyone, if STEM is something that's interesting to you, absolutely jump on board that passion. I've actually got a little bit of time, so I'd love to really quickly go through the 24 hours of STEM challenge that we have. So the 2020 challenge is to find sustainable energy sources. So that's a problem. That is a STEM problem right there. We just heard about waste, and now we can hear about energy. So this could be anything, any new energy source. Maybe we're thinking about solar, wind, geothermal, or it could be about coming up with ways to reduce consumption. I've heard of great projects to do with different automobile things, getting less energy, driving less, and coming up with solutions. It's almost like a little FLL challenge. And wait till you hear what the prize is. So the entry is open to anybody at any level, be it a Duplo model, it might be a crayon drawing or a cardboard prototype, it might be a CAD model, or literally anything else you can think of. The sky and your imagination are your only limits. So the challenge is going to be split up into 4 divisions. So science, technology, engineering, and maths. Rather convenient. That is the 24 hours of STEM after all. And your team can submit 1 entry per division. Your entry can be anything across the STEM spectrum. And I'll give you some examples. So if you're going for the science division, maybe you could do an experiment regarding sustainable energy. Maybe get a little solar panel out and measure the different energy that's producing. That's a cool idea. Could create a tech-based art illustration to show how a sustainable energy source works. That's going to be going into the technology division. What a fantastic idea. Obviously, a big thing of STEM these days is outreach. As a new rookie FTC team, sorry, I've been confused all day. FTC, FRC, got FLL, so it's a fantastic spectrum of programs. But as a rookie FTC team, the Paladins of St. Paul's, that's team 18003. Head to our website if you would like more information. That's paladins18003.org.au. Sorry, got to get the word out there. Absolutely got to get the word out there. And yeah, so jumping board this challenge is absolutely fantastic. And the prize for 4 teams is a Lego Mindstorms EV3 kit. You could think of that as an early Christmas present. Actually, no. It's a global challenge shipping. Probably not going to get it as an early Christmas present. I can't make any promises about that whatsoever. But hey, it's a Lego Mindstorms kit. Absolutely worth the wait. To enter the challenge, all you need to do is post a photo or video, as well as the description to Instagram or Facebook. You need to tag at 24 hours of STEM. That's 24 hours of STEM, and use the hashtag 24 hours of STEM. Sorry, hashtag 24 hours of, and then the division you're entering. So maybe it's hashtag 24 hours of energy, hashtag 24 hours of science. You get the idea. Absolutely fantastic. Alternatively, you can go online to the 24 Hours of STEM website and click the under the challenge, click submit. So we're going to leave you there for now. Thank you very much for joining us. What we can do this stream, the second Mentors Without Borders stream, is going to come to a close. Oh, but you think the STEM's over? It is not. If you pop over to the second, let's get a look, the third Mentors Without Borders stream, starting in about, let's say, 8 minutes, the FRC team 7539 will be presenting the mechanics of FEA. Alternatively, you're more than welcome to join the mass stream, where they will be presenting building on a budget. How far can you go with $1,000 in 5 weeks? That sounds like an exciting stream to watch. That'll be presented by FR team 4739. Thank you for joining us today.